Hello, hi, Professor Karthik. This is Samresh. Can you hear
Hello,
me?
I can hear you fine, and I'm using a mic and speaker. Can you hear me?
Yes, yes, it is fine. Only
Okay,
problem is now the plenary talk is still going on, so it
okay.
is supposed to end on 11 o'clock. So maybe will be little bit delay, like on maybe 5 minutes or something. Okay.
Yeah, that is fine. Who is the plenary speaker today?
There are two speaker. One first one is Professor Edward Chan. He has already done. Now the second one is going on Professor Shubodh from NTU.
Okay, okay.
So this is perovskite solar cell is going on.
Yeah,
Okay.
Shubodh Maishalkar.
Yes, yes.
Yes. Yeah.
So that's why, because we have to give sometimes the other participant will join then this parallel session.
Right, right.
Right. Okay, just wait for
Yeah, no problem.
okay.
One more
So,
thing, Samaresh.
yes.
Can I test out my talk? Can you give me the sharing privilege? Can you make me the co-host or whatever I need to be to
Yeah. You will
share
be.
my screen?
Yeah. So you join using that link only.
Yes, yes.
So
So hello.
I'm.
Yeah, Samresh, are you here?
Yes, sir. So problem is that in plenary speaker still going on. So
Oh,
maybe you,
okay.
okay. So we have to be little bit delay, maybe 5 minutes or something. Will start a delay.
Mhm.
So
Okay. Yeah,
uh,
because we have lunch time. We have lunch time 1 to 2. So I think
yes.
if
So
five
it
or
should.
10 minutes can be absorbed there.
Yes. Otherwise, no. We need some because people will then only will be able to join here.
Yeah. Okay, so 11:05 or something, no? We can start
Yes, sir.
11:05.
11:05.
Okay. Anyhow, I am here. I am there itself. And the speaker is also there, Dr. Karthik
Yes.
Shankar.
Yes.
Yeah,
Yeah.
I'm here.
Karthik, Professor Karthik is already here.
Okay,
So
hello. Good morning, Professor Karthik Shankar.
Yeah. Good.
Yeah.
Here it's afternoon, right? So good
Ah,
morning. Good morning. Good
good.
morning, Professor Rajendra Singh, right?
Yeah. Thanks.
Yes.
Yeah. Nice to meet you.
So,
Likewise.
Professor Karthik, can you share the screen like if it is working or not? You can check.
Yes, that's what I want
Yeah,
to check.
at least
Yes.
that is that thing we can do.
Okay.
Yeah, it is coming. Yeah, it is working. Fine.
Yeah.
Yeah,
Okay.
I think it is fantastic. Yeah,
Okay.
fine.
Your voice is also clear, right? No problem.
Yeah, font is also clear. Maybe like later on it can be shifted to this
Right.
presentation mode. Yeah.
Right.
Yeah.
Right.
Full screen mode you
Okay.
can put later.
Yeah, full.
Okay, I
So
think.
maybe we wait for a few minutes more, 5 minutes or
Okay.
something, so that
Okay.
people
Yes.
like particular session is over, plenary session.
Okay.
Okay. So, hello, Arindam. Good morning. Are you here,
Hello.
Arindam? Maybe he's muted actually.
Maybe.
He's muted or maybe just logged in right now.
Okay. So, sir, can you see my screen? I just shared that what are the talks today for this session. I think it is visible.
Yeah, right now it's not visible to me, but earlier it was visible.
So
Just
now,
just a few minutes, like just 10 seconds back, you started to share, and then I could see that.
let me share again. So now it is showing. Yes.
Yeah, I can see that. Now it is visible. Yeah, it's visible, but yeah, it's too small to read. So I better open my PDF file and then see there.
It is too open now.
Too small. Yeah, now it's better. Yes. Yeah, it's better now. I think now the participants have increased. And I think there are some participants who are coming from the delegate account or this attendee account, and they are not visible here. This is what has been told to me.
Yes.
Because otherwise the number of participants are much more than what are visible here. This is only for, I think, some special delegates, or you see, I don't see many students here.
Yeah, so they are not visible like those.
They are not visible. Yeah.
So maybe I can speak something. So there is an announcement. So yesterday we could not finish the poster presentation for all the poster for 2D materials and devices. So today from 3:30 to 5 o'clock in Hall 8, the remaining poster presentation will take place for the 2D materials and devices. So those who are the presenter as well as those who are interested can attend the Hall 8 from 3:30 to 5 o'clock. Sir, we should start now?
Yes, we can start. Yes, our time is already.
Okay, let me first introduce. So now we are in the second day for the 2D materials and devices. So today we have 3 distinguished speakers around the globe. So because one from Canada, Professor Karthik, one from USA, Professor June, and Professor Samit Kumare from Kolkata. So for this session, I am requesting Professor Rajendra Singh to chair this session, and he is a professor at IIT Delhi in Physics Department. He also the head of the Department of Center School of Interdisciplinary Research. He works on gallium nitride, gallium oxide, and 2D materials. So he is a well-known person internationally on gallium oxide and gallium nitride for materials to devices. Now I'm passing to you, sir, for conducting this session. Thank you.
Okay. So thank you, Professor Samresh Das. A warm good morning to all the invited speakers and distinguished invited speakers and participants. So the first talk in this session is by Professor Karthik Shankar from University of Alberta, Canada. So I will just take a few minutes to present in front of you the salient features of his biography. Professor Karthik Shankar, he did BTech in 1996 from in metallurgical engineering from IIT Delhi. No, sorry, IIT Madras. Okay. IIT Madras. Then he did MS from 2000 to 2002 in electrical engineering from Penn State University, USA. After that, he did PhD from 2003 to 2007 in electrical engineering from Penn State University, USA. And about his professional career, he did postdoctoral research from the Material Research Institute, Penn State University, from 2007 to 2009, almost 2 years. Then he joined as assistant professor in the Department of Electrical and Computer Engineering, University of Alberta, Edmonton, in Canada. And there he was associate professor with tenure from 2013 to 18. And since 2018, July 2018, he is a full professor at the same department. And he has actually a very distinguished career till now, as also like Governor's Gold Medal. He has been awarded for all-round excellence in IIT Madras, a Kodak Research Fellowship in 2003 during his PhD, and then recently Canada Young Innovator Award in 2010. So this is also a very distinguished award. And like professionally, he has authored over 140 publications, having citation 19,000 times with H index of 48, very impressive. And his research interests are actually, he works in the area of carbon dioxide photoreduction, photochemical water splitting, photocatalytic water remediation, plasmonic catalysis, 2D materials. So like he has a research interest spanning over different areas like self-assembled monolayers, spectroscopy, and also semiconductor physics. So it's really our pleasure to have Professor Karthik Shankar to have as like an invited speaker in today's session. So over to you, Professor Karthik Shankar. So you have about 25 minutes. So after that, okay.
Yeah, thank you very much, Professor Rajendra Singh. And so let me get into my presentation. I thank you for that very kind introduction. And like you mentioned in your bio of my bio, I did my bachelor's at IIT Madras, and because of that, I have a number of people I know and collaborate with at IIT Madras, because that's my alma mater. I also have some classmates who did their master's and PhD abroad and returned to India and have become faculty members at IIT Bombay, there's IIT Indore, IIT Ropar, IIT Roorkee. IIT Delhi, on the other hand, I don't know a lot of people, and I'm hoping that a conference such as this allows us to build bridges and make connections. So with that, let me begin my talk, which is on doped graphene and graphenic semiconductors, which are mass-producible, earth-abundant materials for photocatalysis and photovoltaics. And I also thank the organizers for the invite. So yeah, I just want to also thank my funding sponsors and the graduate students and postdocs in my group who actually did all of the work that I'll be showing in this presentation. So most of this talk is the application is photocatalysis. So where we are trying to harvest energy from the sun and use it to drive a chemical reaction. So two very important chemical reactions are CO2 reduction. It's the global warming problem and the increase in anthropogenic CO2 emissions in the lower atmosphere is everybody knows about it. And CO2 reduction is a potential technology, especially CO2 photo reduction is a potential technology to mitigate the CO2 and also get something useful out of it. Instead of viewing CO2 purely as a waste product, CO2 photo reduction seeks to transform CO2 into value-added products, into fuels and value-added products. So fuels would be things like methane, ethane, methanol, and value-added products would be things like carbon monoxide, which is used in syngas, and formate, which is a precursor for many for the synthesis of many chemicals. The other reaction is obviously water splitting, where you can split abundant source of hydrogen, which is water, especially seawater, into hydrogen and oxygen, and the hydrogen is a very clean, portable fuel. So these are two very important photocatalytic reactions that my group works on, but we also work on some other ones. We work on certain transformations. So we look at the transformation of uh, uh, nitrobenzenes into anilines, for instance, which I'll be talking a little bit about. Then obviously photocatalytic remediation of wastewater. So those are also other things that we are interested in. But this talk is on 2D materials, and here there is a few results we are particularly excited about that I'll be sharing with you. So in 2019, we had a JAX paper on C3N5. C3N5 is a brand new graphenic semiconductor because it has the essential sp2 hybridized backbone of graphene, but it also has the carbon atoms in graphene, a certain number of them periodically replaced by nitrogen to obtain a new stoichiometric compound C3N5, which is a low band gap semiconductor with some very interesting properties. So I'll be talking a bit about that. So graphenic semiconductors, as I'll hope to convince you, form a very interesting family of materials with some exceptional properties. So I think of them as very similar to organic semiconductors, but with very few of the disadvantages of organic semiconductors and all of the advantages. So when we think about organic semiconductors such as P3HT, poly-3-hexyl thiophene, or pentacene, or rubrene, or any of all these, or fullerene, what are some of the advantages that come to mind immediately? Well, there's the solution processability. There is the infinite tunability in the molecular structure, allowing you to tune the energy levels, particularly those of the HOMO and the LUMO, ability to tune band gaps, ability to also increase conjugation to tune the carrier mobility, and so on. So, those are some of the, and also potentially making things N-type and P-type and so on. So with the graphenic semiconductors, they retain all of those advantages of organic semiconductors, but they have some other advantages, which is that they are incredibly thermally and chemically resilient, which is something that is not true of organic semiconductors, because organic semiconductors are very vulnerable to moisture and oxygen, whereas the graphenic semiconductors are not. And also they inherently have higher carrier mobilities due to the sp2 hybridized backbone. So this is what makes graphenic semiconductors. So these are semiconductors which share the basic 2D sheet-like structure of graphene, but where several of the carbon atoms have been replaced either randomly or periodically with other elements, while the pi conjugation is preserved. So those are graphenic semiconductors, and they are 2D materials, and that's what I'll be talking about. So here's the outline of my talk. I'll start with talking about nitrogen doped graphene, which is the closest material to graphene that we deal with. And then I'll be talking about some plasmonic heterojunctions of nitrogen doped graphene with silver nanoparticles. So in a way, this is almost preempting one of the later speakers, Professor Samit Ray, who will be talking more about plasmonic structures, but I'm going to also talk a little bit here about plasmonics. And talking about plasmonic photocatalysis using nitrogen doped graphene with silver nanoparticles. Then I'll move on to these doped nanoparticles of graphitic carbon nitride. So these are nanoparticles, which means their sizes are very similar. They're in the 10 nanometer range, smaller than 10 nanometer typically. So very similar to inorganic quantum dots because they're also very fluorescent. Though technically it's probably not accurate to call them quantum dots because you don't see a very strong size quantization effect. But you do see some tunability in the fluorescence and so on. And there I'll be talking about fluorine doped carbon nitride quantum dots and phosphorus doped carbon nitride quantum dots and how they behave as photocatalysts and what their properties are. Then I'll go to C3N5 2D sheet. So C3N5 is this brand new graphenic semiconductor we're very excited about. Then I'll spend a little bit of time on core shell heterojunctions and then conclude my talk. So now nearly all of you here know that graphene is a zero band gap semiconductor. It is basically quasi-metallic. And that behavior of graphene also produces some disadvantages for optoelectronics, where a finite band gap is not only useful but necessary. Now, when you try to open up a band gap by interfering with the conjugation, and the most common way to do it is to transform the graphene using oxidation processes into graphene oxide, which is known as GO, or reduced graphene oxide, which is known as RGO. You end up creating a very large band gap. You end up creating a band gap that is more than 3 eV. So the RGO and GO are wide band gap semiconductors, and those are less useful for solar energy harvesting for the simple reason that they absorb very little of the sun's light. Only 5% of the solar energy resides at ultraviolet wavelengths. So the vast majority of sunlight goes unharvested when you use a wide bandgap semiconductor. So that motivated researchers around the world to dope these with RGO, to dope graphene oxide and reduce graphene oxide with hetero elements, with non-carbon atoms, which are known as heteroatoms. So they worked on nitrogen doped graphene oxide quantum dots, which are known as NGODs, and amorphous nitrogen doped graphene oxide quantum dots. And what they observed was they definitely observed a reduction in the band gap. So now, for instance, the NGODs have a band gap that is smaller than 3 electron volts, and the amorphous NGODs have band gaps that are even smaller. And this taught researchers a few things. It taught them, first of all, that when you replace carbon atoms in the graphene backbone with nitrogen atoms, you're creating more reactive sites here, which is useful for photocatalysis. You're changing the optoelectronic properties usually in a favorable manner because you're reducing the band gap. And you're also able to tune the band edges, the energy levels, which is important for oxidation and reduction reactions. The other interesting thing you realize is that these nitrogen atoms are not all the same. And I'll talk a little bit more in subsequent slides about that. And also that in some cases, the amorphous materials give you smaller band gaps than the more crystalline materials, which is actually unusual. And in organic semiconductors, it works the opposite way. The more crystalline a material is, the narrower the band gap tends to be. But here, an opposite pattern is observed. And part of the reason also has to do with the way the electron density is modified by these heteroatoms. So a bit more about the replacement of carbon atoms. So this is actually, I would ask you to concentrate on this picture first on the bottom right-hand corner, which is showing a graphene sheet where a certain number of the carbon atoms have been replaced by nitrogen atoms. But these result in slightly different types of nitrogen atoms. So if you look at the nitrogen atom here, which is in pink, which is bonded to 3 other carbon atoms, that is exactly replacing a carbon in the graphene sheet. And that is, by the way, known as a graphitic nitrogen atom. On the other hand, you can also have a defect here, which is a nitrogen that is bonded to 2 other carbon atoms and sits at the apex of a 5-membered ring. That is known as a pyrrolic nitrogen. And then you have a pyrazolic nitrogen, which is the non-apex atoms of a 5-membered ring. And then you have the apex of a 6-membered ring, which is the pyridinic nitrogen. And they all have slightly different properties, and these result in slightly different reaction sites. And electronically speaking, they interrupt the conjugation, or they force the local electron density to change in slightly different ways. And the other thing is that they are all accessible through solution processing and fairly simple. Not a lot of elaborate chemistry is required to go from the basic graphene sheet and dope it with nitrogen to reach majority pyridinic nitrogen or a majority pyrrolic nitrogen. It's possible. Okay, now I'm going to deviate a little bit and talk a little bit about surface plasmons, because the structure I'll be showing you is nitrogen doped graphene decorated with silver nanoparticles. Surface plasmons are these coherent and collective oscillations of conduction band electrons in metals, in noble metals, particularly gold, silver, copper, and aluminum. These are the resonance frequencies of these oscillations occur at visible wavelengths, and they are quantized oscillations, which are quasi-particles called plasmons. Plasmons can be differentiated into localized surface plasmons, which are essentially at the interface of noble metal nanoparticles and dielectrics. And then you can also have propagating surface plasmon polaritons, which are at the interface of thin films of metals and dielectrics. Plasmons are interesting because these optical resonances are tunable over the entire visible range by changing the shape of the structure, the dimensions, and the dielectric medium that surrounds these metal nanoparticles. Now, plasmons are also interesting for photocatalysis, and that is because of the electronic processes that occur in plasmons. So the plasmons themselves are excited by light in attoseconds, in 10 power minus 18 to 10 power minus 16 seconds, sub-femtosecond essentially. But the plasmons, if the light that excites them is switched off, they decay. And the plasmons decay essentially in a few femtoseconds due to electron-electron scattering through a process called Landau damping. And so the Landau damping ends up transforming the plasmon into a hot carrier pair. So it ends up transforming the plasmon into hot electrons and holes, which are represented here through an athermal distribution of carrier energy. So this is not a Maxwell-Boltzmann distribution anymore, but it's equivalent to a Maxwell-Boltzmann distribution at a much higher effective temperature. And hence, this is a hot carrier distribution. Now, these hot carriers then, over the next 100 femtoseconds or so, they cool through electron-electron collisions, and over a few picoseconds, they cool through electron-phonon collisions. So in about a few picoseconds, the hot carriers have completely lost their energy and returned to thermal equilibrium. So what plasmonic catalysis attempts to do is to utilize these hot carriers to do something useful, either generate electricity or to drive a chemical reaction in those few picoseconds. So in those few picoseconds, you try to drive a chemical reaction. And so you try to ensure that the excess energy of the hot carriers formed through plasmon decay are used in driving a chemical reaction. And so the best way to do that turns out to be to use a Schottky barrier. So if you have a Schottky barrier of a semiconductor and the metal in question, you can have a band diagram that results like this. So in this case, a wide bandgap semiconductor TiO2 is shown, which is N-type, which has a Schottky barrier with gold, and the hot carrier distribution you can see produces a lobe, a Gaussian band of carriers with energies much higher than the Fermi level. And these now have enough energy that they can be thermionically injected over the Schottky barrier. And the great thing is once they're injected, the chances of them recombining is very small, because TiO2 is a relaxation type N-type semiconductor, and there are very few holes. And so once the hot electron is injected into TiO2, it's very less likely to recombine. And so now you have a lot more time once the injection process takes place to perform useful work or to drive a chemical reaction using this hot carrier. The same thing can be done with other kinds of semiconductors, not only TiO2, and that's something I'll be talking about. Now, the injection mechanism does not have to be the sequential mechanism I talked about, which involves Landau damping and then electron-electron collisions and then electron-phonon collisions. It can also be more direct through a process known as chemical interface damping. Okay, so with that now, returning back to nitrogen-doped graphene. So nitrogen-doped graphene these are grown by large area chemical vapor deposition on copper foils and then transferred by pattern transfer technique over to the substrates of interest, which would be glass or silicon wafers. And so they're decorated with these silver nanoparticles, which have a slight, they're not perfectly spherical, they have a slight cubical shape to them. And this is just showing you that the silver particles are actually present on the nitrogen-doped graphene sheets. Now, the sheets are not monolayer sheets. They're typically bilayer or trilayer sheets. So they are not a single layer graphene. Nevertheless, their quality is fairly high because they were formed by large area chemical vapor deposition. And so the Raman spectra, which are very important in 2D materials, they provide the signatures, and this is showing the D and the G modes of graphene, which show that this is a graphenic material. We're also seeing the 2D Raman mode here. This is all certifying that you do have a graphenic material here. And then we are also seeing the plasmon resonance of the silver. It's somewhat weak, but it is definitely present. And the other thing is, okay, we have this nitrogen-doped graphene where graphene, a certain number of carbon atoms have been replaced with nitrogen during the CVD growth process by introducing a nitrogen-containing precursor. What is the band gap we have? And it turns out the band gap is about 0.26 to 0.35 eV. So it's a very narrow band gap semiconductor, nitrogen-doped graphene. Now, one very interesting thing we saw very early on in this material is when we used Kelvin probe force microscopy, KPFM, which was incidentally first performed by a colleague of yours, Ankur Goswami, when he was a postdoc in my lab. We saw that with nitrogen-doped graphene, even without any junction forming, with 450 nanometer radiation, we were seeing a small persistent surface potential difference develop when you subjected to light illumination. And when we decorated the nitrogen-doped graphene with silver nanoparticles, we were able to generate a much larger surface potential. So this is like a built-in photo voltage that was developing in this system. And that told us, okay, you have charge separation occurring in the system. You probably have a Schottky junction, and electrons are going one way, the holes are going another way, which is good because now we can use the separated electrons and holes to drive a chemical reaction. This is just numerical based finite difference time domain electromagnetic simulations, which are showing that there are hotspots generated on the silver nanoparticles at the silver graphene interface. So one thing the literature says is that when you have silver and nitrogen-doped graphene, you have fairly strong exciton-plasmon interactions, which I'm sure Professor Samit K. Ray will speak a lot more about. And the origin of this is twofold. On the one hand, graphene itself has plasmons, which can interact with the metal plasmon modes, but also the phonons in graphene also tend to interact and couple to the plasmons in the silver nanoparticles. And so you have a kind of dressed states because of this narrow band gap exciton, because the nitrogen-doped graphene has a fairly low dielectric constant, so the electron hole pair are expected to be bound in graphene. So you have exciton plasmon interactions, and the other aspect is that because of this strong interaction, instead of the sequential process involving Landau damping, you can have chemical interface damping where the plasmon directly decays into an electron on the graphene, on the nitrogen-doped graphene, and the hot hole remaining in the silver nanoparticle. So the prototypical reaction we examined is for was the transformation of NBT. So this is NBT. So you can see there's a benzene ring, there's a thiol group, and there's a nitro group. Hence the name NBT, nitro benzene thiol. Okay, so that's all it is, and it's actually technically 4-NBT because this is the para position or the 4 position. And when you and this reaction is a dimerization reaction when two NBT molecules, they dimerize and form an azo bond, a nitrogen-nitrogen double bond. And this reaction is triggered or driven by plasmons. And so what we found, so the green spectrum here is the Raman spectrum of NBT, and this is basically an in situ Raman observation. And the DMAB spectrum is shown in the bottom. It's the orange curve. And when you have just silver by itself without any nitrogen doped graphene, first of all, you see that the Raman counts are only less than 1,000. You see that the reactant peaks are very significant here, which correspond to NBT. And while the product peaks have appeared, the product peaks here corresponding to DMAP, they're quite weak. With just the plain nitrogen doped graphene, the product peaks are a bit stronger, but even here, but the counts are lower because you don't have this Serres effect, electromagnetic enhancement. And also you see that the reactant peaks are very strong. But when you use nitrogen doped graphene decorated with the silver nanoparticles, you see the synergetic enhancement. On the one hand, you see very strong product peaks, much larger than what you see for both the nitrogen doped graphene by itself or the silver nanoparticles by themselves. And you see that the reactant peaks are much weaker. So this indicates the reaction has more or less proceeded to completion almost, even at a laser power of 1 milliwatt, which is very small. To give you an understanding of what 1 milliwatt is, a laser pointer that you use when you're giving in-person PowerPoint presentations has a power of about 1 milliwatt. So that's a very low laser power, and it is able to drive this chemical reaction to form. The big takeaway here is that it's not actually a 1 electron reduction. There's 4 electrons involved, but you have a dramatic improvement in the photocatalytic performance when you use nitrogen doped graphene decorated with silver nanoparticles. And here are quantum dots of graphenic materials. So, like I said, these are truncated sheets which are also stacked 3D to form nanoparticles. And the idea was, if we host them on a semiconductor scaffold like TiO2, can we sensitize a wide bandgap semiconductor to make it absorb more of the visible light? This is particularly an issue for TiO2, which is a very nice, good catalyst, but does not absorb any visible light radiation. And here you see, immediately we had the spectacular performance where we see this brown color sheets, brown color samples, so which TiO2 is transparent, titanium dioxide nanorods, but now once we decorate the surface, actually partially embed the surface with these quantum dots, fluorine doped carbon nitride quantum dots, it becomes brown, which is a very positive sign. And these are all the materials characterization to confirm that such an embedding actually took place. So here our photocurrent density, this is our actual photocatalytic performance, is good but not remarkable. And then and we published this paper in Carbon. And then, this is showing more about the photocatalytic performance, which is, as I said, good but not remarkable. And then we went on to phosphorus doped carbon nitride quantum dots, which have a lower band gap and a different energy level alignment. And there's also DFT simulations that suggest that you kind of get a better hole transfer to the hydroxyl ions in solution. So we now used the phosphorus doped carbon nitride quantum dots, which are again 2D sheets or stack sheets, and we decorated this time on a TiO2 nanotubes, which is another one-dimensional structure. And this time we see that the phosphorus doped quantum dots have a stronger visible light absorption. And now once they're decorated, you see that the TiO2 absorbs across pretty much the whole visible spectrum. Also changes the energy levels. And we see a remarkable enhancement in the photoelectrochemical performance. We see photocurrents under AM 1.5 sun illumination of 2.5 milliamps per centimeter square, which you never see with TiO2 alone. And even with carbon nitride materials, this is an unusually high performance, and we published this result in Advanced Optical Materials. And then we moved on. We tried to create an entirely new graphenic semiconductor C3N5, which has this new composition. GC3N4 is known for about 15 years, but C3N5 is almost entirely new. It also had a lower band gap. It's still a 2D material. You can see the sheets. Also still has the characteristic spectrum. We did NMR, we did yields, and we did a lot of characterization to confirm the properties. But the one thing, this is a very informative slide, because while GC3N4 has this yellowish color powder, C3N5 is a bright orange color powder, and you see this in the UV spectrum. It ends up absorbing a lot more of the visible spectrum because it has a lower band gap. GC3N4 has a band gap of about 2.6 to 2.7 eV. C3N5 has a band gap of 1.7 eV. So it's a noticeable, significant reduction in the band gap. Also, C3N5 is not fluorescent, unlike GC3N4, which is strongly fluorescent. Yeah, here again, we did scanning Kelvin probe, which showed a strong photoactivity and fairly good charge separation, which then motivated us to use it in photocatalysis. Again, we used it. Again, this is not 1 electron, I'm sorry, it's 4 electron photoreduction of nitrobenzene thiol to DMAP. And once again, we saw that the C3N5 works very well. Again, when coupled to silver nanocubes, you get a synergetic activity very similar to what I showed you with nitrogen doped graphene. You get plasmon enhanced photocatalytic reaction here. One thing I don't mention here is that we also used it for in perovskite solar cells, which today's plenary was about. And in perovskite solar cells, the C3N5 again had a number of positive aspects, which we reported in our JAX paper. First of all, it behaved as a superior electron transport layer as well as a hole transport layer because of the positions of its HOMO and LUMO, which is which is very useful, because electron and hole transport layers of the right kind are very important to get the best efficiency in perovskite solar cells. We also blended it into the active layer of these perovskite solar cells, where we observed a pronounced trap passivation effect. And again, we observed an enhancement due to that as well. So I've focused on photocatalysts in this talk, but we also can use these carbon nitride materials in solar cells. So just wanted to point out. So I'm now here almost to my last 3-4 slides. So this is our recent cover in Advanced Functional Materials. Here we formed a heterojunction core shell architecture. It's an exotic heterojunction because we used SNP, which stands for tin iodine phosphorus, which is a ternary semiconductor which has a natural double helical structure like DNA. It has this one-dimensional structure, and the GC3N4 wraps itself spontaneously around this one-dimensional structure to form this core shell structure. You can see the lighter areas here are the GC3N4, and the darker areas are the SNP. We call the SNIP, we call it SNP. And this was in collaboration with the Technical University of Munich. So that's just and it also behaved as a better photocatalyst as a consequence of this core shell structure. And so in conclusion, nitrogen doped graphene coupled with silver nanoparticles is an exceptional photocatalyst for surface catalytic reaction. C3N5 is a brand new graphenic semiconductor synthesized in the Shankar group that has shown promise in photocatalysis and photovoltaics. GC3N4 spontaneously wraps itself around the inorganic double helical semiconductor SNP. The resulting heterojunction is a good water splitting photocatalyst. Heterojunctions of graphenic semiconductor nanoparticles with TiO2 nanorods have shown promise in CO2 photoreduction and water splitting. I haven't shown you the CO2 photoreduction part, but I showed you some of the water splitting performance. Point number 5 is that graphenic semiconductors also provide an excellent playground to explore plexitonic effect. These are plasmon-exciton coupling effects due to the exciton-plasmon coupling and the chemical interface damping. I also want to point out that we are open to collaborations with like-minded researchers on these problems and related challenges. Thank you very much.
Okay, so thank you, Professor Shankar, for this excellent talk, and the kind of work that you have shown is really, really like inspiring, I think. And I think right now we have maybe like time for one or two quick questions. So I will actually, let us say, start this thing. In the meantime, if anyone else has some question, they can put it in the chat box. So I just wanted to ask that this silver nanoparticle and
Right.
this n-doped graphene, this heterojunctions sort of like you have made, and then you did the Kelvin probe microscopy. And without illumination, with illumination, you could see the change in the surface potential. So this surface potential change, I think, might also be depending upon the size and shape of these silver nanoparticles.
Yes, of course it does. It's particularly, it's not as sensitive to size as it is to shape. So the nanocubes which we are using are better than the spheres which you can buy commercially. We make our own silver nanocubes. The spheres don't give you as many hotspots, and the silver nanocubes, because they have corners, generally give you a higher local field enhancement, a plasmonic field enhancement, and a higher density of hotspots.
Okay, thank you. So,
Rajat, can I ask you a question? This is Arindam.
Yeah, please, Arindam, go on.
Yeah, good. I think it's a very interesting talk. I'm not from this field, I'm a physicist, but I just wanted to check with you regarding the plasmonic excitations in graphene. I mean, even if it is end-doped graphene, because of its rather small density of states, the plasmons are way in the
infrared.
Yeah.
I don't particularly think that's an important mechanism. Though it might in a second order way or a third order way, it might be influencing some of the coupling, but it's not the dominant source. I really think that it's the excitons in graphene which are dressed by the phonons, which are what are interacting with the plasmons. But to be honest, Arindam, we don't completely understand this, and we are kind of trying to develop tools and also collaborate to get a deeper understanding of what is really going on in the system.
Thanks. Yeah, that's what I was confused.
Okay, so in the interest of time, we have to now close with this talk. So thank you again, Professor Karthik Shankar, for this excellent presentation.
You're
and
welcome.
Yeah, thanks. So our next speaker is Professor Jun Liu from University at Buffalo, USA. So a very brief CV. I just would like to highlight the salient points of his CV. So he is currently an assistant professor in the Department of Mechanical and Aerospace Engineering at the State University of New York at Buffalo. And he is also an affiliated faculty in Research and Education in Energy, Environment and Water Institute at UB, I think University of Buffalo. So before this, he received his PhD in Material Science, Materials Engineering from the University of Alberta, Canada in 2018. So it's from the same place as the previous speaker is from. So he was a postdoc fellow in the Department of Chemical and Biological Engineering at SUNY Buffalo for almost 2 years. And he is passionate about understanding and manipulating fundamental physics at material surfaces and interfaces for energy and sensing application. I think that is very, very important area of research nowadays. And he's also pioneer in tribo tunneling and dynamic Schottky direct current generator. So he has about 30 plus referred publications in high profile journals. Okay, there's Nature, Nanotechnology, Science Advances, Materials, Horizons, Nano Energy. So very, very let us say high impact factor journals. And Jun is the recipient of also many distinguished awards. And I think with that, I will not take too much of time. So we are eager to listen from Professor Jun Liu about next generation mechanical energy harvesting based on semiconductor. So you have about 25 minutes for your talk. Okay, please.
Sure. Thank you so much, Raj. Can you hear me? Well?
Yeah. We can hear you clearly.
Great. So thank you so much for your kind introduction, and it's my great pleasure to have a chance to give a presentation today. Please, I would beg your pardon if I make any mistake because already 1:15 early here in the East Coast. So I'll try my best. All right. So today I'm going to talk about this the next generation mechanical energy harvesting based on new semiconductor materials. So we all learned in high school that if you move a coil in a magnet, or if you move a magnet in a coil, and you will be able to get a current out of that, right? That is the well-known electromagnetic induction, which was found by Michael Faraday in 1831. And believe it or not, this is still the mechanism people are used for electricity, like hydroelectricity or wind energy, or the energy recycling from electrical car. And there's also a growing demand for self-powering solutions for more and more smaller and smaller devices, right? Which is the basic elements of the Internet of Things, the smart healthcare, and the wearable electronics. So in terms of the energy sources, we can have like traditional mechanical one, and you can also use take advantage of the thermal energies around us, or the solar energy, or the radiative energies. But for thermoelectric energies, we have to deal with the low ZT value, or the performance of the thermoelectric materials, as well as the random thermal energies. Right? And then for solar energy, one of the drawbacks is that late at night you won't be able to have access to solar irradiation. Right? And then radiative frequency energy harvesting, another type of energy, but generally the efficiency will decay dramatically when the distance is long. Right? So mechanical energy is all around us, right? Like we have wind, we have water flow, we have moving cars, and then people walking around. And then people propose different ideas to collect those energies. So one of the ideas is that can we take advantage of the triboelectricity? So what is triboelectricity? So this is a very common phenomenon we all see in our daily life, right? Especially in north parts of the America, where we have a very dry winter. Right? Like you can easily get electrically shocked in the winter time. So those are the triboelectric charges, right? And then we also learned in high school physics is if you rub a piece of glass and with a piece of silk, you will be able to get a positive or negative charges on the materials. So depending on the materials you will have in this context, you can have either positive or negative charges. So can we take advantage of those charges? Right? The answer is yes. So the traditional way of doing that is you take a piece of, say, a metal or another piece of insulating materials, like a piece of polymer. So if you contact them with each other, you'll get a positive and negative charges. But those charges are trapped on the surface as electrostatic charges, right? So basically you can imagine that you have a charged capacitor. And by moving it up and down or back and forth, and you will be able to get a changing voltage or a changing capacitor. And as a result, you will get a very transient AC currents, right? So here you can see that when you have a changing voltage here, you will get a small peak of the outputs. However, there is a serious problem of that. So the reason why we don't kill ourselves in the wintertime when you take off your sweater is that although you can get a really, really high voltage, as high as 1,000 volts, but however, the current density is extremely low, right? You don't have really a lot of currents flowing in the system. And this is understandable because you can, if you look at the equation here, the current is only decent when you have a fast changing capacitor in such systems. And we also know that the efficiency would be very low if you have a frequency lower than 10 hertz. But however, if you look around us, most of the ambient vibrations or mechanical energy has a frequency less than that, right? So that means intrinsically, those old ideas may not be really satisfying, right? So, so about 2 years ago, we have a very interesting discovery, and one of my old colleague, Dr. Ankur Goswami, I think he's the an assistant professor in IIT Delhi right now. So we used to work in the same group. So he proposed this MOS2 modulators with pulse lattice deposition. And initially, we just want to know the electrical conductivity of these materials. Right? And then normally what you do, you have a atomic force microscope tip, and which is conductive. We have a conductive coating on the top. And then normally you just apply a voltage and see how much current you will have. Right? And then on that day, I made a small mistake. I forgot to apply a voltage. I forgot to apply a bias here. But surprisingly, we still see a constant current signal out of the screen, which doesn't make sense at all, right? When we talk to people, they say, there's no way. Remember, in the previous slide, we see that all the traditional piezoelectric or triboelectric signal, they all in the very sharp transient AC form, right? There's no way you can get a DC current. So we did a lot of experiments. We excluded all the artifacts, and we found out this is a phenomenon, a universal phenomenon, as we will introduce in the following slides. So what is the condition of observing the phenomenon? Right? So we did the so-called in situ IV curve. So basically, you can move your AFM tip to different positions on the top of the materials, and you do the IV curves. Right? And then here we have 3 different crystallograms. We have 1, 2, 3 here. And you can see that on grain 2, you have the highest current outputs. On grain 3, you have some. And on grain 1, you don't have any outputs, right? And then we did the IV curve, and then we found out is that this phenomenon only happen when you have a Schottky contact between the tip and sample. But if you have some sort of ohmic contact, then nothing will happen. So that's the first conclusion we have. And we also did, try to fit the data and then try to get the, what is the energy barrier for this phenomenon, and then the ideality factor of the Schottky junctions. Professor Shankar just talked about, the hot electron generation in a Schottky junction by Foley radiation. That is for plasmonic hot electrons, right? So here we are thinking that this is probably because of a very similar electronic excitation process. However, this is due to friction. And in a very similar way, you can generate a DC currents because of the existence of this Schottky contact. So this is very unusual and very different from the traditional way. So we had this first work published in Nature Nanotechnology in 2018. But however, after we published the paper, we have a lot of questions, right? First, is it a common phenomenon for all the metal semiconductor material system? Right? So we talk about in a metal insulator system, there's no way you can get this thing, right? Is it common for the other materials? The other question is high current output scalable? So right now we want to get several nanoampere from AFM, right? Can we actually just scale it up? The third question is, what is the fundamental mechanism, right? We still don't know why you have a DC outputs, right? Can we improve the voltage outputs? So right now we have a relatively low voltage outputs, and how does this mechano electrical coupling happen? So that's first try to answer the first 2 questions. Is it a common phenomenon, and is it scalable, right? So the answer is yes. So first what we did, we pick up another material. So we tried on silicon. I mean, everyone are familiar with silicon. Right? We use that for solar panel or for your cell phones. And first, we still use AFM. We got a very similar phenomenon when you, in the absence of bias voltage, you still get a DC current out of that. And by applying more force, you get more currents, right? And how about the open circuit voltage here? So what we did, we apply another bias to the system and see when this currents will diminish and reverse its direction. So right now from here, so we can see that the bias, when you apply around 100 to 200 millivolts, then these currents will disappear and then reverse its direction if you further increase the bias. So we know that, okay, so right now we have an open circuit voltage of about 100 to 200 millivolts for here. And then people ask again, right? Like you AFM guys has been doing all kinds of things at nanoscale. Can you actually really scale it up? That's always the question people ask a science scientist, right? And the first thing came into my mind is to pick up a metal around me, and then the first thing in my eyes is a tester probe, a multimeter probe, which is made of stainless steel. And this is everything. This is something you can all find in a lab, right? So I just take a piece of silicon and then coat it with aluminum as the back electrode, and then just rub it on the surface. And then surprisingly, you will see that when you have this back and forth, all the rotational rubbing fashion, you will see a continuous current and voltage output. And when you do the rotation, especially when you do the rotation mode, you will see a simultaneous current output and voltage outputs. So this is very different from the previous one. Remember, in the traditional triboelectric or piezoelectric, you only have a sharp change in current outputs when you have a change in voltage, right? And then we calculate the current density. So here we have several microampere out of a multimeter probe. And then the current density we have here, which is current normalized by the contact area, which is around, it's on the order of 1 to 10 ampere per meter square. So, and furthermore, if you use even smaller tip, you get a higher current, also in the DC form. So if we compare that to the state-of-art piezoelectric or triboelectric generators, this is about 3-4 orders higher, right, compared to theirs. So this is extremely high currents in the DC form. So if you compare the features here, again, on the right side, you have those traditional way of generating currents. So they are all in a very sharp features, but in our case, we have a continuous feature. So what does it mean? It means that if you integrate the products of voltage and currents as a function of time, that would be the energy, right? So the total energy available for us is much higher than the traditional ones. And also, this current can be generated no matter what frequency you have, right? And then why it happens? So this is something really bizarre, right? I mean, you never expect a DC current out of that. So what we did, we use atomic layer deposition to which can control the oxide thickness on the top of silicon. So for silicon itself, it has a native oxide with a thickness around 1 to 2 nanometer. And then what we found is that the current outputs will decrease exponentially as these deposition layers. So this is in good accordance with the quantum tunneling behavior of our charges, because, for example, if you have a STM, we all know that the probability for you to find electrons across an insulating layer is in exponential relationship. Right? So now we have a better feeling right now. So instead of staying on the surface like an insulator, those charges or triboelectric charges, they will quantum mechanically tunnel through the thin oxide between the physically contacted metal and semiconductor, and then they will get directly conducted throughout the system. That's why you have a DC here. Right? And here's another little demonstration here. We have a multimeter showing the voltage of a capacitor, and then this capacitor is connected to a silicon and a probe. So I'm using my hand to give a tiny little back and forth friction with pretty low frequency, right? And then you can see that the capacitor can be charged without any rectification, because remember, we have a DC current here. We don't have to have a bridge type of a circuit to rectify the AC signal into DC. So it can be directly charged. Right? So this shows that this phenomenon is universal and scalable. Right? And shortly after that, people around the world trying to trying to get more feeling about this phenomenon. And for example, people try with large area graphene composites, and then they're trying to rub it on the silicon and then test it that this phenomenon is sustainable. And I think here they test it for more than 10,000 times, and you can see that the output is still there. Okay? And then they also tried, different atmosphere, like in the vacuum, nitrogen, and in air, they find very similar phenomena. Right? And also try different velocity and the pressure. So if you look at the contact interface, if you have two bodies contacted with each other, so what happened? Right, so this is actually a very complicated problem, which has puzzled the scientists for a long time, right? Because this is a multi-scale, multi-physics coupling. So at microscopic level, you have the so-called single asperity with a size of several tens nanometer. They basically try to interact with each other at the interface, and then, because of these small features here, you would expect much higher pressure at these single asperities. So normally we don't see a lot of pressure if you just press your two hands together. But microscopically, you have a lot of those single asperity with high pressure. Right? So those pressure can probably cause, photoelectric effects or interfacial dipoles. And also down to the quantum level, it can also influence, the electron cloud interaction or the electron following interaction, which can eventually lead to some of the, tunneling or semiotic emission and the non-equilibrium Fermi level alignments and things like that. So we believe those are will all influence the DC generation phenomenon we have. So now we know that if you have a small feature, it seems like the power can be enhanced. Can we actually use a nanostructure to enhance the power outputs? Okay. So the first thing came into our mind is the MEMS tip array. And then we found out it's actually really costly and time consuming. So is there any other things we can use? So we tried this a special material called carbon aerogel. So it's a powder structure with if you look at the cross section of these materials, it has a lot of nano protrusions. Right? So basically, it's like a nano forest. Right? And then by rubbing the carbon aerogel on the top of silicon, we can see that the voltages are enhanced almost by 10 times, from about 0.3 volts to 2 volts. And the current output from this tiny little aerogel is increased to about 15 microampere. And with this electricity, we'll be able to light up LEDs. And we're also, trying to develop some of the theoretical models. For example, here we have this collaboration with Professor James Chen here in UB, trying to use molecular dynamic simulation to study and also trying to develop an electrical dipole formalism to see how does the interfacial electrical dipoles formed and evolves when you have a contact and a friction. So we also compare the difference between, the charged charges and the directly conducted charges by KPFM and AFM. So basically, KPFM will tell you the electrostatic behavior, while the conducting AFM will tell you the direct conduction behavior. So we found that these two are actually different in this phenomenon. And we all know that in friction, that if you have a really rough friction, you're going to cause a lot of a wearing problem, right? Like this is not really good news for a long-term device. So we're also thinking that can we actually take advantage of some of the two-dimensional materials in the future, such that you have a so-called superlubric contact, but at the same time, you can generate electricity. So here's a further investigation we have, where we try with the large-scale MOS2 single crystal layers. So we try with different materials, right? So for example, in configuration B, we have this MOS2 sliding on a metal. So you can see here, with different metals you use, you can either get positive or negative outputs. So we believe this is related to the surface potential difference or the work function difference between the two materials. And we also tried MOS2 on oxide, for example, titanium dioxide with different thickness. So this is we got similar phenomenon, and seems like there's an optimal thickness for the oxide here. And also we noticed that here, instead of a tunneling mechanism, it seems like the e-beam evaporated oxide has some conduction panel pathways for the electrons to go through. Because right now, if you're the thickness is on the order of several tens nanometer, tunneling mechanism will not work. So there's still some charge generated on the surface, but they can actually get conducted if the materials itself, interfacial material itself, it's semiconducting. And we also tried on silicon, and depending on the doping concentration and type of the silicon, we also observe this phenomenon. So which indicates that in the future, we might have a chance to develop the so-called superlubric nanogenerators. So this is another phenomenon, new phenomenon we observed based on the previous one we have, right? So previous one, remember we had this friction between metal and semiconductor, and we found out that this can generate a constant voltage and currents, right? And then one day I was asking one of her undergraduate students, Lane, whether we can do some testing with irradiation, right? Because we all know that semiconductor has this photovoltaic properties. So the very first experiment was really rough. So we didn't have the solar simulator on that day. So we just tried with a flashlight of a cell phone. And then from the oscilloscope, you can see that when you have a friction here in the middle, you have a signal level in the middle, and then you have a jump when you turn the light on. So we find out this is actually a new phenomenon, right? So you have a coupling effects between the tribal tunneling voltage and the photovoltaic voltage. And well, it seems like the currents also have a jump here when you have a irradiation here. So this is very interesting because in the same time, we find there's another group, they also tried very similar system, but with perovskites materials. And then they find a very similar phenomenon. We published the same papers in the same journal. And it got accepted in the same time, which is quite a coincidence. And then we also received a very warm review from Professor Daniel Lax. They give us comments saying that we are shining lights on triboelectric phenomenon, which is truly compliments. And we also investigate the charge behavior. So why you have a coupling effects here? So it turned out that if you look at the lifetime of those charges, right? So we compare the decay of the signal with and without irradiation, or with or without friction. Then we found out is that these two electric field, one is generated by friction, the other one is generated by photoillumination. They can actually couple with each other and then enhance each other. So we proposed this band energy diagram mechanism based on that. And of course, we try with different doping concentration. We find out that you have to pick up the right doping concentration and type. Because right now, what you have to do, you have to make sure that your photovoltaic potential, the photo voltage, has to have the same direction of the tribal voltage, right? Otherwise, they will just cancel each other. So in order to see the positive effects, you gotta choose the right doping concentration and the doping type. And then we also propose that the tribal things and the photovoltaic things happen on the different parts. So the friction generated excitations happen right at the interface, the very out interface between the metal and your semiconductor. But however, for the photovoltaics one, you have a electronic excitation inside the surface charge region, whether it's a depletion one or accumulation one. So basically, it's the two things happen in two different places, but however, we have coupling effects here. So we also tried the conductive AFM on MOS2. We find very similar phenomenon when you shine a laser on the top. So there are actually additional photocurrents on the top of the Triboel currents. Right? And we also come up with a little demonstration. We just simply put an ITO, transparent glass, and then rub it on the top of silicon, and then we shine a light on the top and then trying to see the macroscopic coupling effect between the two. And then we did see the effects. However, here the current is still a little bit low because of the, we believe it's because of the contact resistance. So if we improve that, we can definitely, push it to another level. And shortly after that, since we discovered this phenomenon, we have seen a lot of enthusiasm in this topic, right? And then people start trying with all kinds of combination. They even propose, the moving p-n junction, right? Not only metal and semiconductor, they propose like p-type silicon or n-type silicon, as well as like graphene, two-dimensional material-based system, and conducting polymer systems. And then very recently, people also extended this phenomenon to a liquid semiconductor contact, because once you have a liquid and semiconductor interaction, if you have a moving liquid, a very similar phenomenon can also happen. So we can see that it's a very fast-growing topic right now, and a lot of rich physics under that as well. So to summarize, we observed this new phenomenon of DC generation with high current density in frictional Schottky contacts, and then we find it's a common phenomenon for semiconductor system. The current density is about 3-4 orders higher than the traditional piezo and triboelectric one. And we also propose that the generation might stem from the interfacial electronic excitation and tunneling, rather than the electrostatic charges and dielectric displacement current because of the vibrating capacitor. And we also find there's some sort of a size effects in this DC generation phenomenon. So we have to have further investigation on the more details and how we take advantage of how we manipulate it for improving the power. And it's also, we can use different materials and heterojunctions, and also different synergetic effects, right? Now, probably in the future, we can discuss more, because for semiconductor itself, it has a lot of physical properties. We can probably introduce other stimuli to trigger new coupling effects. So in the future, as a envision for the future, if you can use that for self-power IoT, or self-power implantable or wearable electronics, or even in the aerospace. So we believe there will be both fundamental as well as application future promise of these technologies. So last but not the least, I would like to thank the 2 graduate students joining my group in this fall, as well as all the collaborators from different places. And without their help, we will definitely not be able to get those exciting progress. And we have a new group website here. So we are also very welcome. So for any collaboration opportunity and discussions. And thank you very much. And last, I would like to quote Albert Einstein's words: "In the middle of difficulty, always lies a great opportunity." And hopefully we can go through this COVID crisis together in next year. Thank you so much.
Okay, so thank you, Professor Jun Liu, for this very, very interesting and scintillating talk on this frictional metal semiconductor contacts. So I also work in this area on metal semiconductor contacts, and since last almost 2 decades or so. And I always feel that this field never saturates, this metal semiconductor contacts. And now you have brought another dimension to it and sort of rejuvenated this field. I think it is going to, in future, going to have a huge impact actually on the research, particularly in this area and triboelectricity. So since we are running short of time, I will pick up one question from the attendees. Dr. Hemajit Singh has asked, I am just reading out his question. In slide number 21, to get the tribo charges, the metal probe you are showing on the schematic diagram is conducting AFM tip. So there is a conducting AFM tip for this thing, this metal probe. So if it is, while rubbing, does the tip's conducting coating get affected? So this is the question.
Yes, so this is a great question, actually. So the metal coating will influence the output in a couple of different ways. So for example, in the first case of between this MOS2 metal case, we can see here, if you try with different metal, you will going to see different potential directions, right? I mean, if you know some knowledge of Schottky context, the direction of the building potential will depend on the work function difference of the two materials. Like that's what determine how the energy band will go near the surface, right? For example, here we can see that with different metals, so actually the magnitude as well as the direction of the output voltage will be different. So we kind of propose that this is also related to the different, work function of the materials. So I think that for metal parts, that will definitely play a role. So most of the time, for example, especially if you check the literature, some of the people use aluminum material. Aluminum has a relatively lower energy work function, right? Like around 4.1, 4.2 or something. And sometimes you can get a direction of the currents for silicon metal context. So that's one thing. Second thing is that we also found that the interfacial layer, just like in a MOS structure, like a metal oxide semiconductor or metal insulated semiconductor heterojunction, that the interfacial materials will also influence the power outputs, the direction and magnitude. So that is also a very interesting area to investigate.
Okay,
thanks.
So thanks, Professor Jun Liu, again for this very, very interesting talk. So thank you. Yeah,
thank you so much.
Yeah. So now we move on to the next speaker of this session, and Professor Samit Ray is already here.
Yes, I'm here.
Okay,
yeah.
Hello. Good.
Yes, hello, how are you?
Yeah, good afternoon. Now it is already good afternoon. Hello, sir. How are you?
Right.
Yeah. So Professor Samit Ray, he's a very well-known person. I know him since last 1.5 decades, and I think we had a lot of interactions at various platforms. So it is my pleasure and honor to introduce Professor Samit Ray, who is currently the director of S.N. Bose Center in Kolkata. And briefly, he is a professor in IIT Physics Department, IIT Kharagpur, and he has served as the Dean, Postgraduate and Research Studies, and professor and head of the Department of Physics. And he is also the founder head School of Nanoscience and Technology at IIT Kharagpur. So his research interests are in the area of semiconductor nanostructures, quantum dot, photovoltaics. He is a very eminent researcher, well known nationally, internationally, and is fellow of the National Academy of Sciences, Indian National Academy of Engineering, West Bengal Academy of Science and Technology, and also the recipient of INSA Young Scientist Award, UGC Homi Bhabha Award, MRSI Superconductivity Material. I think I can keep on going. So he has more than 325 research publications in international journals, 7 book chapters, and he has also co-authored a book on strained silicon heterostructures, materials, and devices. I think he's already, let us say, a very well-known person. So we are eagerly looking forward to listen from Professor Samit Ray. So please, Professor Samit Ray.
Yeah, thank you, Rajendra. Is my slides you are able to see?
Yeah, we can see it very clearly.
So, yeah, thank you so much. But the introduction was too long, of course. And let me start thanking with Samresh and Ankur, definitely for inviting me. And I see from the very beginning I am there, so it was very interactive, very interesting. But unfortunately, we are meeting online this time due to COVID. But still better, at least for the students, research students, they can still share their experience. That is one very good thing. Okay, so this is the title of my talk. Of course, I am also at the Department of Physics, IIT Kharagpur, and all this work has been done at IIT Kharagpur by my research student Rup Chaudhary. It is out of his PhD thesis, so I'll be presenting that. And since this is basically a symposium on 2D materials, so I don't think I have to give any introduction of 2D materials, their uniqueness or their novelty, and how they are attractive for nanoelectronic and nanophotonic devices. But since I'll be doing these materials, I will be presenting the result of these two materials, MOS2 and WS2, and it's a very well-known band structure that have been reported in the literature. That both of them are the bulk, of course, in indirect band gap in the bulk. But when you bring them into the monolayer or even a bilayer, yeah, bilayer will be a little bit different. We can get a direct band gap at the K point. So that is very, very interesting, particularly for many applications, and particularly I'll be talking about the photonic applications. And not only that, other important features of this, due to strong spin-orbit coupling, there is a band splitting at the K point, particularly for the both conduction and the valence band. But the valence band splitting is quite high, about 0.5 to 0.7 eV. So it can be very, very useful for many electronic applications. Okay, for photonic applications, the important thing is that, of course, which photons interact with this kind of 2D materials. So we can start with, of course, the graphene is the semi-metal, but if you start with graphene, silicene, arsenine, etc., this is beyond that mid-infrared, 5 micron and above. On the other extreme, we have got, of course, 2D materials of insulators like hexagonal boron nitride. So this is useful for UV photodetector, ultraviolet applications. And in between, you have got lots of materials starting from black phosphorus on the infrared to all transition metal dichalcogenides in the visible to near infrared range. And everything is so attractive. So people are making a lot of van der Waals structures using 2D materials, and there are lots of here, including Arindam and many other groups. They are already demonstrated van der Waals photonic devices using these TMDCs. Okay, so then other interesting things in 2D materials is basically their excitonic behavior. Because of the, as I said, because of the strong spin-orbit coupling and the reduced dielectric screening and strong modified Coulomb interactions, many of body effects, they show some very, very interesting. As you know, normal semiconductor is very difficult to get the excitons stables at room temperature. And forget about the zinc oxide, the gallium arsenide and silicon, germanium, etc. You have to really cool down to the low temperature, etc. But here, the excitons are actually stable at room temperature because the excitonic binding energy is quite high. So depending upon the things which you are probing, you can get either dark excitons. If you have a spin forbidden transitions, you can get bright excitons when the spins allow conditions. Yes. Am I okay? Am I audible?
Yes, it is fine, sir.
Okay, that's fine. Yeah. So then you can get also dark excitons, particularly spin forbidden transitions. Then you can have a excitonic complexes like a charged excitons, like a trion or trion positively charged trion, negatively charged trion, as well as the bi-excitons. So that's why so interesting, particularly for photonics and quantum photonics applications. Now my talk will be a little bit more on the plasmonic. I heard some of the talk of the Karthik Shankar talking more about the plasmonics. So my interest will be, of course, these interactions between the plasmon and the excitons, and somehow in some cases actually my main emphasis will be these ultra-fast tangent spectroscopy studies of these kind of interactions. Okay, so as you know that plasmons are nothing but the sub-wavelength metal nanostructures, and they can actually are a very, very strong absorber of electromagnetic radiations. So that depends upon what plasmons you're using, gold, silver, and what are the sizes, what are the shapes. So they're very, very strong light absorbers. On the other hand, 2D layers are basically they're monolayer thick. So the light absorption capability is really very, very small. So interactions between these plasmons and 2D materials are very interesting because you can absorb a lot of light due to the surface plasma resonance in the metal nanoparticles, and you have got a very nice strong charge mobility layers. You can try to make some devices with the enhanced so-called photo absorption characteristics. Okay, so so the traditional devices, of course, the people tried, which has been already reported by many people, is basically a metal semiconductor, metal photodetectors, which have got mono or bilayers of 2D materials, put plasmonic nanostructures, and basically collect the photogenerated whole pairs. And since the thickness of these layers are very, very small, so the recombination is very small. So that gives rise to very high responsivity and detectivity of these kind of devices. On the other hand, you can use, of course, use the heterojunctions like Van der Waals heterojunctions and try to get a built-in electric field, and you can do more and more enhancement of this detector performance. So in this talk, I'll be covering. I'll try to do it on time. I'll try to cover 2 to 3 exciton plasmon coupling lasing. So the first one is basically conventional, what we call the conventional surface enhanced Raman scattering, or basically some conventional partial enhancement. In that case, we have got a arbitrarily situated exciton and plasmonic peaks, but we don't tune much of the metal nanoparticle size or etc. So the coupling is normally very, very weak. As you see here, this is the excitonic absorption peak, this is the plasmonic absorption peak, and there is a very, very weak coupling. And we can get a resultant absorption or emission spectra where actually either emission or absorption intensity is enhanced by significant amount. So this is actually called the partial enhancement. On the other extreme, if you go to when you go to very, very strong coupling regime, you get something very interesting phenomena called a quantum phenomenon called the Rabi splitting. And this is very, very popular in the chemistry, particularly the J aggregates, dye, and the nanoparticles. So as you can see here that you try to tune your size of the nanoparticle in such a way so that exactly matches with the plasmonic absorption peak and the excitonic peak. And if it is strong, coupling is very, very strong, you get some kind of a Rabi splitting, or which is nothing but a signature which is manifested by the energy branching. So you have got 2 energy branches, one is the upper energy, one is the lower energy. So this is a very interesting phenomenon, and this can generate what is called polar return, which I will discuss later on. The intermediate coupling gives another phenomena, which is also called a quantum interference effect. It's called the phonoresonance. So in intermediate coupling, the green one is the plasmon band, broad, and this is the excitonic absorption band, and the resultant is nothing but a very asymmetric line shape, which was first predicted by Fano long back, 1961, kind of S-shaped curve. So the question is that the question that you ask, can we get all these line shapes or all this behavior in different plasmonic and excitonic coupling in 2D materials? So that's the question we asked. So now let me start with the first one, which is more conventional. So obviously we started with this one, that where we have actually made a not monolayer WS2, we made a few layers of WS2 by simple chemical exfoliation using lithium ion, and intrinsically these WS2 exfoliated are chemically exfoliated are p-type, and then we wanted to dope with the silver nanoparticles. Now the silver nanoparticles has got dual effect here. First, it acts as a plasmon, and the second that we have seen that silver nanoparticle gives rise to some kind of doping in these WS2 layers. So intrinsically WS2 was p-type, but we did Hall measurements, etc. We got an n-type behavior for silver doped WS2. But of course, we had to do some trick. The silver is not stable with a WS2; it immediately makes silver sulfides. So you have to cap the silver nanoparticles with a very, very thin PVP-coated polymer. So by well-known phenomena of Maxwell-Ognard-Siners effect, we get a lot of electron hopping to this one, and they donated a lot of electrons in the WS2 layers. And we really measuring the IV characteristic Hall effect, we got an n-type WS2. I don't want to go into the details here. It will take some time just to show one X-ray photoelectron spectroscopy peak, that why did we do that PVP capping of silver nanoparticles. If we don't do that, within very, very soon, within a few hours, you get the formation of silver sulfide. So as you know, silver nanoparticles interact with WS2, and it makes silver sulfide. That's clear from the 3D electron spectrum of course, this one, of tungsten. And when you do the PV capping, we have seen that it's stable, I mean, for days and almost a month without formation of WS2. So that is the only reason. So I'll just present one curve of my device structures without going to any IV characteristics or any other details. In fact, the motivation of this work was to make a 2D, 3D kind of mixed dimension heterostructures, not van der Waals. So we are trying to see that whether 2D materials can be integrated with the bulk silicon, whether it can make kind of a silicon photonic devices. So that was them. So in one device, it was a PWS2, which was not doped on N-silicon. This is one. This is a kind of a control device. And the other one was plasmonic doped silver nanoparticles doped WS2. So if you see the papers are published, of course, long back, and you see that the intrinsically WS2 was not doped. The responsivity we are seeing as ampere per watt, we are showing here. We are showing both the absorption band of silicon and the excitonic kind of absorptions of WS2, and we get a little bit of broadband, but of course your responsivity is still very low, about 0.2 ampere per watt. This is expected because, as I said, this is about a few layers of WS2, so absorption is very, very small. But as soon as you put the silver nanoparticle doping, as you see, that we can easily get about 1 ampere per watt at a very low electric bias. So responsivity increases by about 5 times. So 1 ampere per watt, and we get a broadband enhanced absorption, which is shown by the blue dots here. And if you increase your voltage, etc., it's a vertical detectors, you can easily get 8 to 10 ampere per watt. So this is one demonstration we showed. Then we just wanted to show whether it happens for only these combinations of WS2 and silver. No, it happens of any other nanoparticle. This is the one thing that we have just communicated. So we can see that from the IV characteristics, of course, this is a different structure. This is a metal semiconductor metal structures with a gold nanoparticles on MOS2, and as you can see that the photoabsorption sort of photo response is about 3 orders of magnitude higher compared to a dark one, and also we get easily a responsivity more than 1 ampere per watt, and detectivity is very, very high because of the low dark current or low noise of the device. So I will just move to the other one in the strong coupling regime where you wanted to get the Rabi splitting, but as you see that the phenomena is explained here, that as you know that when you have got a coupling between the photon and plasmon, which we get the surface plasmon, we call surface plasmon polariton. Between the photon and exciton, we call them an exciton polariton. And one you have a kind of a multiple, this 3 particle kind of a coupling. We have got a plasmon, we have got incident photon, and we have got exciton. We get something quasi-particle like exciton plasmon polariton. And this is also short in the literature described as something called plexitons. So signature of these plexitons will be very clear from this dispersion curves presented here. As you see, these are for the exciton, these are for propagating surface plasmon polariton, and when the combination of these things will give rise to some kind of a anti-crossing or energy bunching phenomena, what is called the label repulsion, and that is the signature of the Rabi splitting. And this is actually the Rabi splitting energy omega r. This is the Rabi splitting energy, and that is the unique phenomena that you get when the coupling is very, very strong. Of course, in the higher order, you can get many more things, but that is not aim of our work. So I will not go much into sample preparation because of the lack of the time. So only wanted to mention here that we didn't use any electron beam lithography process. What we did is gold nanostructure that we'll be presenting here on WS2. These are all self-assembled colloidal growth. And we did in 2 different samples. I will show. One is on silicon substrate. And as you do in silicon substrate, the average size of the gold nanoparticles was of 30 nanometer. When you do on a glass substrate, the average size was about 90 nanometer. Why did you do this? This will be very, very clear from this one. This is kind of a APSM figures where it shows the WS2 flex on which we have got, gold nanoparticles of different size, approximately 30 nanometer size of gold nanoparticles or islands. I'll say them islands, not particles, and average size of 90 nanometer. And this can be also probed by the Auger mapping as well as the AFM height profile. But what is interesting is here, where did you choose the size is given here? See, normally if you take a WS2, you get a two excitonic peaks, excitonic A peak and excitonic B peak at 530 nanometer and 630 nanometer. So you wanted to have the plasmonic kind of nanoparticles of the gold or nanoislands of the gold, which strongly combines or which strongly couples with individual plasmons, individual excitons A and B. So as you see, this is the plasmonic kind of a peak for the 30 nanometer side, and this is plasmonic peak for the 90 nanometer side. So it's a reasonably well strong coupling. But of course, if one does these things by electron beam lithography, you can tune the size in a much better way. But still, we could show that this shows the Rabi splitting of the formation of the polaritrons, which I'll present now. We did some simulation to basically find out electric field calculations and detection of plasmonic hotspots before designing the structure. That was necessary, of course. And the main measurement that we did actually is called that's called pump spectroscopy. This helicity resolved pump spectroscopy, because it's very difficult to get these flexitons and polaritrons, detect this at a steady state measurements. Some people have done at a very, very high light intensity, but we could easily detect it through pump spectroscopy. So this is the kind of a schematic of the measurements that we have done. So don't go into the details. Only thing that we are pumping the sample with a 808 nanometer pump beam, and this is my sample. And the probe beam with a particular delay, and this was a broadband probe, and we could probe the interactions between the light with these plasmonic nanoparticle cyclics. And since we have used either silicon substrate or glass substrate, in the reflection mode, actually, we have tried to see that in the reflection mode, we have used the silicon sample, because for the excitons B and plasmon, which I call the B excitons right now, because A excitons are submerged due to high pump induced reflection beyond 550 nanometer. Please remember, A exciton was at 630 nanometer, so it's very difficult to probe in one measurement. So we have to do two different measurements. On the other hand, in the so-called absorption mode or the transmission mode, we use the glass as a substrate for detecting the A exciton, because the substrate absorption of gold nanoislands overlaps with A and suppresses the B excitons. So we cannot see both at the same time, but in the same sample, but two different kind of measurements. Okay, this is the standard measurements. I will not go to that. The standard spectroscopy at IIT Kharagpur that we have used. So now this is the result. So these are transient results, Rabi splitting for the hybrid samples, So if you see here, let us see the two curves given in the left-hand panel of this one. This is for the B exciton at 530 nanometer and the A exciton at 630 nanometer. This is for only two. You can see we have plotted this sample with a varying delay time over different wavelength range. And there is no splitting of so-called excitonic peaks. So this is the kind of a control samples. So, but on the other hand, you could do the same sample actually, say either 30 nanometer hybrid nanoparticles, gold nanoparticles, or 90 nanometer gold nanoparticles. You can see the excitonic peaks now splitted into two completely different peaks. This is nothing but the actually Rabi splitted energy peaks or energy levels. So in one case, I am showing since I am using two different or deflection mode, I am either seeing a peak or valley. So we plot it a little bit differently, that we try to see that what is the exciton formation time actually. So what is does it happen in what time scale? So as a function of probe delay, if we try to find out, we see it does not happen instantaneously. It happens after 5 picoseconds, or exactly, to be very frank, it happens around at 7 picoseconds. This is for the plexiton A and for the plexiton B. For both of them, this Rabi splitting, as you can see, two energy branching takes place at the delay time of about 7 picoseconds. So this can be either calculated from this contour map, or you can just calculate it from the lifetime measurements, or you plot the delta OD, the change of optical density as a function of time. So stable plexiton formation time is measured to be 7 picoseconds for both A and B plexitons. And of course, it is also known that Rabi splitting or the Rabi, this phenomena is not stable at a very, very high pump fluence. So we have seen that also, that this is only stable on the low pump fluence, just to see that there are no artifacts. So this actually completely vanishes when you go above 75 microjoule per centimeter square of fluence, about 100 microjoule per centimeter square, and you see that Rabi splitting is completely destroyed. So this also proves the premise that now the mechanism of this phenomena actually can be two different mechanisms. Either it can be completely coherent interactions between the plasmon and excitons, or actually it can be a kind of a non-radiative interactions between the plasmon and excitons. As you see here, this is a kind of a model that has been published here, so we are trying to follow here. So this coherent time scale actually is in the range of femtosecond scale, about few femtoseconds, and that is beyond our detection limit in our pump spectroscopy. On the other hand, the excitation formation time is about 7 picoseconds. So we think that the incoherent exchange of photons emitted from one emitter and basically subsequent reabsorption by another basically gives rise to interactions between these plasmon and excitons. So the phenomena is nothing but a non-radiative channel occurs at picosecond time scale with a vacuum field and phonons. So that is the. So this is the typical energy branching plot of the Rabi splitting that we normally do. As you see, we have plotted for both A exciton and B excitons. So this is the upper energy branch and this is the lower energy branch. And this is the kind of a. Rajinder, how much time do I have?
So you can speak for another 10 minutes.
Okay. So I was going too fast. I didn't see my watch, so I was going a little bit too fast.
It's okay. Yeah.
Thank you so much. Right. So I'll take some time. Okay. So then, as you see, is very, very clearly that, of course, the energy branching was there, as I have shown in the contour plot. If we plot it energy versus the wavelength, and this is the kind of a plasmonic energy, and if you see it crosses the zero, so this is called the zero detuning. So this zero detuning can be basically the energy gap between the upper energy branch and the lower energy bands at this delta equal to zero gives rise to actually Rabi splitting energy. So we plot this behavior ultimately feed by a kind of a quantum two-state model, which probably I'll just briefly describe in my next slide. And from there, we found out what is the kind of a Rabi splitting energy. So the model is something like this. We consider these actually excitons and plasmons, and both of them have dipoles. So both of them have some kind of dipole moment, and they are coupled together by a massless spring. So that is a model normally very, very popular in the literature. And as you see that schematically, as you see that either A or B plasmon or B excitons, when they interact with the plasmon, when the interactions is very, very strong, actually they give rise to the upper energy branches and the lower energy branches due to the Rabi splitting, which are experimentally shown till now. So if you try to model these two particular model, and if you write the eigenvalue matrix, so the coupling strength is determined by actually the coupling rate is determined by this factor G. So Rabi splitting is basically given by the 2G, and the G is the coupling rate, and delta when the delta equal to zero, one is the zero detuning energy. So this is delta is the exciton plasmon detuning. So if these equations are solved, actually the equations that is energy branching equation for Rabi splitting on this particular quantum two-state model has been reported in the literature is gives like this. So we have used this model to fit our experimental data, and so as I said, the G is the coupling rate. And since we can easily find out EP and EX from our measurements, and we can get the delta, the zero detuning energy, from there actually we try to find out the G coupling rate, and from there we find out the Rabi splitting energy. So Rabi splitting energy after the fitting of the experimental data in two different cases, for X exciton becomes about 270 MeV, in the other case is around 250 MeV. So this is very interesting because this shows that really stable at room temperature. So you are getting some polaritons which are stable at room temperature. So ideally you can make some devices, and if you make this kind of devices, these are definitely very, very interesting application for the quantum photonics. So now I'm going to the other one, the intermediate coupling between the exciton and plasmon. I've shown the weak coupling, I've shown the strong coupling when the Rabi splitting takes place. So this weak intermediate coupling, as I said, that there is a possibility of the Fano resonance or the asymmetric Fano line steps. So can you these asymmetric fine line and nanoshapes from our measurements of the pump of spectroscopy? The answer is yes. But what is more interesting actually that till now, experimentally, that of course, Fano's theory says that if you have a coupling between two discrete energy levels and one continuum, ideally you should get a double Fano resonance kind of a phenomena. But at least in any solid state system, till now, we have not seen any double state kind of a Fano resonance. So since you know that we have got both A and B excitons in any 2D materials, and we can have a broadband plasmon continuum from the plasmonic nanoparticles, whether it is possible to see both double Fano resonance in this system. The answer is yes. So this has been reported very recently. So as you see that, okay, don't need to go to the theory because with the original prediction of Fano, you get a asymmetric line shape, the S line shape, and this is of course single Fano resonance between a single discrete state and one continuum state in an intermediate coupling. And of course, the theory says there can be a multiple Fano resonance also. And very recently, people have started measuring this thing. And you see, but most of the measurements till now, actually, of course, ultrafast spectroscopy, people have started measurement. One measurement is using attosecond dynamics, so it is extremely fast. So we don't have that kind of facility, of course. And as you see, two very, very recent science papers, but none of them actually measure the double Fano resonance. So the double Fano resonance is feasible in our system. Again, I say these nanoparticles are just self-assembled. We don't have much control. We just try to optimize their size. So as you see in this case, my choice of the system has suddenly changed. Till now I was talking about WS2 due to the Rabi splitting, but now I am coming to MOS2. The reason will be very, very clear. So this is the broadband gold plasmonic band for a kind of a self-assembled gold nanostructures. And I try to fit or actually MOS2 absorption peaks, excitonic A and B peaks within this gold plasmonic band, a broad plasmonic band. Then only I have got some kind of intermediate coupling, not very strongly coupled, but they are coupled. And they're coupled to both A and B excitons. So this is the schematic of the sample preparations. We don't need to go into details, but we again did a pumper spectroscopy of these hybrid samples. And basically the energy exchange between either the A exciton and B excitons with a kind of a plasmons. So these are the discrete excitons. And this is kind of you can think of a continuum surface plasmon. So you see clear signature here. So let's see this curve. This is the green one is the plasmonic band of gold nanostructure that we have prepared. MOS2 is given by the kind of a maroon one or the magenta one. As you see, this is the MOS2. We have got excitonic A peak and excitonic B peak, and which more or less couples with the plasmonic band. And as you clearly see, for a 5 picosecond spectra, I'm just showing one spectra here, you see that change of the line shape of the excitonic peaks. Now suddenly it has become asymmetric, and asymmetric Fano line shapes of the S shape that is predicted by the Fano. So we get both resonance due to the so-called the B excitons and the Fano resonance to the excitons, A excitons. So double Fano resonance that we have detected, and this is a little bit more details, of course, that we could do the real-time mapping of this double Fano resonance A and B, and it does not happen, as I said, instantaneously. Typically up to 1 picosecond, we normally get simply exciton and B exciton separately. Above 1 picosecond, that means as you see this, we get these Fano line shapes, and this is very, very stable up to 5 nanosecond. That is the instrument delay limits that we have. So ultimately, that we have also seen this time delay measurements as well as the pump fluence measurements also we have seen, and this happens only after a critical pump fluence. So this shows that actually this double Fano profile confirms this is basically a non-linear modulations actually in time domain. So this is of course a non-linear effect. So that's why you cannot get it in a steady state absorption measurement. It's impossible to get. Otherwise, you have to get a very, very high optical field. So as you see that, but it's stable. As you increase the intensity of your beam, that pump fluence, 1 gigawatt centimeters to 4 gigawatt centimeters square, actually you see the Fano resonance becomes stronger and stronger. And typically, you measure this phaneroresonance strength of the phanerogens by the phanoparameter. What is basically two things. One is the what is the phanoparameter, what is the width, and what is the asymmetric line. Say the QVX and gamma EX. I didn't want to go to the detail. Just written here as a function of the probe delay and the function of the power. So this shows a very, very nice quantum interference effects that can happen in these 2D materials, and that can be very interesting for future quantum photonic devices. So to conclude, of course, I have not shown that ideally. I just wanted to tell you that Pumper spectroscopy is a very, very powerful tool for detecting these time resolved phenomena, which takes at a picosecond or femtosecond time scale, and interactions between the plasmons and excitons in 2D materials. So it started from a simple parcel effect. It is very, very well known. This, of course, I have not shown. Second phenomenon, I have not shown that we could detect the bi-excitons also, but I have not discussed this one. You can get individual bright excitons or polaritons by this phenomena when there is a strong splitting due to the Rabi splitting, or you can get a very, very rare double phaneroresonance in real time in a two-dimensional materials when they are coupled with the plasmons. Okay, so this is the research group at IIT Kharagpur. Most of them are there. One or two of them have graduated. Rishi has already graduated. I've talked on the PhD thesis of Rishi. So he'll be going for a postdoc soon, waiting for the Viva, thesis Viva. And of course, Subhojit also has contributed a lot of work in the MOS nanoparticles, and he's already postdoc in kind of Israel. So basically from these two. And so thank you very much. And of course, there is this thing that 2D quantum photonics using metal TMB hybrids are actually one of the futures in this low dimensional materials. Thank you very much.
Okay, so thank you, Professor Samitre, for this very, I will say, plexiting talk. Not exciting, but plexiting talk. You talked about plexitons, and really very interesting that you have brought in a new dimension to these metal TMD hybrids, and using this light metal coupling phenomena so that it can find application in future quantum photonics. I have actually, maybe I can start with my question, and then I will wait for some questions from the chat box if they are there. So you showed initially, I think in MOS2 photodetector, using this metal nanoparticle dispersed over that. I think there is a gold nanoparticle.
Right.
And you could observe the enhancement in the photoresponsivity. So
Right.
these gold one question is, gold nanoparticles were monodispersed or they were self-assembled, like formed by evaporation and dewetting phenomena?
Yes, they were actually self-assembled. So that is one of the things that is really not monodispersed, because we still don't have our electron beam lithography purely, I mean, settled right. We have one. So this is a self-assembled gold nanoparticle.
Okay, so I have just related questions. What do you think that if we have this monodispersed nanoparticles of various particles of various metals, if we have that kind of control, then will it be more useful for tuning the photoresponsivity of the photodetectors?
Yeah, absolutely. That is what is necessary. As you will see that monodispersed gold nanoparticles done by the electron beam lithography process. And you see, even my MOS2 that we have grown, that was a kind of a CVD process. This was not really monolayer. So this was kind of 6 layers, about 3 to 4 layers. So if we can do really a combination of these two, monolayer MOS2 and a monodispersed gold nanoparticles, we expect a much more enhancement. I mean, the photodetector property should be much, much better. Definitely.
Okay. Thank you. Thanks for. So there is a actually question from Professor Karthik Shankar. Very interesting and insightful talk. Have you considered time-resolved PL measurements of the MOS2 and WS2 and plasmonic hybrids to determine the spontaneous emission rate in the different coupling regimes?
Yes, the answer is still now not no, because unfortunately, still this Pumper spectroscopy we have set up in our department at physics at IIT Kharagpur. This is still kind of a common facility. So that's why that is one of the reasons actually I could not do the plasmonic, kind of photoluminescence measurement of these plasmonic nanoparticles, particularly for this one. But simple partial enhancement of the photoluminescence? The answer is yes. Of course, that result I have not put it here. But in details, the answer is no, definitely. Particularly in the for the polariton and the Fano, we have not done. But that will be very interesting indeed.
Okay. Okay. So I think with that we can now wind up with this like your presentation, because now we are running a little bit short of time. So thank you, Professor Samit Ray, again for this very, very motivating talk. So thanks. So
Thank you, Rajendra.
yeah.
Oh,
So
bye.
now, yeah, bye. Thanks. So we have the last last presentation. This is an oral presentation by Mr. Sankalp Ganeshan. He is from BITS Pilani, Hyderabad. And the title of his presentation is Doping Induced Band Tunable Mixed Dimensional P Nickel Sulfide and NMOS2 SCE2 van der Waals heterostructures. So you are here?
Yeah.
Okay.
Yeah, I'm here. Thank you for the introduction. Yeah.
Okay. So you have about 12-13 minutes for your presentation.
Okay.
Please go ahead.
Yeah, I'll just share the screen.
I have to stop sharing. Yes.
Yeah.
Yeah, it's now there.
It's visible, right? Yeah.
Visible.
Yeah, thank you for the introduction. One second. Yeah. So thank you for the introduction, and I'm here to present a research work on doping-induced band-tunable mixed-dimensional PNIS and N-type MOSSE. This is JNS molybdenum sulfur selenide mixed-dimensional van der Waals heterostructure for enhanced photodetector. In brief, this work is about the strategy used for enhancing the photodetection using chemical doping and heterostructure formation. So we are from Flexible and Wearable Nanoelectronic Devices Group from Department of EEE, BITS Pilani, Hyderabad. So in brief, let's see the outline of the talk. I would be going to the introduction, the brief motivation, the synthesis and fabrication of the device part, the characterization, the photodetection experiments, and in brief, the conclusion and acknowledgements. To start with, if you see, materials have helped in the development of human civilization, right? From the Stone Age, you can see, then we come into the Bronze Age, where you see metals coming into picture, where copper, nickel, iron, all these metals come into picture, and then slowly we are emerging towards the area where polymers came into picture with many plastic, ceramics, and glass, with the introduction of glass, and then the huge revolution of silicon industry, and completely it has revolutionized everything here. So slowly we are going from bulk to the nano and nano to the quantum. So right now we are in the nano age, and we are trying to exploring various materials, and they play a crucial role in the progress of mankind in the evolution of new technologies. So if you see layered materials, the speculation on the properties of layered materials was first initiated, by asking questions such as, by Richard Feynman, a famous physicist, where he says, like, what could we do with these layered structured materials? If you see, we can just manipulate the things at plenty of room at the bottom. So this is what they said, like, showed that there is opportunities to explore this material. So this was somewhere around in 1950, in the year almost like in the year 2010, with the Nobel Prize awarded for graphene discovery. Huge research has been put into to explore various 2D materials. So let it be transition metal dichalcogenides, graphene, black phosphorus, mexene, and many 2D dimensional materials came into picture because of their exceptional properties such as high mechanical strength, low bending rigidity, high surface to volume ratio, tunable band gap. So then they became a very good source for wide applications. Let it be sensors, photodetectors, LEDs, optoelectronics, transistors. Another important thing is they were able to integrate these 2D materials into flexible electronics, which is the modern era of electronics, where because of the solution process techniques and various fabrication methods, these can be easily integrated into flexible electronic systems. So you can see in picture like the various applications, wearable sensors, flexible displays. So coming to the flexible photodetectors, because flexible photodetectors have very huge applications, in flexible displays, electronic tattoos, wearable sensors. So coming to that, conventional photodetectors, if you see like silicon, they are based on rigid substrates such as silicon or silicon carbide, which makes them very difficult to be applicable in flexible electronic systems. And also the absorption band is very limited to such detectors. So photodetectors in general also have very good applications in imaging, chemical analysis, sensing, and bioimaging, telecommunication, like visible light communication. So all of these. So there's a need to come up with photodetectors which are flexible and also have very good broadband detection. So if you see the basically 2D transition metal dichalcogenides, they have been an interesting materials in the class of 2D materials because of their exceptional properties such as layer dependent optoelectronic properties, strong absorption with tunable band gap. Strong electron hole confinement, and they are very flexible and bendable due to their exceptional mechanical properties, because of which they can be integrated into flexible electronic systems. And also they are like the building blocks of like the small kids play with the Lego blocks, they construct the buildings. So with them we can easily build heterostructures and also form sharp p-n heterojunctions, which are very good. They have potential applications for development of enhanced photodetectors. Right. Then what are the challenges actually, and what is the motivation? If you see the pure transition metal dichalcogenides, they have weak absorption, and the absorption is only confined to a particular region of the electromagnetic spectra. Generally, most of them are have strong absorption in the NIR, infrared region or the visible region. So hence there is a need to enhance the broadband detection. Also, the transition metal dichalcogenides, the fabrication process involves CVD, which is a high temperature processed, high cost, and the fabrication is quite complex. So in case to develop flexible electronic systems, CVD is not that useful, as the transfer process is also very difficult. So there is a need to come up with some other alternatives to overcome these challenges. So if you see what are the strategies that can be used, is to come up with a solution process technique which is low cost, low temperature process, and which can be easily compatible with the flexible substrates. And as mentioned, what are the strategies to improve the performance of these photodetectors? One is the chemical doping, other is the defect engineering, and another interesting is the formation of heterostructure, which these class of materials have. Like you can see the Lego structures here, like you can just build one above the other different heterostructures and get different variety of properties and utilize them. So there are different types of heterostructure, maybe two-dimensional, zero-dimensional, as mentioned in the before talk, like using of quantum dots, then two-dimensional, one-dimensional materials, two-dimensional, two-dimensional materials. So if you see like using a combination of materials with different absorption also enhances the broadband spectra. So here in this talk, we are using the concept of chemical doping and the heterostructure formation of two-dimensional and one-dimensional material for enhanced photodetection application on flexible substrate. So if you come here, like MOS is widely studied, but in the year recently, 2017, the chemical doping of MOS2 with selenium created this genus MOSSE, which is called, and it has very exciting properties because of the loss of symmetry which we observed. You can see here the picture, one half is sulfur and the other half is selenium. So the thing is, because of this, you can tune the band gap of the material. Doping of selenium actually reduces the band gap of the material, and also the interlayer spacing of the material is increased. Thereby, you can effectively create heterostructures. So the improved electronic conductivity, band tunability, expanded interlayer spacing, these all can lead to exciting applications. So in this work, what we are doing is we synthesized the MOSSE by facile synthesis, and this has not been reported yet. Most of it is done through CVD and other processes. And we have synthesized NIS nanoparticles as the one-dimensional material and the two-dimensional material through hydrothermal synthesis, and used a facile spin coating method to fabricate the device by forming the heterostructure on a flexible ITO-coated PET substrate. So coming to the characterization, MOSSE nanoparticles, like the synthesized has very good, a netted nanoflower morphology, as you can see here in the FESCM images, and the confirmation of the incorporation of both sulfur and selenium was done by doing the IDAC spectra. And also we confirmed the presence of sulfur and selenium using the Raman spectra, where you can see the characteristic peaks. And also from the Raman spectra, we could analyze the formation of a 4-layer MOSSE from the distance between the wave number of A1G and E2G. And you can also see the XRD spectra, where you can see the characteristic peaks, and part of the synthesized material is oxidized, partially oxidized. So you can see the oxygen peak and MO3 formation in the XRD as well. Then coming to the elemental characterization, you can see the XPS analysis, where MO in +4 state, sulfur and selenium, all these elemental compositions were confirmed. And then going into the NIS synthesis, if you can see the interesting morphology of NIS, you can see it's similar to that of a pine tree. And in nature, actually, trees are actually have a particular orientation where they can absorb light very much. So this morphology, if you can see from nature, has very good absorption to light. Like this morphology is very suitable. So this is one thing which quite was fascinating. So we thought of why can't we make a heterostructure of this? And you can see it is a one-dimensional material which stacked nanoparticles like nanorods together, which form this pine tree-like structure. And then you see the XRD of the NIS with the characteristic peaks, and this is the XPS characterization where nickel in +2 state and sulfur is confirmed, and this is the Raman spectra confirming the formation of NIS. So then coming to that, we then started with the photo detection experiments we wanted to try. So then here you can see on illuminating visible light, you can see a sharp increase in the current, a photocurrent observed, and when the light was switched off, and you can see the dip in the current. So this device which was fabricated was tried for both visible light and NIR illumination. If you see, MOSSC has a strong absorption in NIR region and NIS has strong absorption in visible light region. Hence, we can get this broadband photo detection. And then we increase the intensity of the light, and you can see as the intensity is increased, the photocurrent also increased gradually. So this is the temporal response with different intensities. Then if you see the figure of merits, the figure of merits are very important for a photodetector. That is the responsivity, which is the photocurrent generated per unit power instant on the light. So this was calculated to be 21.5 milliampere per watt and 28.1 milliampere per watt in the NIR and visible region. And you can see that photodetector is more responsive to the visible region than the NIR. This can be attributed to the strong absorption and the morphology of NIS nanoparticles and the electron quantum efficiency, right? It was calculated to be 3.41% and 6.21%, and the response time, if you see, it's the time between the sensor to reach to 10%, from 10% to 90%, and was calculated to be 2.1 and 2.3 seconds. And this is relatively higher because of the usage of hydrothermal synthesis. You get some defects due to which you can see an increase in the response time. But overall, if you see, the responsivity was very good because in the enhanced photo detection. And also, like, the response rate is directly proportional to the EQE ratio. Then coming to understand the working mechanism, you can see the band diagram where you can understand properly where NIS is an N-type material and MOSSC is NIS is an P-type material and MOSSC is an N-type material. And you can also tune the band gap of MOSSC by by using the doping content. Here we have used it at the 1:1%. So when you shine visible light, NIS is more responsive to that. Electrons and holes are generated. So when electrons and holes are generated, and you can see in the band diagram, these electrons can, because of the lowering of band gap, they jump in and the photo electrons are collected and you get a response. In the other case, when NIR light is illuminated, MOSSC is more responsive. Therefore, you get the electrons and holes which are generated. And then holes, they can jump in, and these holes are collected at the contacts, electrical contacts, which are made using silver paste to copper contact. So on the whole, NIS has added the visible light detection, and MOSSC has added to the NIR detection. Along with that, you can see the formation of a PN junction diode, due to which localized electron carriers are generated, which help in the charge carrier separation. So this is in brief about the band diagram, and in conclusion, a low-cost mixed-dimensional PN and NIS MOSSC heterostructure was formed. So we have used the technique of chemical doping for tuning the band gap of MOSSC, and also the formation of PN mixed-dimensional heterostructure of two-dimensional and one-dimensional material. And we have showed it, it is compatible, we have fabricated it on a flexible IT on PET substrate, showing it to be a potential application for flexible photodetectors. And we also showed the facile hydrothermal MOSSC. And the device showed good responsivity of 21.5 and milliampere per watt and 28.1 in the NIR and visible region. So if you see the unique properties of MOSSC, that is the enhanced electronic conductivity, high interplayer spacing, modified surface and interface with defects, which helped in the effective formation of heterostructure, and also the broadband detection, which by addition of NIS nanoparticles and the effective construction of PN heterostructure, all together contributed to the enhanced performance of the photodetector. And this work opens new paths for the development of low-cost, superior, flexible photodetectors, as they have potential applications in wearable devices, optoelectronics, and security systems. And acknowledgement, I would like to thank my supervisor, Dr. Parikshit Sahatia, Assistant Professor at Department of Triple, and also the PhD scholar along with whom we worked on this project, Mr. Venkatrao. And I would like to thank the funding sources, BITS Pilani, Red Pine Signals, and SERP India for helping us supporting through the funding. And we are from Flexible and Wearable Nanoelectronic Devices Group. We generally work on novel 2D materials, wearable devices for photo detection, memristors, and pressure and strain sensors. You can just have a look at the website for any other interesting work which we do. And yeah, I would like to thank the organizers. Thank you for your attention, and any questions you can ask. I hope I utilize the time. Yeah, that's right.
Yeah. Okay. Thanks, Sankalpa, for being in
Yeah.
time and for the nice presentation. I just have one question to you. You
Yeah.
see that these 2D material-based photo detectors, so
Yeah.
there are a number of maybe hundreds of reports are there in the literature, and
Yeah.
even from India also there are a number of groups who are working on this area, and the photo responsivity of these 2D material-based photo detectors, what has been obtained is much higher, like even close to 1 ampere per watt or something like that. In your case, what you observed is quite less value. So can you try to
So the-
guess why it is so less in your
So the
case
thing
and
is,
how it can be
in
improved?
our so actually, if you see, most of these devices are based on silicon substrate, and proper growth through CVD method is done. So if you see there, the photo responsivity is quite high. But in our case, we are using hydrothermal synthesis, so the proper growth is one issue. Even though it's a growth, there are defect issues which come through hydrothermal thing. So because of the defect issues, if you see, the sensor takes relatively more time to respond. And also we are doing this on a large area growth of ITO coated PET. So we have to compromise when we need to bring in the flexibility into integrating flexibility into photo detectors. So in that case, that is the main reason of using the hydrothermal synthesis and the large area growth, because of which the responsiveness is quite low.
Okay, so I think it needs to be looked into, and you can work on of this one. So there is one question from Professor, I think, Shankar. It's a nice talk. The similar responsivity for visible. What were the bandwidths of the visible and NIR sources you used to illuminate the heterostructures to measure their responsivity?
Yeah, the NIR source.
Sources or narrowband sources. Also, how did you determine the band alignment at the heterojunction?
So
Could
okay,
you hear my question?
Yeah, I can hear it. So yeah,
okay.
The band alignment
so it's a
in
question
the
about the
heterojunction. Yeah,
bandwidth
so
of
the
the sources.
bandwidth
First
is
thing is bandwidth of this.
Yeah, so the bandwidth was actually we used a particular wavelength of light. That is, one is for visible was around 534, and other one for NIR was around 700 or so, 730 or something. And also there was another source with a wide band gap, NIR source. So actually it was a particular wavelength, like it is not a wide bandwidth. It's only a particular bandwidth which we used, and the device was more responsible towards visible light, that is around 500 or so, and near NIR region. And then other question was measure
how
the
did you
response.
determine the band alignment at the heterojunction? You
So
see, there is
basically,
some. I also feel there is you have to work out at the interface how to make the band alignment actually between the heterojunctions, because it is not. I think it's not correct what you have drawn. So this is the, I think, similar kind of question, but Professor Karthik Shankar is also raising.
So initially the confirmation.
So how did you determine it?
Yeah, so initially the band alignment first through FESM images, the formation of heterostructures, we did it. And then through the IV characteristics, we just saw the PN characteristics. Actually, I didn't show that because it was not published yet. So we got the IV characteristics of a diode. And then if you see the band alignment, we actually, this is for just an understanding.
I think,
yeah. Yeah, in this band diagram, it's not the
so I
exact
think maybe
value. It's not the exact value, it's just for an
no, you need to
understanding
work
through
on it,
literature.
actually.
Yeah. It is through literature which I have mentioned the band gap values. For an understanding, I have showed this band diagram. So it's not the exact value
what
from
kind
the
of
experiment.
alignment is it? You are showing type 1 or type 2?
Yeah, type 2.
Between these two semiconductors.
Yeah, metal semiconductor.
But,
1 minute.
no. It's okay. Anyhow, you look into the basics again and try to make a correct energy band diagram at the interface. Okay. So all the best to you. Yeah.
Thank you.
Now you can let us say switch off your the presentation. So with this, we come to the end of this session, and very interesting session, I think. And we had 3 invited talks on oral presentation, and I think a lot of interesting discussions also happened. Hopefully, the participants also found it to be very interesting. So now I hand it over the session to Professor Samresh Das, if he is here. Professor Samresh Das.
Hello, can you hear me?
Yeah. Okay.
Yeah.
So
we have a very good session for all the renowned 3 invited speakers, so different topics, and I'm thankful to all the invited speaker and also session chair, Professor Rajendra Singh, for timely finish this session. So we'll meet in the next session is for 2D materials from 2 o'clock. So we have 2 invited speaker and 2 contributed oral presentation. And we'll see there, and also poster presentation will take place in the hall 8 from 3:30 to 5 o'clock. Thank you all. Thank you all.
Okay, thank you. Bye.
Bye. Professor Ankur, are you there?
for inviting me to give a presentation in this conference.
इसको full slide करिए, full slide कीजिए इसको.
Giving this live over Zoom, but it's in the middle of the night my time, and I'm just afraid that I would be somewhat in.
इधर है. हेलो.
Good afternoon. First of all, I'd like to thank the organizers for inviting me to give a presentation in this conference. I apologize for not. The field of 2D
एक मिनट वेट कीजिए, एक स्लाइड पूरा होने दीजिए.
images obtained.
स्लाइड ऑटोमेटिक चेंज होगा, कुछ करना नहीं है. फर्स्ट स्लाइड में आ जाइए, फर्स्ट स्लाइड को ओपन करके छोड़ दीजिए. अभी ठीक दिख रहा है कंटेंट, इशू नहीं है ज्यादा. बस आप एक स्लाइड पूरी कंप्लीट प्ले होने दीजिए बस. अभी रुक गया, प्ले नहीं हो रहा है. आप फर्स्ट स्लाइड से जाइए, आप फिर से प्ले कीजिए.
The field of 2D materials really took off in the early 2000s with the isolation and characterization of graphene. And then soon after, there was interest in exploring the properties of other materials that also have a layered crystal structure. So for example, in a material like moly disulfide, the molybdenum atoms are covalently bound to the sulfur atoms within a layer, and then the layers stack and are held together by weaker van der Waals forces. So it's possible to exfoliate a monolayer film or a few layer film that has a passivated surface, which is great for an electronic or optoelectronic device. In addition, this class of materials offers a very wide range of electronic properties. So this includes materials like hexagonal boron nitride, which is an ultra wide bandgap semiconductor, transition metal dichalcogenides like moly disulfide, which have moderate band gaps, elemental semiconductors like black phosphorus, which has a narrower band gap, and then materials like graphene and niobium diselenide, which are semimetals. So our work has focused on the transition metal dichalcogenides, which includes materials like moly disulfide, tungsten disulfide, and moly diselenide. The interesting properties and applications of TMDs all occur in layer films. So how do we get a?
अभी आप ये बताइए कि आपने ये कैसे किया?
सर हमने वैसे किया सर, जैसे यहाँ से शेयर किया और
हाँ जी,
ऑप्टिमाइज मोशन वीडियो ऑन करके बस शेयर कर दिया.
तो मैं शेयर कर रहा हूँ यहाँ से, आप देखिए, अदरवाइज फिर 2 बजे आपको शेयर करना पड़ेगा.
ओके सर.
तो आप देख के मुझे बता दीजिए कि आपको स्लाइड में ठीक दिख रहा है या नहीं. मैं शेयर करता हूँ कंटेंट. ओके
ओके सर. ओके.
आपने कौन सा वाला फाइल शेयर किया था, पीपीटी वाला या वो एक और जो है दूसरा?
पीपीटी वाला सर.
ओके. देखिए दिख रहा है आपको?
हाँ सर।
Good afternoon. First of all, I'd like to thank the
साउंड आ रहा है आपको?
organizers for
आ रहा है सर, आ रहा
inviting me to give a
ऐसा
presentation
पिक्चर
in this
क्वालिटी कैसी है?
conference.
मतलब टेक्स्ट दिख
I
रहा है आपको क्लियर?
apologize
हाँ
for
हाँ
not giving this
ओके,
live over
मैं नेक्स्ट स्लाइड
Zoom.
जाता हूँ।
ठीक है।
यहाँ पे दिख रहा है आपको टेक्स्ट
हाँ
वगैरह
सर
सारा?
बिल्कुल क्लियर है सर, क्लियर है।
ओके, थैंक यू।
ओके।
सर मैं ये बोल रहा हूँ कि मैंने चेक कर लिया, ठीक दिख रहा है। हो सकता है कि हम उधर बैठे थे ना, क्या बोलते हैं 201 में, इंटरनेट मतलब वो ठीक से फाइल लोड नहीं हो रही थी। अभी बस वो जो सेकंड वाला ऑप्शन आपने बताया था ना, ऑप्टिमाइजिंग मोशन एंड वीडियोस, बस वो सिलेक्ट करके स्लाइड शेयर करना चल जाएगा। हाँ यहीं बैठ।
Hello, Sumi. Can you hear me? Hello. Hello, Shlomi.
Yes, sir.
Can you hear me?
Yes, sir.
Can you share the session?
Okay, sir.
अभी तो शेयर कर दो।
Slide I can share.
हाँ उसमें
Okay, sir.
जो वाले हैं उसको शेयर कर दो।
Okay, sir.
अरे हेलो
Yes, sir.
इस सेशन से जो तीनों चार टॉक है उसको शेयर करो। समझ में क्या करना है? हेलो
হ্যাঁ, সমরে শোনা যাচ্ছে?
হ্যাঁ it is okay আমার একটু অন্য কম্পিউটার আছে
Okay. Sound okay. Is audible?
yes it is fine.
Fine. Okay. Okay, thank you.
Hello, Sumit, can you hear me now? Clear?
Yes, sir. Hello, yes, sir.
Hello, Sumit, can you hear me clearly?
Yes, sir. Now it's clear.
Okay. Hello. Hello, Professor Kostabdas. Can you hear me?
Yes. Okay.
So maybe we start little bit, maybe 4 or 5 minutes. Just wait.
Okay.
Because our lunch session just going to end. So just wait for 4 or 5 minutes, then we'll start.
Okay, no problem. Sure.
Okay, then maybe I can introduce the session chair first. So now this is for 2D materials and devices, second day, second session. So we have two distinguished talk in this session, and then two contributory talks. So the first speaker, because of the time difference, she is not able to present live, so we'll play the pre-recorded talk. So for sharing this session, I'm requesting Professor Kaustubh Das from Jadavpur University. So he's the associate professor at Jadavpur University. He did his master, MTech and PhD from IIT Kharagpur. Then he worked as a senior scientist at SN Bose, Kolkata. Now he is a professor at Jadavpur University. He works on germanium wire photodetector and also quantum dot optoelectronics devices. So now I'm handing over to Professor Kaustubh Das. So Professor Das, now it is you.
Okay, thank you, Shamuresh, and thank you the organizing committee for giving me the opportunity to chair this session. So as you know, this session will have two invited lectures and two contributory lectures. So the first speaker is Joan M. Redwing, and she will be giving lecture on epitaxy in 2D, the path to wafer scale single crystal monolayers and heterostructures. Now, Joan Redwing is the professor in the Department of Material Science and Engineering at the Pennsylvania State University at USA, and at the same time she is serving as the director of the 2D Crystal Consortium, as well as she is the vice president of the American Association for the Crystal Growth, and obviously the co-chair of the 17th International Summer School on Crystal Growth, which held last July. Apart from that, she is the fellow of the American Physical Society, Material Research Society, and also a senior member of IEEE, and obviously an co-author of over 300 publications in the referred journals, and has 8 or more US patents. So I hand over this to the organizing committee, because they will now run the recording of the video of her talk. So please, you can start the talk.
Good afternoon. First of all, I'd like to thank the organizers for inviting me to give a presentation in this conference. I apologize for not giving this live over Zoom, but it's in the middle of the night, my time, and I'm just afraid that I would be somewhat incoherent if I tried to do that. So I've pre-recorded this, but I'd be really happy to answer any questions that you may have when I join the conference later. So what I'm going to tell you about today is some work that we have been doing recently in the area of epitaxial growth of two-dimensional materials. The field of 2D materials really took off in the early 2000s with the isolation and characterization of graphene. And then soon after, there was interest in exploring the properties of other materials that also have a layered crystal structure. So for example, in a material like molybdenum, the molybdenum atoms are covalently bound to the sulfur atoms within a layer, and then the layers stack and are held together by weaker van der Waals forces. So it's possible to exfoliate a monolayer film or a few layer film that has a passivated surface, which is great for an electronic or optoelectronic device. In addition, this class of materials offers a very wide range of electronic properties. So this includes materials like hexagonal boron nitride, which is an ultra-wide bandgap semiconductor, transition metal dichalcogenides like molybdenum, which have moderate band gaps, elemental semiconductors like black phosphorus, which has a narrower band gap, and then materials like graphene and niobium diselenide, which are semimetals. So our work has focused on the transition metal dichalcogenides, which includes materials like molybdenum, tungsten diselenide, tungsten disulfide, and molybdenum. The interesting properties and applications for TMDs all occur in monolayer films. So how do we get a monolayer? Well, the most common approach is to use Scotch tape or another technique to do successive exfoliation of layers from a bulk crystal and then do characterization to determine an area that's single layer. So this simple technique has made the field accessible to a wide variety of researchers. However, it isn't scalable to large areas. And this is because the main bulk growth technique for TMDs is chemical vapor transport, which is carried out in a sealed quartz ampule under a temperature gradient using a transport agent like bromine or iodine to volatilize the source material. It's difficult to get large single crystals using CVT. About the largest bulk crystals that I've seen are these samples that I got from Bruce Parkinson at the University of Wyoming. The tungsten diselenide in this case was grown by CVT, and it's about 1 inch in size. The molybdenum that I'm showing here is a naturally occurring mineral. So it is possible to get larger crystals from Mother Nature, but nevertheless, these are still too small to be practical for device technologies. This motivates the interest in developing vapor phase epitaxial growth methods to deposit large area single crystal monolayer films. Since these are van der Waals bonded solids, this isn't epitaxy in the conventional sense, where chemical bonding occurs at the film substrate interface. This is instead referred to as van der Waals epitaxy, a technique that was first described in 1985 by Koma and Miyajima, who carried out very elegant studies of MBE growth of a number of layered chalcogenides on other van der Waals surfaces. For example, this is an AFM of gallium selenide grown on molybdenum, showing the characteristic triangular shape of domains. And they also observed moire patterns from STM of lattice mismatched heterostructures, such as the molybdenum on molybdenum shown here. Given the limited size of bulk TMD crystals, however, we don't want to use those as substrates. Instead, we want to be able to use large diameter, commercially available substrates. And this is possible to do if the surface can be passivated to form a quasi-van der Waals interface. Since TMDs have a hexagonal crystal structure, we consider substrates like sapphire or silicon carbide or the group 3 nitrides. But due to availability, we primarily use sapphire as a substrate. While the lattice mismatch is large, there's commensurability between the lattices, which significantly reduces the effective mismatch. Twinning is another commonly observed problem in epitaxially grown layered chalcogenide films. And this occurs because the energy difference between domains that are oriented 0 degrees or 60 degrees on the substrate is very small. They're energetically equivalent. And the problem is when oppositely oriented domains coalesce, they form a twin boundary, otherwise known as an inversion domain boundary. And the twin boundary has metallic character. So this introduces conducting paths in the semiconducting layer, and it also makes it difficult to observe valley polarization. So instead, we would like the domains to be oriented in the same direction so that when they coalesce, they do so without the formation of a grain boundary. When considering a vapor phase deposition method, we need to take into account the different physical properties of transition metals and chalcogens. So transition metals have high melting temperatures, low vapor pressures, so consequently, high growth temperatures are required for sufficient surface diffusion. So typical growth temperatures are in excess of 700 degrees C. Conversely, chalcogens have low melting temperatures, high vapor pressures, so high chalcogen to metal ratios are required in order to have sufficient chalcogen on the surface to promote stoichiometric growth. And finally, we need relatively low growth rates so that we can control the nucleation density and laterally grow the domains so that they coalesce and form a monolayer film with negligible bilayer growth. There are a variety of vapor phase growth techniques and sources that have been used for TMD epitaxy. A popular method is powder vapor transport, or powder CVD, which involves the vaporization of chalcogen and metal powder, such as moly trioxide, in a tube furnace under a carrier gas flow. This is simple to implement, but it's tricky to scale this process to large areas. MBE has also been used, but it's difficult to use ultra-high vacuum for sulfur-containing TMDs due to the very high vapor pressure of sulfur. So our approach has been to use metal organic chemical vapor deposition for TMD epitaxy. In this case, the precursors are introduced into the reactor in the vapor phase, and growth can be carried out at pressures closer to atmospheric, which reduces the vaporization of chalcogens from the growth surface. In our MOCVD process, we use metal hexacarbonyl sources for tungsten and molybdenum, and hydrides, including hydrogen selenide and hydrogen sulfide. These are photos of two MOCVD systems that we have in the 2D Crystal Consortium facility at Penn State. The first one is a horizontal cold wall MOCVD reactor that's capable of growth on a single 2-inch diameter wafer. And it loads and unloads through a glove box to minimize air exposure of the reactor and the sample. And the second system is one that we just brought online before the coronavirus shutdown. It has a vertical cold wall reactor with optical ports for in situ ellipsometry and laser reflectivity measurements. The results that I'll be discussing were all obtained in the horizontal reactor and another small scale system that we have in the lab. As I mentioned, we used high growth temperatures, moderate reactor pressures, and hydrogen as the carrier gas. The flow rate of the metal precursor, which controls the growth rate, is very low, but the chalcogen to metal ratio is quite high, over 4 orders of magnitude higher. And using these conditions, the typical growth rate is on the order of 1 to 3 monolayers per hour. To control the nucleation density and lateral growth rate of domains, we developed a 3-step process, which is demonstrated in this case for tungsten diselenide. In this process, the chalcogen flow rate is held constant throughout, but the flow rate of the metal source is varied. So initially, a high flow rate of the tungsten hexacarbonyl source is used for a short time to supersaturate the vapor phase and drive nucleation of a high density of small tungsten-containing clusters on the surface. Then the tungsten hexacarbonyl is switched out of the reactor and the clusters are annealed under hydrogen selenide for periods ranging from 5 to 30 minutes. And this enables the clusters to diffuse and ripen and small triangular domains to form. Then the tungsten source is switched back in, but at a lower flow rate to laterally grow the domains while suppressing the bilayer growth and additional nucleation. So this process enables us to control the growth rate at the monolayer level, and it also enables us to study fundamentals of the growth process. For example, this is a series of AFM images obtained at different times during the ripening step. All other conditions were held constant, and the ripening time was varied from 0 to 45 minutes. So initially, you can see that after 5 minutes, there are a high density of very small clusters on the order of 5 nanometers. And then as the ripening time is extended, the density of small clusters decreases and the triangular domains appear until after about 30 minutes, there are only triangular domains present. If we plot the domain size as a function of time, we can see that the domain size increases rapidly within the first 15 minutes, but then becomes relatively constant. We can fit the domain size and cluster density to a classical model of 2D ripening, where the domain size increases as time to the 1/3, and the cluster density decreases as 1 over time. And then we can use this to extract an estimate of the surface diffusion coefficient for the clusters, which is on the order of 1 × 10⁻14 centimeters squared per second, similar to the range of diffusivities measured for the diffusion of platinum clusters on sapphire. So this provides us with a way to extract information on surface diffusion in this process. Likewise, we can study how the growth temperature affects the domain size and domain density. In this case, we held the conditions for nucleation and ripening constant and just varied the growth temperature during the lateral growth stage. This is a series of SEM images showing that over the range from 700 to 900 degrees C, the domain size and density are relatively constant, which is consistent with a process that's limited by mass transport of source material to the surface. When the temperature is decreased to 600 degrees C, however, the average domain size decreases, and we get a bimodal distribution of domain sizes, where the larger domains have formed during the nucleation step, but the smaller domains have formed during the lateral growth stage due to their lower surface diffusivity at this reduced temperature. So this illustrates the role of growth temperature and surface diffusion in the process. In addition, the shape of the domain is dependent on growth temperature. You can see in the inset images that the domains transition from being triangular to truncated triangular as the growth temperature is increased. In this case, by varying the growth temperature, we are varying the chemical potential of the selenium species by desorbing more selenium from the surface at higher temperature. And this changes the relative growth rate of the tungsten-terminated and selenium-terminated edges. So at 700 degrees C, selenium is present in excess, which results in triangular domains with selenium-terminated edges. And as the growth temperature is raised to 900 degrees C, more selenium desorbs from the surface, which reduces the local selenium to tungsten ratio, and it causes the domains to evolve to a truncated triangular shape. We can test this by adding more of the selenium source during growth at 900 degrees C to increase the selenium to tungsten ratio, and we see that the domains transition back to being triangular. And then to get a coalesced monolayer, we just increase the lateral growth time. So in this series of SEM images, you can see that the domains are getting larger and they start to merge. And eventually, after about 45 minutes, we have a nearly fully coalesced film. There are also some darker triangles in the SEM image. These are bilayer domains that have started to nucleate. We can measure the monolayer and the bilayer coverage as a function of time. And we see that the growth rate of the bilayer starts to increase once we have reached about 50% monolayer coverage. At this point, it may be favorable for bilayers to start to nucleate rather than filling in the monolayer. But nevertheless, you can see that after about an hour, we have a fully coalesced film. Now, if you take a look at the orientation of domains in this image, you can see that they're primarily oriented in two different directions. These are the degenerate 0 degree and 60 degree domains that I mentioned earlier. And in this case, they're present at about 50-50 ratio. So when these domains coalesce, they'll form an inversion domain boundary. However, if we adjust the growth conditions by going to higher growth temperatures, 1000 degrees C, and even higher selenium to tungsten ratios, about an order of magnitude higher than the previous case, we observe a preferred orientation for the domains. These are two AFM images obtained at 10 minutes and 22 minutes during lateral growth. And in the 10-minute case, the majority of domains, about 86%, are pointing to the left. And as the film coalesces, the open regions on the sapphire have a triangular shape, which is pointed to the right. We don't know the exact origin of the preferred orientation yet. However, a recent paper on powder CVD growth of molydiselenide on sapphire suggests that the domains can become oriented at step edges on the sapphire surface. The benefit here is this provides us with a way to dramatically reduce the density of inversion domains in the films. Using this process, we can grow fully coalesced monolayer films of a range of TMDs on 2-inch sapphire. This is an example of tungsten disulfide grown on sapphire using hydrogen sulfide. For sulfur-based TMDs, we have to use even higher chalcogen to metal ratios due to the high vapor pressure of sulfur compared to selenium. These are AFM images of the surface of tungsten disulfide at the center of the 2-inch wafer and near the edge. The monolayer completely covers the surface and it's very smooth. You can see the steps in the sapphire. The triangular domains that you can see are bilayer regions that have started to grow on top. We can use in-plane X-ray diffraction to assess the epitaxial orientation and crystal quality of the films. From the phi scan, we have peaks associated with tungsten disulfide and sapphire, and this confirms that the films are growing epitaxially, and it also gives us the epitaxial relationship. In addition, the full width at half maximum of the phi scan peak for tungsten disulfide provides a measure of the in-plane misorientation of the domains. And in this case, it's relatively narrow. The full width at half maximum is on the order of 320 arc seconds, which is quite good for a heteroepitaxial film. And since this is a monolayer, it exhibits strong photoluminescence at room temperature, centered around 2 electron volts. To characterize the structural properties of the monolayer by TEM, we need to remove it from the sapphire growth substrate, and this is done using a water-based transfer process. So the sample is coated with PMMA, and then it's immersed in a water or a dilute sodium hydroxide solution, and capillary forces cause the film to peel away from the sapphire. These are photos of tungsten disulfide film being lifted off of a 2-inch diameter sapphire substrate. And then in this case, it's been transferred to an oxidized silicon substrate, or you could transfer it to a TEM grid or an electrical test structure for further characterization. TEM was used to characterize the microstructure of the tungsten disulfide monolayer to examine the type of grain boundaries and other defects that may be present. This work was done by Danielle Hickey and Nassim Alem at Penn State. So the selected area diffraction pattern is consistent with the single crystal, and the bright field TEM image shows contrast only associated with the bilayer. However, if we do a dark field TEM, we can see that there's additional contrast that appears in the monolayer that wasn't present in the bright field image. And I want to particularly point out the features marked as 1, 2, and 3 in this image, which don't show up in the bright field image. So if we obtain a composite map by overlapping a series of the dark field images, we can see that there are patches of contrast throughout the monolayer, as well as bilayers which show up bright in this image, and also some small voids and also tears that result from the transfer process. And I want to point out that the circular features in this image are artifacts from the TEM grid. So initially we thought that the regions of dark contrast may be associated with inversion domains in the film. Danielle carried out detailed high-resolution TEM characterization and analysis of the boundaries of these regions and found that they are not inversion domains. As you can see in this image, the lattice orientation is the same on both sides of the boundary. So So instead, these are translational line defects that result from a subunit cell misalignment of the lattice of coalescing domains. So this slight misalignment induces a tilt in the lattice, which changes the contrast primarily associated with the sulfur atoms in different regions. And this gives rise to the different contrasts between these regions. So these are regions that are bound by translational line defects. The good news is that we can modify the number of translational boundaries in the monolayer by adjusting the growth conditions. So in this case, we increased the growth rate of the film, which resulted in a reduction in the number of these regions with darker contrast. This particular sample has a very low bilayer density, so less than 1% coverage, and also a low density of these translational boundaries. So we can say that this sample is nearly single crystal. And then in addition to the tungsten dichalcogenides, we can also grow molybdisulfide and molydiselenide using this same process. And these films are all grow epitaxially oriented on the sapphire with a relatively low density of bilayers, with the exception of molydiselenide, where we see a high bilayer density for this particular case. As I mentioned earlier, we can transfer the layers off of the sapphire, and this turns out to be important because the properties of the monolayer are altered quite a bit by being in contact with the sapphire growth substrate. For example, the photoluminescence peak of tungsten disulfide is quite broad when it's still on the sapphire, and there's considerable variation of the peak position, which may be due to residual strain in the layer. However, when the tungsten disulfide is removed from the sapphire and transferred onto oxidized silicon, the peaks narrow considerably, and it's possible to resolve the exciton, trion, and other emission peaks at low temperature. In addition, the peak position is much more uniform. In this case, the PL properties are comparable to that reported for tungsten disulfide monolayer flakes exfoliated from bulk crystals. The transport properties of the monolayers were also characterized using field effect measurements. The backgated FET devices in this case were fabricated by Saptarshi Das's group at Penn State by transferring the molydisulfide monolayer onto a backgated test structure that included a 50 nanometer thick ALD alumina gate dielectric and nickel gold contacts for the source and drain. The transfer characteristics indicate dominant electron transport due to Fermi level pinning near the conduction band, which is common for molydisulfide. The mobility in this case is 30 centimeters squared per volt second extracted from the peak transconductance. And this compares very favorably with devices fabricated using exfoliated flakes. In this case, the molydisulfide flakes were about 5 to 7 layers thick compared to the monolayer thickness for the MOCVD film. In addition to sapphire, we've also looked at epitaxial growth of TMDs on hexagonal boron nitride. The motivation here is to identify a substrate material that doesn't negatively impact the TMD properties as much as sapphire, so that we don't have to do a transfer process. In this case, we used hexagonal boron nitride multi-layer flakes exfoliated from a bulk crystal and transferred to sapphire. So the flakes in this case are still quite small, on the order of several millimeters in size. Interestingly, we also see a preferred orientation for domains in this case as well for tungsten diselenide. About 84% of the domains are oriented in the same direction. This was also puzzling, as based on DFT calculations, the 0 degree and the 60 degree oriented domains should be nearly degenerate, so we should get an equal mixture of both orientations. Our collaborators, Yanqi Wang and Vin Crespi at Penn State, looked at the influence of defects in the HBN on this process and identified a stable defect pair that consists of a transition metal atom and a boron or nitrogen vacancy in the HBN surface. So vacancy defects in HBN can trap metal atoms, which then serve as preferred sites for nucleation. In addition, the particular defect type, boron versus a nitrogen vacancy, can impart a preferred direction to the TMD domain. We've been able to study this experimentally by controlling the defect concentration on the HBN surface. This is a series of AFM images showing the density of tungsten diselenide domains that have nucleated on hexagonal boron nitride versus sapphire for increasing growth times. On sapphire, the density increases with growth time, but on hexagonal boron nitride, it remains relatively constant, indicating that the density of nuclei is limited by defects on the HBN surface. We can also modify the defect density by plasma treating the HBN, which leads to an increase in the tungsten diselenide domains, or by annealing the HBN in ammonia to reduce the defect density, which leads to much lower nuclei for tungsten diselenide. So this provides further evidence of the role of point defects in this process. And then finally, if we grow a coalesced film on the HBN and compare the optical properties of the tungsten diselenide to what we would get for growth on sapphire, you can see that similar to what we saw for the transferred tungsten disulfide films, the tungsten diselenide on HBN has a much narrower PL peak width, and the PL is much more uniform on HBN compared to what we obtained on sapphire. The downside here is that we're back to using exfoliated flakes. However, there have been recent advances in CVD and MBE growth of large area HBN films, which could be used as a substrate for TMD growth. Before I wrap up, I want to note that this work was done in the 2D Crystal Consortium facility at Penn State. This is one of the NSF Material Innovation Platform facilities. It's focused on the synthesis of 2D layered chalcogenides. The MOCVD equipment that was used is part of the thin films facility, and we also have equipment for MBE growth and in situ characterization, such as ARPES and 4-probe STM. There's also a bulk crystal growth facility, which has equipment for CBT and bridgement growth of chalcogenide crystals. And finally, a Therian simulation facility that specializes in DFT and reactive force field molecular dynamics simulations. This is useful to simulate growth kinetics and mechanistic processes. This is a user facility, so it's accessible for free by the academic and government lab community. And we also host a number of outreach activities. So if you're interested in learning more, please check out our website. To summarize, TMDs are an exciting class of ultra-thin semiconductors with a wide range of potential applications. And while exfoliation of flakes has been used for many of the seminal studies in this field, this won't be a limiting factor for device development. Epitaxial growth technologies are rapidly catching up. However, this is a field that's still in its early stages, and many challenges remain, not only in material synthesis, but also in processing, such as contacts and dielectrics. So there are many opportunities for continued research. And then finally, I want to acknowledge the people who did the work on this project, members of my research group, in particular, Xiaoten Zhang, Tanushree Chowdhury, Mikhail Chubarov, Ray Zhu, and Ben Hewitt, as well as collaborators at Penn State. And finally, the National Science Foundation for funding this work through the MIP program. Thank you. If you have any questions, please feel free to contact me by email. Stay safe.
So nice presentation. So we can convey our thanks to Professor Redwing, and we can now start with our next invited lecture by Professor Mahesh Kumar. He is an associate professor of IIT Jodhpur, and his main research interest focuses on 2D materials, semiconductor materials and devices, nanomaterials and sensors, and so on. He has received his MTech from IIT Delhi and has completed his PhD from ISC Bangalore. He has more than 100 publications. He is basically a recipient of various medals and awards like INSA medal for young scientists, then MRSI medal, DAE Young Achiever Awards, and so on. And he is the founding member and served as Young Academy of Sciences. So he will be delivering his lecture on real-time detection of heavy metal ions using aluminum gallium nitride on gallium nitride for high electron mobility transistor for water quality monitoring. So we can look forward for his presentation. So Professor Mahesh Kumar, please.
So first of all, I would like to thank the organizer for inviting me for this talk. So today I am going to talk about this heavy metal ion detectors, and we have used aluminum gallium nitride, high electron mobility transistors And basically we have functionalized the gate, and then we can make the selective heavy metal ion sensors. So if we talk about the water quality in the last few decades, really this water quality has degraded, and this pollution starts from the surface water, and mainly due to the basically we are throwing the chemicals and stuff in the water, and these surface water mixed with the groundwater, and then overall our this water circulation system is there. This one is disturbed by the type of the pollutant here. And broadly, we can divide these pollutants in three categories. First one is the pathogenic organism. Second one is the basically organic materials, and third one is the heavy metal ions. And today I am going to talk about these heavy metal ions, how to sense basically by using these semiconductor devices, by using the 2D materials here. And because these heavy metal ions are toxic in nature, and we use applications, and from these applications basically they are mixing, they are coming in our water sources and destroying the complete cycle here. So these are the recent basically news from the country here, from the different parts. For example, in the West Bengal region is arsenic arsenic dominated. So in the water, arsenic quantity is higher. Also in MP and other parts of the country, there are the different these heavy metals, ions, mercury, cadmium, lead here. So we talk about a few, mainly the mercury here, how to measure the mercury here. So few heavy metal ions in a certain quantity are useful for our health basically, and these are the copper, zinc, iron, and silver, but in only in the certain quantity. And here you can see in this table, these are the WHO defined limit is there, how required for both. Other metal ions, example nickel, arsenic, chromium, lead, mercury, these are highly toxic here. Right here you can see the water quality. And basically this one is the TDS level, how much TDS level we have. And mainly in the Rajasthan and Gujarat, this TDS level is very high. So how we are measuring the TDS? Basically, we are measuring the conductivity of the water, and from there, at conductivity, we can calculate what is the level of the TDS here, water is drinkable or not drinkable here. But there is no relation between the TDS and the heavy metal ions. There is high possibility we have less TDS, but then also the possibility is there we have the heavy metal ions here. So how to detect basically these heavy metal ions? And we need some real time monitoring system. For example, water purifier, we are drinking the water, but we don't have the display. Just we trust on our cartridge here, whatever water is coming, that one is the drinkable, but we have to test, we need some real-time monitoring system. And for this, we have to develop the sensor, and then whenever water we are getting, in the display we can get how much TDS is there, how much mercury level is there, arsenic level is there. And this basically, as per region, we can develop, for example, in the West Bengal, we have the high arsenic level. In MP, in few regions, we have the mercury and lead here. So as per region, basically, here we can make this display, or we can make the common display here. If you see in the literature, there are many methods by using that we can measure here. So mainly these are the electrochemical, biochemical, and colorimetry. So these are the TDS method. Again, the size is basically big size when we are making, basically based on the electrochemical. Another we are using, for example, in the lab we are using ICP, but we cannot install everywhere ICP because of the high cost here. But if we can develop that low cost using these semiconductor materials, that we can basically attach with every water purifier, and then we can see the water quality is drinkable or not here. So we can use these semiconductor based devices to monitor the water quality. So already basically here we can use the field effect transistor. So we have the basically channel in between this one, And by using this semiconductor, we can make similar to glucometer. For example, we can put one drop and then we can test, or we can in the water purifier, we can insert basically this one, and then we can get the real-time data, and then we can connect with the microcontroller and can check basically is this water is drinkable or not here. So for this, what we have done here, we have used the 2D materials. So first thing, why 2D materials here? So here, general concept is that if you reduce the dimension, what will happen? This make the less mobility, but in the quantum, this phenomena is opposite due to the quantum confinement here. If you reduce the dimension, basically mobility is high. If mobility is high, then the overall the sensor response will be short here, and we need the basically high response here. We need a short response time, so we can make basically the fast sensing system by using these 2D materials. Another concept here is that suppose this, if you are using the simple our field effect transistor here, so when we are applying the threshold, above threshold voltage here, channel is forming, and this channel I can consider basically based on the thickness. So in this case, we have the slightly this one thicker layer, and when we have the thicker layer, basically what is happening, these ions impact is only on the top surface, not at the bottom. These at the bottom level here, and carriers can move from the bottom here, because carriers will follow the shortest path. So here on the top surface, if you have impact, carriers can move from the bottom. So overall, whatever quantity we are measuring, electrical quantity, overall the impact will be less here. But if we are using the 2D materials, because we have very thin layer, or you can say we have only one monolayer or few monolayer, in that happen will be high. Okay, whatever here charge transfer is taking place between the these ions, and particularly our channel atoms here, when these ions are coming in the contact, so overall impact will be high, and whatever this electrical quantity we are measuring, this one, we will get the high change corresponding to the small amount of these metal ions here. To make this one we can use directly 2D materials, for example MOS2, WS2, or graphene we can use. Another way is that we can play with the band engineering, and then we can make basically here in few materials we can make the 2D electron gas, 2D electron channel, and for this here, gallium nitride and aluminum gallium nitride is popular for this one, these high electron mobility transistor. So what is happening here, this one is the gallium nitride, this one is the aluminum gallium nitride. For example, we can say this one is the conduction band is there. And now due to this polarization, what is happening, these carriers are trapped at the heterojunction. Now in this direction, basically, we can make the source here, and then we can take the advantage of this 2D electron gas, and we can make the high electron mobility transistor. Already we are using mainly for the power and high frequency applications. So same here we have used for these heavy metal ion sensing purpose. And this one is the well-known phenomena because of the polarization. Here these electrons are trapped basically and making the 2D electron gas. And here you can see this 2D electron gas we can make to make these high electron mobility transistors. So why gallium nitride for the sensing purpose? Here these are the few advantages. One thing, gallium nitride basically is stable in the water. Another, gallium nitride we can use in the harsh environment. Mobility is also high here, and we have the more this one dangling bonds particularly on the surface. So because of this one we will get the high sensitivity. There are in this one other, again we have the wide temperature range. So these are the other advantage. Because of this one we can use this gallium nitride. We have grown this gallium nitride. Basically our collaborator from IMRI Singapore, they have grown for us this gallium nitride, aluminum gallium nitride HEMT structure. So you can see here we have to do the stress management. We have to minimize the defect and dislocation density. And finally here to grow these gallium nitride and aluminum gallium nitride, because gallium nitride substrates are not available. So we have to grow on the foreign substrate. And here our collaborators, they have grown on the 8-inch silicon wafer by using the MOCVD reactor. And here these are the parameters. For more detail, you can go through these papers here. I will not go in more detail about the growth, but what we have done here at IIT Jodhpur, we have fabricated these devices. So we have made the basically source and drain contact, metal contact. We have deposited these tri-metals, aluminum, chromium, and gold. And then we have made the ohmic contact. First, we have tested by using the TLM method, how much is the contact resistance. Then we have isolated basically by using the silicon nitride, by sputtering we have deposited, and then we have deposited basically the gate, nickel, gold. And here you can see the schematic diagram, and this one is our actual device is there. So here we have source, drain, and this one is the gate here. We can also apply the bias on the gate, but here so far we have not applied the biasing. Biasing is coming because of these ions. Basically ions are creating here electric field here, potential, and due to this potential here 2D electron, this density is changed, and we are getting the change in the source drain current here. So here you can see basically here, this one is the gold here, but again for the different heavy metal ions, we have to gate, and we have to make the selective sensor here. And to make selective, we have used the various basically here nanomaterials, 2D materials, and then we have made for mercury, lead, and so you can see system, we are inside the water, and in the water we have dissolved the this known quantity, and then we have measured basically how this current is changing. So first we have made for the mercury, and for the mercury, this functionalizing material, we have used the MOS2. At IIT Jodhpur, we are growing the MOS2 by the different technique here. So here you can see that the cost, if you buy the 100 gram MOS2, bulk MOS2, we will get in the around 70 USD from the Sigma Eldridge. But same if you buy monolayers, 1 centimeter by 1 centimeter square MOS2, around cost is around 700 USD. But same if we convert this 100 gram MOS2 into monolayers, around cost will be the around 70 million USD. That means here this fabrication process is the complicated. Because of this one here, the cost is very high here. So at IIT Jodhpur, we are growing by the chemical vapor deposition. Also, we are trying with this one by sputtering, we are depositing. But in this case, we need the low temperature method here, because already we have fabricated source and drain. Now we cannot grow in the CVD because temperature is very high. So what we have done here, we have used this hydrothermal method. We have used MOO3 precursor, NaOH, and this thiourea, and then here you can see we have kept in the autoclave, and then finally basically we have synthesized this MOS2, and we have characterized this one. So grown material is basically MOS2 by the Raman spectroscopy and by Icee, E2G and A1G peaks basically, and here you can see the electron microscopy image. So you can see these are the basically flakes here, and we need for the sensors particularly the large area. And here if you have the flakes, basically more ions can be absorbed on the surface here. And then next we have functionalized our gate. How we have functionalized here? So basically here we have fabricated the source, drain, and gate we have functionalized. You can see here, so on the gate basically by the drop cast we have put, basically we have dissolved in IPA, and then we have used the different concentration, and then we have uniformly basically distributed on the gate here. And finally here again we have done the characterizations. So you can see after transferring this MOS2 on the gate here, we have done the characterization. This one is the surface morphology, how is there. Now this is the cross section. Again, we have done the basically Raman spectroscopy. We have confirmed this one transferred material is the 2D MOS2 is there. This one is our sensing setup is there. We have measured this IV here, this one for the bare device. after functionalizing the MOS2, after this one using the 10 ppm of this one mercury, how basically current, this source drain current voltage is changing here. And here you can see with the time here, we have used the different this one concentration, even because WHO defined limit is around 5 ppb is there, but our sensor is able to detect below this one also here, below 1 ppb here, and then again the current is changing depending on the concentration, how much concentration of mercury is there here. So easily we can make out from the current change how much change is there in the current, and then we can develop this sensor here. We have also proposed a mechanism basically sulfur, because of this one here making the H2S bond, and because of this bond here, what is happening basically, these ions are absorbing on the surface and developing the potential, and because of this potential here, electron density in the 2D electron gas is changed, and overall this current is here changed particularly. Also, to make the selective, what we have done, we have used the different ions here possibilities, because few certain ions are useful for our health here. So we have used cadmium, copper, nickel. Here you can see this one, and our sensor is highly sensitive to mercury here. Mercury. Also, we have mixed and checked the cross selectivity, and then also we found almost here the sensitivity here change in the current is almost is the same here. So we have calculated basically sensitivity, linear detection limit here. So in the lower range, sensor is the linear, basically transfer function is the linear, so easily we can detect basically how much mercury level we have here, and this sensitivity and this detection range is indicating that we can make in the lower range, we can make these sensors for the commercial applications. Again, we have basically optimized the functionalized this one. We have mg 20 40 here, and we found this one 20 mg is basically sufficient, because we get the this one limit of detection is around 15 ppt. That one is this one below, then the defined limit is there. So by using this one, we can calculate this one limit of detection. We have calculated here. You can see how this current is changing when we are using the different this concentration of mercury, and also with this concentration of MO. So this one improved the sensitivity by using the UV illumination. So in this case, what we have used the UV illumination. By the UV light also we are killing the bacteria. So same here, light source we can also attach with our mercury sensor, and then we found this one, our response time is improved, also sensitivity and limit of detection also improved. We have published IEEE transaction of electron devices. So by activating by the UV light, we can improve the sensitivity and selectivity here. Recently also we have basically mixed, because MO is less as compared to the metal. So what we have used here, we have mixed with aluminum nanowire and MOS2, and then we have functionalized with this one, and we found this here sensitivity is this one almost double compared to MOS2 here. So by using here this composite silver nano and MOS2, this we can again improve the sensitivity. Selective, you can see this one. This sensor is selective to mercury. Have done for cadmium and lead here. Because of that, here briefly I will talk about this one. So how we have made cadmium? Cadmium first we have deposited the MPa, because MPa here this is good addition with the gold. So we have to see the targeted ion, also how to absorb. Also we have to see basically how to absorb our functionalizing material with the gold, because both are important. So here we have used the MPa and this one GSS. Mostly this one is the chemical. I have taken the help from the chemistry department. you can see the mechanism how this one is making the bond with the cadmium. So we need the good adhesion with gold. Also, we need the good absorption with our targeted heavy metal ions here. So here you can see the sensitivity. Another important, if you are making the real-time sensor, this response time is very important. So our sensor is able to give the data within 3 seconds. That one is reasonable, very good result here. Again, the selectivity, sensitivity, we have calculated this one, and these are the much lower than the WHO defined limit here. We have also measured the selectivity. Here you can see. So the sensor is this one cadmium selective, but also we got some response from the this one lead here. So idea is that we can mount this one different sensors on a single chip, and then from the data analysis by using the here machine learnings, we can make basically the here get the actual concentration, how much which heavy metal ion is present. Also, we have developed for the lead, and for the lead we have used this TMDD, and then we have made this particularly here sensor. So again, if you see the limit here is much below than the 1 ppb, we can measure even in the level here. So sensitivity is also very good here, and this one limit of detection is also very good, around 18 ppt is there. So now here again we have checked for lead also, we have checked basically this one selectivity, how is the selective. So this sensor is highly selective to lead here, but we got small this one response from the mercury, because this our gate is not fully functionalized. Somewhere gold is there, and gold is always sensing the mercury here. But by using mercury and lead sensor, we can quantify this one, how mercury basically we have. And again, we have tested basically repeatability here. So we have used the different concentration of these lead ions, and then we have measured, and simply by using the DI water, we can clean this one here. Now we are basically developing all these sensors on a single chip here. So we are already we have fabricated mercury, lead, and cadmium, and now we are planning to connect with the IoT system, and then we can make the real-time this one sensor similar to the glucometer here, and then we can put one drop and we can test basically how much level of these heavy metal ions are present in the water here. So I would like to summarize my talk. We have grown, basically, we have functionalized the gallium nitride, aluminum gallium nitride, here HEMT gate, and then we have used basically made this heavy metal ion sensor for different ions, mainly for mercury, cadmium, and lead. In the mercury also, we have improved the sensitivity by using the UV illumination, also by using the silver and MS2 nanocomposites here. So at the end, I would like to acknowledge this work is mainly done by the Adarsh Nigam and Nipun here, and I would like to thank Dr. Sudhir Ranjan Tripathi, because these wafers were grown at IMRI here, A-Star, and for the funding agency SERB. So thank you very much. You can ask me.
Okay, thank you, Professor Kumar. So it's a nice and informative talk. So we can go for some questions.
Yes, sir. Yeah, Akshay here. Sir, I have a couple of questions. Very interesting talk. Sir, first question is why specifically this sensor is giving high sensitivity for Hg2 plus or cadmium? So do you have any surface modification on the gold?
Yes. Yeah, because we have functionalized the gate basically. For mercury ions, we have used the most to nanocomposite. So basically, M2 is absorbing this mercury ions. And for example, for lead, we have used the different materials.
Okay, and you have coated this MOS2 using hydrothermal method. So how stable is that on the surface of gold? The adhesion, I want to ask.
Actually, we have synthesized by the hydrothermal, but simple drop casting we have on the gate, and then we have the.
So, have you taken the mixed ions water or the specifically single ion when you were casting on the device?
No, we have used mixed also. Yeah, you can see here we have used this one graph is the mixed ion.
Yes, sir.
We have mixed all ions basically, and then we have taken.
Okay. And the last question is, what about the debye length? Have you taken into account that?
Debye length for what?
For detecting the ions means. I know that there are like in bioreceptors, there could be a little bit screening of ions. So in your case, you have used MOS2. So,
yes.
So what is there like in still there some screening of ions, or specifically it's attracting the specific ion?
No, actually they are attracting. Basically they are this one, and then making basically absorbing on the surface.
Okay, sir. Thank you.
Yeah, thank you. Thank you.
Yeah. Hello, Professor Mahesh.
Yes.
Yeah, I am Gufran. Thank you very much for your nice talk. So I have a couple of questions. That what is the source of power? If you going to connect these sensors in the IoT network, what will the source of power and how much it will means how you will connect this power these sensors? This sensors array. You have built basically sensors array.
Yes. So for each sensor, we are using around 0.5 volt or 1 volt.
Okay.
Okay. So now we can calculate here how many sensors we are connecting. Suppose we are connecting 5 sensors, we need at least.
Okay, and if you are connecting the network, so means have you also tested the durability of this sensor? Because if on the frequently basis you will change these sensors.
No.
If you continually collect the data.
Actually, we have done around 50 cycles, not more than that.
Okay, 50 cycles only. So all sensors.
Yeah, 50 days basically. Cycles are more. We have this one continuously. We have monitored for the 50.
Okay, and the second, I have one issue with the reliability, that if we are going through means any thin film material through the hydrothermal methods, so each and every time when you will develop the materials, the morphology will be different. So these sensors will behave differently, or every time it will change.
Yes. Basically, the current is slightly changing.
Okay, so then how means it will affect on the data collection automated when you will means collect the data through the microprocessor? So it will affect there also?
No, actually data we are measuring the change, how much change is there in the current. So our base current is changing because of this one morphology and this one. Not the change.
Means every time we have to do the calibration again and again.
Yeah, calibration we have to do for each sensor.
Okay, for each and every, okay. Means every time when you will going to change this again, then you will do the calibration for that.
Yes, that we have to do.
Okay, thank you.
Yeah, thank you. Yes, thank you, sir.
Any more question? If no more question is there, so we can again thank Professor Kumar for his nice presentation and move to the next presentation, which is the first oral presentation of this session by Mr. Ankit S. Rao, ISC Bangalore. So is Ankit Rao here?
Yes, am I audible?
Yes, you are audible. So you try to finish your talk within 10 minutes and then we can take few questions.
Okay, I'll try. Hello, so my name is Ankit. I am from Center for Nanoscience and Engineering at the Indian Institute of Science in Bangalore. I work with Professor Vasu. So today I'll be talking about modeling and experimental evidence of the effect of, just a second. Sorry. So the effect of concentration gradients on the surface processes during CVD growth of So as we had the presentation from Professor Edwing, she discussed about the necessity of 2D materials and why we require large area. So I'll just briefly discuss the synthesis methods. So there are, by and large, 4 to 5 synthesis methods by which you can grow 2D materials. CVD is the, by and large, most important and most studied, as you can grow wafer scale materials and then make devices out of them. So there have been a lot of work on wafer scale technology and to understand how these materials can be grown on large scale. So we can see here for graphene and for HBM, there have been a lot of developments in time. And similarly in TMDs such as MOS2, WS2, we see that people have grown over large areas. But still, there isn't an industry standard, as every process differs due to various parameters and various other things. So we need to understand how these 2D materials grow to have a standard technique of wafer scale commercialization. So this is a figure which shows how the thermodynamics and kinetics of the precursors on the substrate and the vapor phase affect the growth on the substrate. So as we see here, there is vapor phase precursors which are affected due to thermodynamics. They come on the surface, and there is a lot of reactions and various other processes, surface processes happening, which affect the growth. And then by that we get multi-layer, monolayer, various other we get materials out of it with different properties and stuff. So we need to understand this growth mechanism and how we can control this growth on the surface as well as in the vapor phase. So for that, many groups have taken up large-scale modeling of CVD, such as multi-scale modeling with simulation efforts to study how the flows and the concentration gradients and the surface processes due to various parameters affect the growth on the surface. So this is one of the examples here. They study the effect of concentration gradients on the surface, and they see very good. This is the simulation. This is the experimental result. They see very good correlation between them. So there is a need for understanding these processes, and thus simulation is one of the ways to understand them. So now I'll discuss the system in which we do our growth. So the system I'll be discussing is MOS2. Okay. So we use the precursor MOCO6 and H2S for the growth of MOS2. MOCO6 is a solid precursor which can be vaporized and sent inside the reactor, and H2S is a gas. So we have precursors outside the system which can be flown inside at a certain pressure, temperature, and a certain flow rate. So this is why we call it as a true CVD, because we have control over all the precursors. So to understand the growth, we incorporate or we bring up a term called as supersaturation, which is given by this term delta G. Delta G takes into account the energy which is driving the reaction in the vapor phase in this case. As we see here, there are a lot of terms involved. And if we see, there is a temperature term which can be controlled by the furnace temperature. We can control the flux of the moly precursor going inside. We can control the H2S precursor with MFCs and other stuff. We have CO, so we can incorporate an additional reactant to suppress the reactions happening inside the reactor. And we have the pressure as well of the system, which is controlled by the throttle valve. So we have control over all these parameters, and thus we can control the supersaturation, which in turn can help us control the deposition rates. So these systems have certain complications as they have multiple precursors. There are multiple reaction pathways, so you have to optimize them. But there are opportunities as well, as you can control the nucleation densities and the growth rates to get single crystal wafers, as Professor Edwin discussed. We can have large grain sizes, uniformity, and also control defect densities to have like favorable properties required. So this vapor phase supersaturation, as we have discussed, affects the surface supersaturation, which affects which is the energy driving the reaction on the surface, which in turn affects the nucleation and growth. So by discussing or by understanding these terms, we can understand this growth on the surface. So let's discuss the surface processes which are involved in the MOS2 growth. So this picture here shows us that there are multiple processes. There is adsorption, which is the precursor coming on the surface. There is desorption, which there is surface diffusion. There is attachment to the growing edge or the growing nucleus. So all these terms affect the nucleation density, which is the number of nuclei per unit area, which in turn also defines the grain sizes, and these terms also affect the growth rates. So the rate at which these edges grow. So we have to have a control over these phenomena to have favorable growth. So here we can see in our system, we go from very low, very high nucleation density and very low growth rate to a very high growth rate and very low nucleation density. So this is around a 60 micron triangle, this is around a 1 micron triangle. So we have a lot of control over the system by having control over the surface processes. We'll discuss how we get to it. So let's see how these processes are in terms of the equations, the energies and the equations involved. So the delta G, as we discussed, affects the surface supersaturation. The vapor phase affects the surface supersaturation. So if we increase delta G, the delta G surface should increase. Then the delta G 2G star, which is the barrier to the 2D nucleation. So the nucleation which is happening on the surface is affected by this delta G surface term inversely. So if this increases, the other decreases. In turn, this affects the 2D nucleation rate. So the 2D nucleation rate is the rate at which in a particular area per time, how much nuclei are forming. So this increases if there is an increase in this term. Also, there is an effect of surface kinetics. We'll discuss it later. And also, this J naught and this surface kinetics and 2D delta G surface term also affects the step velocity of the surface edge that is growing, as we had discussed. So all these terms, in effect, determine the saturation nucleation density, which is the nuclei which are in the end forming grains on the surface. So vapor phase processes affect the surface processes, and these vapor phase processes are affected by lots of parameters such as flow profiles, reaction pathways, mass transport, that is the concentration gradients across the reactor. Okay, sorry. What happened? Hello. Hello. Am I audible?
Hello. Can you again share your things?
Yes, sir. I guess somebody else shared the screen. Okay.
Who shares? If somebody is sharing, please stop sharing. And you try to finish within another 2 minutes because it's already okay.
So yes, okay, I'll try. Okay, so these in turn can affect the PT. So by controlling these terms, we can control the reaction inside the tube. So this is the flow in a tube reactor, and this is the velocity profile. This is the diffusion profile, which affects the flux on the surface. I'll go fast as there's no time. So for a certain conditions inside the reactor, we simulate the effect of these flow profiles. So we see that there is a red means there is a very high concentration gradient across the surface. So we see at low pressures of 20 torr, there is a very high gradient which results in bulk growth or multi-layer growth. As the pressure increases, there is a drop in the concentration gradient across the boundary layer, which in turn drops the nucleation density and the growth rates. And with further increase in the pressure, we see further decrease in the concentration gradients, which results in large grain sizes and low nucleation densities. So we simulate it for various pressures and temperatures, and we see that at higher pressures and higher temperatures, there is not a lot of effect. Thus, all the three substrates across the reactor should have uniform growth. And we see this experimentally as well. We place 3 different substrates, and we see that the nucleation density and grain sizes are similar across the three substrates. So the nucleation density and grain sizes also can be varied. So at 600 torr and 750 degree Celsius, we see a grain size of 20 nanometers and close to 10 raised to power 8 per centimeter square of nucleation density. Whereas at a higher temperature of 1050 and 900 pressure, we see a grain size of around 60 microns with an decrease in nucleation density 10 raised to power 5. And keep in mind that all these growths are done at the same time. So if there is no change in time of growth, there is a lot of effect on surface processes, which affect the 3 orders of reduction in nucleation density and 4 orders of. So by modeling this phenomena, we see that the nucleation density linearly increases with time, but eventually saturates. And there is by coverage data, we can calculate the growth velocities. So we see with increase in pressure, there is drop in nucleation density. And we extract the energy values from the plots that we show. So with increase in time, the nucleation rate should drop, which is expected due to higher rates of desorption. Whereas with this nucleation rate is a function of this EJ0, which is defined here. Thus P increases, EJ0 increases, so nucleation rate drops. Thus we see a dominance of surface kinetics. And the step velocity also has an effect. So we see with P increasing, the nucleation rate drops, thus the delta G on the surface will increase, which then increases the V step. And with increase in T, the step velocity should increase due to diffusion dominated growth. So by this, we also calculate the saturation nucleation density, which is given by this, as it is a function of J0 and V step. So we see two regimes coming up. At higher temperatures, we see a desorption limited, which is limited by the availability of atoms. And at higher temperatures, we see attachment limited, which is limited by capture of the atoms to the supercritical nucleus. So in turn, by physicochemical modeling, we get large ions of close to 141 microns in a very small time frames of 40 seconds, and has a growth rate of 3.3 microns per second. So we determine that the concentration gradients determine the flux of the precursors on the reacting surfaces. The nucleation density of the domains in the CVD process can be controlled by tuning the supersaturation. And the saturation nucleation density of the MOS2 has a strong dependence on the steady state nucleation. And by all this analysis, we come to a very large grain size domains of MOS2 with a relatively large step velocity, which has been not reported yet. Thank you. So this was a very fast and fast-paced talk. I'm sorry for that, but if you have any questions.
Okay, so thank you, Ankit. We can take one quick question, if possible.
So, Ankit, what is the thickness? Is there any monolayer thickness variation? Like how many monolayer?
No, sir. So all the data is for the data shown is for monolayer. So we have controlled the densities and the grain sizes for a monolayer of MOS2. We can, so in another paper that I had mentioned, so we have discussed the effect of supersaturation on the thickness, like the layers of MOS2. So we can go from bulk to N, 2, 3, 1. So we have done that work as well.
Okay, thank you.
Yes.
Okay, so we can quickly move to the next speaker. The last presentation is by Shamir Kumar Malik from IOP Bhubaneswar. So is Shamir Malik there?
Yes, yes.
So
Okay.
can you quickly share the Shamir and as Professor
And
Kostov does mention, try to finish.
yeah, try to maintain the time. So keep it within 10 minutes.
Because 3:30 we'll have a poster session in this same hall. Okay. So
Yeah, so we should finish it.
Samir, can you share your things? Hello, Swami, we are not able to see your screen. Can you share it quickly? Hello, Shamir, are you there?
I think he is not connected now. Samiti, can you hear us?
Shamir, can you hear us? We are not able to, yeah, you are coming and going. You don't have to switch on your video. You just share the
Yes.
screen and then start. Because video, if you switch on, it takes maybe more bandwidth. You just share the screen and start presenting. Yes.
Yes, start your presentation, please.
Hello.
Yes, we can hear you. Just share the screen and start presentation.
Hello.
Is Samir is here or not?
Shomir, I don't think he is here. I didn't find his name in the list now.
Hello.
Okay, he is there. Yeah, can you hear?
Yes, yes,
So, can you start the presentation?
yes.
You don't have to switch on your video. Just share the link and start the presentation.
Okay. By switching on the share, it is taking me to the switch to the desktop app. This browser. Okay.
So you just share content. You share the PPT. Then you click on the PPT.
Give me 20 seconds, please. ବୁଝିପାରିଲି କଣ ହେଇଛି? Hello.
It is sharing. Just do it.
Okay.
You just open the your PPT. We can see now it is fine. Just go ahead and try to finish within 8 minutes because we have a 3:30 poster presentation in the same room for different. We have to leave this room.
Okay.
Okay, go ahead.
So today's talk is about our recent work, and you can find this work on archive. It is, and this is our group at Institute of Bhubaneswar, headed by Professor Satyaprakash Sahu. This is the outline talk, today's talk. And regarding the MOS2 is a very well-known material due to its atomically thin layered structure and owing to its varying application in the several device applications in low power electronics. So in this study, we are using monolayer MOS2 synthesized by the CVD methods. So this is our CVD setup, and these are the parameters that affects the growth conditions. And in past few years, the salt-driven CVD technique is becoming more popular due to the large-scale growth. So here we are using NaCl as our growth promoter for the large-scale MOS2 growth, and we can see that from this vapor pressure of transition metal oxides and salt, that vapor pressure of salts is very high as compared to the transition metal oxides such as MO3 and WO3. So during the vapor phase reactions, the fusion of MO3 and NaCl brings out an intermediate product which forms a molybdenum chalcogenides, so molybdenum oxychloride, which is highly volatile and which increases the sulfurization and reaction rates, which again promotes the lateral growth. As a result, we can see from this microscopic image that with NaCl we can reach, we have optimized our CVD parameters to reach up to 70 microns, but without NaCl, we have reached up to 10 to 15 micron lateral dimension. And these the number of layers are confirmed by the Raman images, microscopic images, by seeing the frequency difference between the monolayer layer and multilayer MOS2. So before going to the fabrication part, it's just a DFT calculation to study the interfacial properties such as metal-induced gap states and Schottky barrier. So here MOS2, two views of the MOS2 and Icee heterostructure, and these are the partial density of states of the, this is the for pristine MOS2, and this is for a heterostructure. And as we can see around the band gap region, we can see some overlapped molybdenum and the sulfur states in the band gap region. We have also conducted a band structure calculation which shows the direct band gap for monolayer MOS2 and the projected band structure of MOS2 in Icee MOS2 heterostructure. And from this projected band structure, we can directly calculate the Schottky barrier, which is nothing but the energy difference between the consumption minima and the Fermi level of the Icee MOS2 heterostructure, which is here 153 millielectron volt, which is considered to be as a low Schottky barrier and forming a N-type contact. So now coming to the experimental part, here fabricated the monolayer MOS2 field effect transistor, and this is the high magnification image, shows the Icee electrode fabricated on the monolayer MOS2 samples, CVD grown samples, and this is the schematic which shows the cross-sectional view and the necessary electrical contact for the backdating. And these are some steps for electrode fabrication. And this is the output and transfer characteristics I have got. So output we are seeing that a completely linear characteristics we are seeing. So it confirms the ohmic contact between the MOS2 and Icee metal electrode, and also the dependence of the current, drain current with respect to the gate voltage shows the stable gate control. And in the right hand side graph, we can see the transfer plots between the drain current and the gate voltage, which shows again the high current on-off ratio up to in the order of 10 to the power 7, and which again shows the stability and low power performance of this transistor. So after we have also carried out the mobility calculations in both the case, that is the ambient pressure condition and vacuum condition. So in vacuum, we have gone up to 10 to the power minus 5 millibar pressure. So in ambient condition, we can see the mobility is around 3 centimeter square voltage in second inverse, where in case in vacuum we can see the mobility is increased up to 4 to 5 times, that is 15. So also the not the mobility, also the current on-off ratio is also increased in case of vacuum as compared to the air condition. So this is expected due to the carrier confinement and carrier trapping, and also scattering center presence due to the ambient surrounding effects in case of ambient condition. So this is our mobility and current values for our as synthesized with a comparison to the previously reported some results. So we are getting a good mobility. For the study of the hysteresis, we have conducted dual sweep measurements, DC measurements, where, again in both air and vacuum condition. So what we observed that in air condition, we have got the hysteresis with around 21 voltage, where in case of vacuum condition, it is decreased to 95%, that is 0.91. So in case of vacuum, the external factor that affects the hysteresis, that is the adsorption and ejection of gases, is removed, and that's why we are getting a very low hysteresis. But still, this remnant hysteresis cannot be characterized or cannot be minimized by using a DC measurement. That's why we are switching to the pulse IV characterization. So in case of pulse IV characterization, due to the shorter measurement time, we are getting we can characterize the remnant hysteresis. So here a DC characteristic is also shown for the fair comparison, and here the pulse sweep the pulse width is also changed from 90 to 0.5 millisecond. So as we can see, upon decreasing the pulse width, the hysteresis becomes nullified. So and we are getting a intrinsic transfer characteristics and high mobility. So right hand side we can see by in case of DC mobility we are getting 15, and in case of shortest pulse width we are getting mobility 30. That means 100% increase in mobility. So and also we can see the hysteresis width dependent pulse width dependent width, which is decreasing and giving a 0 value for the shortest pulse width. So to correlate these results, we have also carried out the waveform transient current analysis, where we have applied a single gate voltage, which is shown in the and the corresponding current measurements are and the corresponding currents are measured. So in these cases, we have measured, we have carried out 4 waveform measurements drain current of different pulse width with decreasing pulse, and we can see the highlighted region represents the reduction in drain current throughout the trapping mechanism, and we can see that with shortest pulse width at 0.5 millisecond, no drain current reduction takes place, which implies to the intrinsic transistor performance, or which gives the intrinsic mobility, as we see from the previous slide. So these transient drain current are modeled by are fitted with 2 models, that is 2 trap model contains 2 time constant, that is tau1 and tau 2, which is time constants for faster and slower trapping constants, and these are the trapping fitting parameters. Hello?
Can you finish within 1 minute, because we are waiting
Yes.
for
No. So this is the summary. We have also observed the for 0.5 millisecond pulse width, no degradation in the drain current value, which illustrates the 100% increase in the mobility, which gives the intrinsic transistor performances. Finally, I acknowledge my group for this work. Thank you.
Okay, thank you, Shamir. So since we are out of time, so we cannot take any more question. So I switch it over to the organizing committee.
Okay, so as there is no time because other people are waiting for the next sessions to start. So because other session will start in this. So our 2D material session will start in the hall number 8 for the poster session. And we are very thankful to Professor Kaustav Das for chairing this session and both the invited speaker for giving the nice presentation. And we thank to the contributed speaker also. Thank you.
Hello, yes, sir. Hello, sir. Our session in hall 8. Hello, yes, sir. Okay.
Hello. Is my screen is visible to everyone?
Yes, ma'am.
Visible.
Yes. Then I am sharing the posters. So whoever is giving the poster, the first poster is from Himanshu. So he can start. He'll be giving 2 minutes for speaking and then 1 minute for the questions.
Am I audible, ma'am?
Yes, you can start.
Hello, everyone. In this poster, I will discuss our recent work in which we have studied spin pumping in the TMD and IFE sectors. In this work, we have used 4 different TMD samples because they have different and very high spin orbit coupling strength. And to prepare our samples, we have used deposit formula thin films of various thicknesses using the magnetosputtering on the commercially purchased CVD grown TMD samples. And to study the spin pumping, we have used the ferromagnetic resonance technique. In the FMR measurement, we have shown here the raw FMR data. Here, the green curve shows the FMR data for the reference sample and the red curve for the TMD formula sample. And we fit this data with the help of equation, which is sum of the symmetric and antisymmetric low-origin function. And you can see clearly that the red curve has much higher line width as compared to the green curve, which shows that indeed the spin pumping is taking place from the ferromagnetic layer to the non-magnetic layer. And by fitting this data, we extract the line width and the resonance field, which we use for the further analysis. And in the second figure, we plot here the line width versus the frequency. And we fit it to determine the effective Gilbert damping parameter. And then we fit the frequency versus resonance field to determine the effective saturation magnetization. In the figure 1, we have shown here the effective Gilbert damping parameter versus the inverse of permeable thickness. And we fit it with the equation below to determine the spin mixing conductance. Spin mixing conductance gives the spin current that is being pumped from the ferromagnetic layer to non-magnetic layer. And in the figure 2, we plot the resultant spin mixing conductance values for different monolayer TMD samples. And we can clearly see that the tungsten-based TMDs have much higher spin mixing conductance as compared to the molybdenum-based TMDs. It is because that the tungsten-based TMDs have much higher spin orbit coupling strength, which can be seen from the insert of figure 2, in it which we have plotted the spin splitting values for different TMD samples. And we can clearly see that the spin splitting values and the spin mixing conductance value both follow the same trend. And from this, we can conclude that we can regulate the spin pumping from the ferromagnetic layer to non-magnetic layer by varying the strength of spin orbit coupling of the non-magnetic layer.
Finally, I would like to gratefully acknowledge the facilities provided by the Department of Physics, IIT Delhi, and the nanoscale research facilities of the IIT Delhi. And I also acknowledge the CSIR for the providing me the junior research fellowship. Thank you. Hello.
I think all the examiners who are looking into the posters are not there, so probably we'll wait for 5 to 10 minutes.
Hello everyone. This is Dr. Muduli, the convener of the Spintronics Symposium. So there is one more session going on. So maybe we'll start the posters. Am I audible?
Yes, sir. You are audible.
Now you are audible. You are not audible, sir.
Hello?
Yes, sir. You are audible now.
Okay. So I think we'll once that last talk in that session is finished, then all the examiners can join the session. And after that, I think we will ask every student to speak about their poster, maybe 2-3 minutes each.
Okay, sir.
Okay.
Hey Pankhudi,
Yes.
मैं उपासना. Hi. So we have trained a spiky neural network in two modes. The first is complete learning method and selects the property in your isolated.
Upasana, mute yourself.
The mute
Nee, but when you are practicing to talk, everybody can hear it right now. म्यूट नहीं है उसमें क्लिक करोगे तो म्यूट होगा वो ग्रीन जो है उसमें क्लिक करो देन ओनली टू गेट म्यूटेड
Okay.
Still not muted.
But सर यहाँ पे म्यूट शो चल रहा है showing muted.
Hello, everyone. Can you people hear me?
Yes, sir.
Okay, I think we should start. Actually, it's because previous session got extended a bit. So I think what you'll do is that we'll start presenting one by one. Maybe each student should not take more than 2 minutes or maximum 3 minutes, let's say. And so that there are examiners who are actually listening. So if there is any question, they will ask.
Okay, so the first speaker is Himanshu. So Himanshu, you can start. Himanshu, are you there?
Yes, can you hear me?
Yes, you can start.
Okay.
Professor
Hello,
Rahul
everyone.
Mishra and Devanjan Bhamik, are you online?
Yeah, I'm online.
Thank you for joining.
Sure, sure.
Okay, Pintu will shortly join. But I think we can start.
So good afternoon, everyone. And in this photo session, I will be discussing our recent work in which we have studied spin pumping in TMD and IP structures. In this work, we have used 4 different TMD materials because they have different and very high spin orbit coupling strengths. To prepare our sample, we have deposited the permanent thin films of various thicknesses using magnetron sputtering on the commercially purchased CVD ground monolar TMD samples. And to study the spin pumping, we have used the ferromagnetic resonance technique. And here in the small measurement, we have shown the row of data. For the green curve shows the data for the reference sample, and the red curve shows data for the TMD permanent sample. And you can see that the line width of the red curve, which is the TMD permanent sample, is much higher as compared to its reference sample, which shows that the spin pumping is indeed taking place from the ferromagnetic layer to TMD layer. And we fit this data with the help of equation, which is sum of the symmetric and the antisymmetric Lorentzian function. And the fitting to determine the line width and the resonance width, which we use for the further analysis of the data. And by plotting the line width versus the RF frequency, we fit it with the linear equation to determine the effective Gilbert damping parameter. And next, we use the RF frequency versus resonance field curve to determine the saturation magnetization by fitting it with the help of Peters equation. And we use the effective Gilbert damping parameter with the inverse of permeable thickness, and we plot this in the figure 1, and we fit this data with the help of the equation below. And from it, we determine the spin mixing conductance, which gives the spin current that is being formed from the ferromagnetic permolar layer to the non-magnetic TMD layer. And the result spin mixing conductance values are plotted in the figure 2 for various monolayer TMD samples. And we can clearly see that the tungsten-based TMDs, WS2 and WSE2, have much higher spin mixing conductance values as compared to the molybdenum-based TMDs. And this is because of the very high spin orbit coupling strength of the tungsten-based TMDs, and which we can see from the insert of figure 2, in which we have plotted the spin splitting values for the various TMD materials. And you can see that spin splitting values as well as the spin conductance values follow the same trend, which we can conclude that we can regulate the spin pumping from the ferromagnetic layer to non-magnetic layers with the help of the by varying the spin orbit coupling strength of the TMD. Finally, I will acknowledge the facilities provided by the Department of Physics and the nanoscale research facilities at the IIT Delhi. And I also acknowledge the CSIR for providing the junior research facilities. Thank you everyone for the kind attention.
Hi, Himanshu.
Hello, sir.
Have you measured this spin orbit strength for these materials, or from the literature you are saying?
These are theoretical spin splitting values, sir, from the literature.
Okay. No, but you mentioned that the spin mixing conductance is proportional to the spin orbit coupling strength. So have you measured the spin orbit coupling strength, or from the literature you are saying?
We are seeing from the literature, sir.
Oh. But does it vary by the same order, or is it different?
Like the still mixing conductance is 3 times Icee. So the difference in SOC strength is also same, approximately.
Please could you please repeat your question, sir? I could not understand.
Like the spin mixing conductance is 3 times, right, between MOS2 and the tungsten-based TMDs.
Yes, sir.
So the ratio for the spin orbit coupling strength, is it the same ratio? 1:3, or I mean, or is it different? Like,
Yes, sir. It is almost the same, slightly less, but it's almost the same.
okay. Okay. Yeah, but it would be a good idea to maybe investigate the SOC strength on these TMDs also. Yeah. Yeah. Thanks. Good talk.
So the next speaker is Somiru.
Hello, audible?
Yes, Somiru, you are audible.
See my screen? Okay.
Yes. Yes.
I'm Somiru Bhait, and I'm going to present my work entitled as Temperature Dependent Magnetic Resistance in Polycrystalline Permanently Thin Film. So the study of magnetic resistance continues to be one of the exciting research topic owing to its application in magnetic sensors and MRAMs. So magnetic resistance is basically the change in resistance of a material when it's subjected to a magnetic field. Now this magnetic resistance is manifest of different kind of scattering process that occurs in a material. Now these all scattering process are different in nature and dominates in different temperature region. To understand this scattering contributions, which basically responsible for MR, we have performed a temperature dependent resistivity and magnetic resistance study on a pulse DC sputtered NIF thin film. So the structural study reveals that it's polycrystalline nature with a finite presence of ordering with a very low surface roughness of 0.5 nanometer. The temperature dependent resistivity studies performed over the temperature range of 25 to 300 Kelvin, and this data is fitted with the Boltzmann law to find out the exponent which actually indicate the different scattering mechanism that are happening. So below 250 Kelvin, the exponent is nearly equal to 2, which indicate that electromagnetic scattering and imperiodic scattering is present, is dominant. But however, at high temperature range, there is T greater than 250 Kelvin, N is equals to 1, which nearly equals to 1, which suggests that the electron photon scattering is dominance over the other scattering contributions. The temperature dependent magnetic resistance study reveals that the magnitude of MR is reducing from 0.97% to 0.51% when the measurement temperature is increased from 30 Kelvin to 300 Kelvin. This reduction in MR percentage with the temperature is basically due to the enhanced photon scattering and less ordering influence of magnetic field at higher temperature, measurement temperature. So first study will help to understand the different scattering which is responsible for MR in a single layer NIF thin film. Thank you.
Hi, Somiru.
Yes, sir.
Hi. Yeah, so this NIF is deposited using some special technique, like from the poster I see it's normal sputtering, right?
Yes, it's a pulse DC sputter.
Okay. Because this NIF is a well-studied system, I think even MR deposed. So I could not really catch what is the new thing you are trying to do. I mean, can you please explain it a bit?
The new thing is to try like MR, the MR can be divided into many parts in low temperature. higher temperature region, the contributions of MR are different. So basically, using a temperature-dependent resistivity study and magnetoresistance study, we want to classify the fact that in which temperature, which contributions is responsible MR. That's the initial motto of this work.
Oh, okay. Yeah, I got it. Okay, thanks.
Okay, thank you, Somiru. So
Hello.
the next speaker is Ajit Kumar Sahu.
Hello. Am I
Yes,
audible to
Ajit.
everybody?
Yes,
Yeah.
yes, you are audible.
Okay. Let me. So you can also see my screen, right? Am I correct? Hello.
Yes, we are able to see your screen.
Okay. So good afternoon, everyone. So my name is Ajit Kumar Sahu. So this presentation entitled on investigation of amorphous amorphous ferrimagnetic bilayer system for Scorpion device application. So the idea of the poster is, so we take two bilayer system. One is TBFO system, TBCO system. Another is GDFO system, which are both ferrimagnetic system and amorphous in nature. If you see the internal magnetization structure, which is not in well order, which is disorder in nature, but the resultant of the magnetic moments are anti-parallel to each other. That means rare earth, if it will be in this direction, transition metal will be in other direction. So this anti-ferromagnetically coupled, so the net moment will give towards the rare earth moment. So if you couple these two moments, the two system, the GTFE and TBCO system, so as we see the internal magnetization, which is not in well order, so it is a local it's local anisotropy, which is not equivalent in the local environment. So that may be the reason giving the canting in the spin system. So we add two system in micromagnetically, and we see there are various kind of spin textures available in the range of the two bilayer system. We can see the TBCO system and GTFE system. We have varied from 0 to 100 nanometer. Here also TBCO 0 to 100 nanometer. We see various kind of magnetic texture, just like here the lower thickness of GTFE, we see the vortex kind of signature, and in higher thickness we see the chiral stripes and nil scorpionic nature. And to further understand, so we have taken two examples, which is one is lower one, which is vortex signature. Another is one example of vortex. One is nil scorpion and chiral stripes. We can see here. So this system, this example is somewhere this one. That means TBCO 6 nanometer, GDFE 30 nanometer. That means bottom one is less nanometer, which is 6 nanometer. Upper one GDFE is 30 nanometer. We see the static. We see the ground state of the system, which is vortex in nature, and we can see the hysteresis is something like this. And we can also investigate if the thickness of two layer is just exchange, and that means the TBCO is 30 nanometer and GTFE is 6 nanometer. We see the ground state is something like nil scorpion as well as the chirality in the domain structure. And to further understand, so we have done sub-layer modeling with the layer result modeling. So this shows, so as we know, the rare earth transition metal system, which gives the spin reorientation effect as we increase the thickness. That means the lower thickness we see the in plane. When we increase the thickness of the sample or the thickness of the film, we see the spins are transit from in plane to outer plane. That is the meaning of spin reorientation effect. So we have taken one example, which is here TBFE 30 nanometer, GTFE 20 nanometer. Then we divide into equally layers. That means TBFE here 3 sub layers, 10 nanometer, 10 nanometer, 10 nanometer. GTFE here 2, 10 and 10. That means 30 nanometer of TBFE, 20 nanometer of GTFE. So as you see here, 30 nanometer and 6 nanometer, when TBCO, that means hard magnetic in nature, is 30 nanometer, we see the ground state is nil Skyrmion. So then you simulate this one, we see the ground state also shows similar behavior to this system. That means, so the main motto was to understand the Skyrmionic nature present in the system. So we understand by doing sublayer modeling or the layer result modeling, so the Skyrmion nature, the Skyrmion texture exists in the system. So finally my conclusion is, we can also investigate the Skyrmionic textures or the Skyrmionic spin textures in bilayer system without presence of any heavy metal system, which basically gives the DMI in the system. So the DMI basically comes here with the inherent property due to the random arrangement of the speed moments. So this is all about my poster presentation. Thank you. Hello.
Yeah, hi Ajit.
Yes, sir.
In this different file layer, I see 3 TBCO layer and 2 GDFE layer. What exactly did you change from layer to layer? It's not clear.
Yeah,
Can you
so
explain that part?
so the idea was to investigate the origin of the canting takes place in this amorphous system. What we have done, as we are seeing, the TVFE should be higher thickness and GDFE should be lower thickness. Then only we see the something in this region. That means the Skyrmionic nature exists in this system. So then what we have done, the TBFE, this is just one example. So TBFE we have divided into 3 sub layers. Then what happens here, we have taken the parameter. Here we can see the TBFE parameter is something 2 times 10 power 6 joule per meter cube. Then what we have done, we have divided 2 to 3 layers. That means if this whole layer is 30 nanometer, we have divided 10 nanometer, 10 nanometer, 10 nanometer. Similarly, A, K, and MS, which is the material parameter, we also divided into 3 3 equal times. So it's like 3 divided by 1. So this will be 1 times 10 power 6. This parameter will be same and this parameter same. So only changes occurs is angle. So this angle, this you can see this whole layer.
No, I did not understand. What is the meaning of divide? Divide.
So okay, so in
you are
general,
varying MS or you are varying KU. Is that what you want to say?
Yes. So the idea of division is when we do a deposition of the sample in the any sputtering mechanism or any deposition technique. What we see at the lower thickness, we see the in-plane sample. Increase the sample thickness, we see the magnetic moment orient towards the out of plane direction. That means so we see a spin reorientation occurs from in plane to out of plane. So we have imagined one layer, then we divide to 3 sub layers. That means it's in sputtering also we see a layer by layer deposition occurs. So that idea we brought here. Then the division of parameter values are something like in 3 equal values. If this will be,
maybe I can ask you later. That's okay.
Okay, sir.
Thank you.
Okay, sir. Thank you.
Okay, so we are running out of time, so make sure you'll finish back in 2 minutes. So the next speaker is Miss Shilpi Bose. Shilpi, are you there? Shilpi, are you there? So then we can move to next one, Mr. Lalit Pandey.
Pankuri, I think Shilpi is presenting something. I see a screen.
Sir, this is something I have shared. I shared Shilpi's poster.
Okay.
So if Shilpi is not there, then we can move to Mr. Lalit Pandey.
Hello.
Lalit, are you there? Yes. Yes, Lalit, we
Yeah.
can hear you.
Okay. Can you see my screen? Hello?
Hello, yes, Lalit. You,
Can you see my screen?
you can make it full screen and then start.
So, good
Yes, you
afternoon.
can start.
Good afternoon, everyone. I'm very fine. I'm PhD scholar in DFL lab, and this is the recent work that I have done, entitled as optimizing the stoichiometry and topological discrete telluride thin film using DC magnetron co-scattering. So, as you already know, topological insulator are new emerging quantum material.
Lalit, can you come a little closer to your microphone, please? We can't hear you properly.
Okay. Now you can hear me.
Yes, better. Please go ahead.
So topological insulator are new emerging quantum material having some exotic properties which are beneficial for spintronics and semiconductor based application. So however, it is very challenging to synthesize this material using industry friendly technique like sputtering, as at least one of the compound element in this type of compound is uh, so it is very challenging to synthesize this using uh, these techniques. So, but to overcome this obstacle, we have used here a 4-gun DC magnetron co-sputtering. So, to use co-sputtering, we have used this formula. Initially, we first optimized individually a bismuth and tellurium target. Optimize bismuth and tellurium of bismuth telluride, and then further to optimize to study the structure and phase analysis, we have used XRD and Raman measurements, and using analysis, and we have find that surface morphology and grain size highly influenced by this tellurium partial pressure, and now in future we will do transport measurement in this film, and we will make hydrostructure of this metal film with ferromagnetic uh, ferromagnets to study transport and dynamic properties. So, thank you. Hello.
Hi, Lalit.
Hi. Hello, sir.
So have you confirmed that this is really a topological insulator, like
No.
from, or it's in your future plan?
Yeah,
With
it is
electrical measurement.
by using transport measurement. I will confirm.
Okay. Yeah. Then it makes sense. Yeah, because else it can be just alloy, just a mixture of two.
Yes, sir.
Okay. Thank you.
Thank. Can I ask a few questions here? Who is this? Hello.
Yes.
Yeah, I'm Debanjan. Yeah. Can you hear me?
Yeah. Yes, sir.
So can you just tell me? So what is so what evidence do you have of this being a topological insulator?
No, there is no evidence. Actually, optimizing the stoichiometry is very challenging task using this sputtering instrument. So these were our initial like step to optimize this, because as you know, the little bit of tellurium deficiency can change
like topological property or trivial and non-trivial properties. So our initial motivation was to optimize that bismuth tellurium exact document.
टोपोलॉजिकल का कोई एविडेंस नहीं है.
No sir.
कुछ एविडेंस नहीं है at this moment.
No sir.
Well, how do you plan to get an evidence if it's topological or not?
Yes sir, we will perform transport measurements like
What kind of measurement? Topological Hall effect.
not topological Hall effect sir,
And?
like from weak anti-localization effect like MR measurements or like oscillation in MR we can confirm whether it's a trivial or non-trivial.
SDH oscillation.
Yes sir, correct.
So Ratnamala madam does also similar work, no?
Yes sir, but she has used a single crystal of bismuth tellurium. She has make a bulk.
Oh, while
Yes,
you
sir.
people are growing it.
Yes sir,
You are doing sputtering.
Yes sir, we are using sputtering and then we are planning to make a heterostructure.
So this is not single crystal. Her one is a single crystal. She took a crystal or she grew it.
So he grew
Hello?
single crystal. Yes sir.
Hello?
So these film are
Hello?
also. Hello? Yes sir. Hello?
Hello?
Am I audible? Hello?
Yeah, I can hear you.
Yes, Lalit.
Hello Devanjan sir. Can you repeat your question? Maybe he's disconnected.
No. I think my connection just goes off for WebEx. Teams, I never have a problem. But with WebEx, something happens all the time. Hello?
Yes sir. Yes sir. Can you repeat?
But for whatever reason, WebEx, I just keep getting disconnected all the time. Teams, I've never had any problem. So my simple question is this: that okay, the third one is co-sputtering, so it is polycrystalline.
Yes sir. It's not. It's highly oriented. I can say if you can see my XRD pattern, you can
Okay.
see here only one families of planar visual.
Okay.
So
Chalo,
yeah,
theek hai.
epitaxial film I also like have to do reciprocal space mapping and all those things. These
All right.
are future plan. Okay,
Okay,
thank
let's
you.
move on to the next slide. Next person.
Okay, thank you, Lalit. So the next speaker is Dr. Sagrika Nayak. Dr. Sagrika Nayak, are you there?
Hello, sir. Hello. Hello.
Hello. Yes, ma'am. Yes, ma'am. You're audible.
Madam, can you please give me 5 minutes? Can you?
We can move to next speaker.
Yes. Huh. After that, I will join.
Okay. So the next speaker is Mr. Pushpendra Gupta. So, Mr. Pushpendra Gupta, are you there? I think I cannot see him in the chat, in the participant list. So we can move to Mr. Vidnandan Ojha.
Hello, ma'am.
Yes. Hello.
Okay, myself Bindavan Oja.
Okay. So you can start.
Yeah, just 1 minute.
Someone is typing. I think you should mute yourself.
Yeah, my screen is visible.
Yes.
Hello.
Yes, your screen is visible. Yes, you can start.
Okay. Myself Brindavan Oja. So I am from Niger, Bhubaneswar, and my title of my poster is thickness dependent study of Jalison-Moria interaction in platinum cobalt iron boron bilayer. First I will give some introduction. The Jalison-Moria interaction is an anti-symmetric interaction, and in thin film it arises at the interface between heavy metal and ferromagnet, and this heavy metal should have the last spin orbit coupling. the Alscoria interaction when the interaction value is greater than some critical value, critical DMI value, and it can stabilize the vortex-like spin texture, otherwise Kariman or chiral domain, depending upon the value of the DMI. And next, this is my sample structure. Here I have taken the tantalum, platinum, cobalt, angioin, tantalum heterostructure, where the cobalt thickness varied from 1.1 nanometer to 1.9 nanometer. And the motivation of taking the cobalt boron is that as cobalt boron has less spinning side and low damping material, so it is very useful for dynamic study, and it is for dynamic study. And for experimental details, I have deposited my film using DC sputtering and EV sputtering, and I have measured the hysteresis measurement, and basically the saturation magnetization, and using more using squid, and the domain images basically I have did using car microscopy and the magnetic force microscopy. And I have quantified the IDMI value using Brillouin light spectroscopy BLS measurement. So here it is squid measurement. For my sample, this is from 1.1 to 1.6 nanometer sample. I have got the outer plane hysteresis loop, means the EG axis is here out of along outer plane direction, and from 1.7 to 1.9 thickness, cobalt thickness, I have got the EG axis of sample is from in plane direction. So if I see from 1.1 to 1.6 nanometer, if we see that, then we can see that around 1.6 the magnetization switching from in plane to outer plane, means this is near SRT. And we have also performed the squid measurement, and we have found that we have found the dead layer thickness around 0.4 nanometer, and the and saturation magnetization around 1578 EME per cc. And so we have performed the MFM in the outer plane, mean 1.1 and 1.2 nanometer. We have observed the bubble domain, although I have not shown here this picture, but in the near SRT sample, that means 1.5 and 1.6 nanometer sample. In 1.5 nanometer sample, we have observed zero fields carbon. This is a little bit distorted, but in one little bit distorted. But for 1.6 nanometer sample, we observed Ulm-Life domain at demand tested, but when we applied a 3 mil-Tesla outer plane field, we have observed a isolated skyrmion here. Next, we have used the BLS measurement to quantify this IDMI, and here in case of BLS, a photon light is incident on the sample, and the photon due to phonon magnon photon interaction, the Stokes and anti-Stokes line created, and from the frequency difference of the Stokes and anti-Stokes line, the IDMI constant can be quantified. And the right hand side, I can show here the BLS spectra, and here we have shown the Stokes and anti-Stokes line, and the from the and I have plotted the delta F versus wave vector, and from the slope of this wave vector, I can quantify the D. And in my case, the DMI value varied from 0.43 to 0.56 millijoule per meter square. And also we have plotted this DMI value with thickness, inverse thickness of the cobalt iron, and we have seen that the first for higher thickness of cobalt iron, it is linearly proportional of the DF of the D with the D effective, but for a higher lower thickness, it is not proportional. It is little bit deflected, at maybe due to the intermixing it may happen. And the conclusion of my talk is that we have observed the dead layer thickness around 0.4 nanometer, and also we have stabilized the scarmion, zero split carbon, by tuning the ferromagnetic thickness only, and we have quantified the IDMI value in our platinum cobalt iron boron system. And I am acknowledge the authors should acknowledged to DAE, DST, ACRB, and CEPIPRA project to give me the opportunity, and to uh, give some funding for this measurement and all these things. Thank you.
Yeah, hi Brindavan.
Yes, sir.
So, how did you confirm the skyrmion in this?
Hello. Sir,
Hello.
basically, sir, in platinum cobalt iron bond system, this is it is not first time I have did. It is already established in this kind of heavy metal. This kind of structure we can get skyrmion, and also, sir, using MFM when we are getting this kind of structure, and we all for current induced dynamics also will do. And if we see that using applying current, it is moving along the current direction, then we can surely say that it is skyrmion. If it is domain bubble domain kind of thing, it will not move, it will shrink, otherwise it will increase in size, it will not move.
Okay. So your this MFM measurements you are talking about skyrmions from this
Yes,
MFM.
yes.
Okay.
Okay, thank you, Vrindavan. So the next speaker is Mr. Shakti Ranjan Mohanty. Mr. Shakti Ranjan Mohanty, are you there? I think.
Hello. Yes, ma'am. Am I audible?
Yes, you are audible.
Oh, okay.
Okay.
So,
You can see your screen. You can start
yes.
presenting.
Yes. So, topic of my poster is effect of iridium spacer layer on cobalt platinum synthetic antiferromagnetic of cobalt platinum layers. So, when two ferromagnetic layers are separated by a non-magnetic spacer, then depending on the thickness of the spacer layer, the two ferromagnetic layers are aligned either parallelly or antiparallelly. So if parallel alignment is there, we can say that these are synthetic ferromagnets, or if antiparallel alignments among the magnetization is there, then we can say that is the synthetic antiferromagnet. So that is happening through indirect exchange interaction, that is archic interaction. And in this work, I have prepared synthetic antiferromagnetic samples by taking cobalt platinum multilayer, and in between the two cobalt layers, I have taken iridium as a spacer layer. I have prepared all the films using DC sputtering system in our lab, and measured its magnetization properties using core microscopy and squid magnetometer. So the sample structure is here as shown. I have taken tantalum as a sealer, then platinum cobalt. Either in below the iridium spacer layer, I have taken either two layers of platinum cobalt or one. Similarly, above the iridium spacer layer, I have taken either two or one. Here, all the sample structures are written. So here in this work, I have only shown only the samples with antiferromagnetic coupling, which I have got only antiferromagnetic coupling. This is iridium, and this sample is with iridium thickness 0.5 nanometer between and cobalt. My cobalt thickness is 0.8 nanometer, which provides in combination with platinum 3.5 nanometer, it provides a perpendicular magnetic anisotropy. This is this is below the iridium layer, and then there are two cobalt platinum layer, and above the iridium layer there is one cobalt layer. Similarly, here also below the iridium layer there are two cobalt platinum layer, and above there is one. But the difference is here the iridium thickness is 1.5 nanometer. And here we have got strong interlayer exchange coupling, that is antiferromagnetic interlayer exchange coupling. Similarly, this is of sample we having one cobalt platinum layer both below and above the iridium layer, and here above is 2 and below is 1, and similarly here above 2 cobalt platinum layer and below 2 cobalt platinum layer. So in this telling this, suppose this figure I am considering, when the magnetization, when the field is saturated, then all the magnetization are in same direction. But when reducing the field, one of the layer switches fast. One of the layers switches fast, and that becomes antiferromagnetically coupled. Both the layers below and above the iridium spacer layer, both the layers become antiferromagnetically coupled. Again, while decreasing the field, then at negative saturation, both the layers becomes negatively saturated, and in same direction. So in this region, basically in this region, the sample is antiferromagnetically coupled. And here we have calculated the exchange coupling energy. Basically, using this formula, Jx equal to Hex. Hex is the exchange coupling field, Ms is the saturation magnetization, and T is the thickness. That is thickness of the ferromagnetic layer. So exchange coupling field we are taking, like where the coupling is lost. Suppose we are from zero magnetic field, we are increasing the field. Then where the coupling is lost, then that point we are considering as exchange coupling field, and using that field, we are calculating the exchange coupling energy. And I have found the maximum exchange coupling energy as 0.45 or per centimeter square in the sample, having both two layers of cobalt platinum below and above the iridium layer. And these are all the domain images. In every sample we have got small bubble domains, where we have got antiferromagnetic coupling, but where we have got ferromagnetic coupling, which I have not shown in this poster. There we have got big bubble domains. So and we have successfully conclusion of my poster is we have successfully fabricated cobalt platinum synthetic antiferromagnets. First of all, we have obtained the perpendicular magnetic anisotropy, and the antiferromagnetic exchange coupling energy is we have got 0.456 or per centimeter square. I'd like to thank DAE and DST SRB and Inspire also. And I'd like to thank my supervisor, Dr. Subhankar Vedanta, for his constant cooperation. Thank you.
So, sir, if there is any question for Mr. Shaktiranjan Mohanty.
Can I ask one question to Shaktiranjan Mohanty? So I just
Yes.
wonder how much interface roughness you have observed if you vary the iridium thickness. Like
I have not that we can obtain from XRR measurement, but I have not checked for roughness of iridium. Iridium with iridium with cobalt interface. I have not checked the roughness.
Is it something? Do you think like exchange field will have a relation with dead layer as I can see maybe?
There may be magnetic dead layer, but yes, that there may be magnetic dead layer, but we have not gone through that. We have just prepared the sample and calculated its exchange coupling energy and considered the magnetic layer thickness as we have deported. So we have not considered any magnetic dead layer.
Okay.
While calculating.
And how this exchange field is varying? Is this something like RKKY coupling as you were showing on the top of your poster, which is the introduction and motivation section? Is it the same format? Because I don't see any kind of pictorial mention of your experimental data. So is it the same format or something else is showing? So you can see the energy, right? The RKKY is a sinusoidal and it decreasing at increasing the thickness, right? The spacer layer.
Yes, I understand your question. Here, actually, we need a large, means more number of samples in order to plot this curve, like in every thickness. But I have taken a limited number of samples, so my exchange coupling field is I cannot plot this curve due to limited number of samples.
Okay, okay. And the last one, so you find a AFM state, right? So antiferromagnetic state. So
Yes.
you were
I
saying
think,
you were
Mr. Ajit,
okay, okay,
can we
sure,
ask
sure,
these
sure,
questions
sure,
later because we have
sure,
yes.
sure.
So
Thank you.
if any professors want to ask some question to Shakti Ranjan Mohanty. Okay, then we move to the next speaker, Miss Upasna Sahu.
Yeah.
Okay, sir. Okay.
Yeah, let me just one real question. Shakti Ranjan, what is the purpose of growing this?
Sir, first of all, we are establishing a synthetic antiferromagnetic structure. Then we will try to host scormion in it, which will reduce the scormion Hall effect. So that work we have not done yet, but our next step is that.
Okay, fine. Thank you.
Actually, our just one announcement. So our next like the talk will start at 5 o'clock. So you have to finish the poster session exactly 5 because that is scheduled.
Okay, sir.
Hello, Samresh ji.
Go ahead. Up to 5 o'clock you can go ahead. But 5 o'clock our talk is scheduled. Invited talk.
Yeah, I think they should have created a separate link or something. Anyway, what we can probably do is just stop at 5 and then rest. We can have another discussion sometime later.
Do it today after the plenary session, evening plenary
How many
session.
more are left?
How many left? So you can do after the plenary with the same link. You can tell that after the, because we did some of the other poster like 359, right? So the same day you can do today itself after the plenary. You can ask the student to be in the same link. They can present it.
Okay.
So we are
plenary talk is up to 7
9
or
to
8?
10. 9 to 10 posters are already be there.
Yeah, it's not going to possible to finish this in the next 10 minutes because
Yes,
they
sir.
also need some time to introduce the speaker and all that. So maybe we do this is the last one we can do, and after that maybe we'll ask them to join again after the plenary in the same talk, same link.
Okay, sir. Upasna Sahu, are you there?
Yes,
You can
yes.
start.
Yes. Hello everyone. I'm going to present my work entitled as Training of a Spiky Neural Network on Spintronic based analog hardware for handwritten digit recognition. So, hey, I can't see my presentation. Am I audible?
Yes, you are
Yes,
audible,
yes.
but hide your poster. Pankuri, I
So
don't see the.
just wait. Yes, now it is visible.
Yeah. So we have trained spiky neural network in two modes. The first is completely unsupervised learning mode. Synapse follow HTTP property and neuron exhibit homeostasis property. The other mode is partially supervised learning mode. In this mode, synapse update their weight HTTP. However, partially supervised nature comes from applying biased current. So you can see in figure both the stretches are in A and B stages. And in partially supervised learning mode, during training phase, when the input belongs to particular date, no inhibitory current is applied on the post neuron allotted for that digit, but inhibitory current is applied on the other post neuron. So the knowledge of the digit each input belongs to is used in the learning phase. But in completely unsupervised learning mode, no such inhibitory current is used on post neuron at any stage. The knowledge of what digit each input belongs to is not needed at learning stage, but only for determining the accuracy. So the pre-neuron and post-neuron follow the Ricci integrated fire model, which is described by this equation, RIF equation. And for pre-neuron, threshold voltage is fixed, but for post-neuron, threshold voltage is the function of time following homeostasis property. Every time neuron spikes, threshold voltage increasing by a fixed amount of voltage to delta VTH and decay with homeostasis time constant. And pre synapse, when a pre-neuron gives output, post-neuron receives and current and changes current by this equation. Here you can see the weights, which is the weights of the synapse, which is updated by using the HTTP property. And we have implemented synapse and neurons using the current-driven domain wall motion, which is in figure 4a. When the current is passing through the heavy matter, the domain wall is moved, and when the domain wall is moved, the conductance is changed, which is change in conductance is directly proportional to the change in weight. Similar for the neuron. In neuron, when the current is going through the heavy matter, the domain wall is moved. The domain wall is moved at the end of the ferromagnet. It gives output, and when the neuron gives output. And the pre-neuron is connected to the post-neuron through synapse. The transistor-based circuit is seen in figure 6, and the result of this figure 6 is in figure 7. We have implemented it in cadence virtuoso. Now we have computed the energy consumed in the implemented the spiking training algorithm in synaptic device and the time taken it. The energy consumed per report is same for both the running. Thank you.
Hi, Upasna.
Yes, sir.
In figure 7, is there any reason why the depression and potentiation curve are not symmetric?
Okay. So, sir, for when we simulated in my mat, so for the higher accuracy, we change its parameter, and based on that parameter, it is not symmetric.
Okay. I mean, I don't understand, but maybe I later. It's okay. And one more thing, this test for figure 2, right? Normally you do test after training, right?
Yes, sir.
So the red curve is for training.
Yes, sir.
And if first point in the test curve, the accuracy is very less, even after finishing the training. So is there some reason for that? Or? Normally after you finish your training at good accuracy and once you do the test, so the accuracy or something I'm missing here.
So train sample and the test sample are different. For the train sample, we have taken the 1000 train sample, and after it, we have taken the different 100 test sample. So for that different 100 test sample, it is also required to adapt that code, that accuracy. So that's why after some epoch, then only accuracy get increases.
Mm-hmm. But train and test are, I think, of course, they are always different. That's why they are called train and test.
Yes.
But okay, it's okay. Because after you train, then you basically set the weight, right? And then with those weights, you put the test samples and then see what the accuracy is, right?
Yes.
Mm. Okay, thank you.
So probably we can stop for now, and Mudli sir can tell when we can start again.
There are a lot of background noise actually. Maybe next time you can try to announce that the noise. Okay.
The people, those who are not using, they can switch off they can mute themselves. Then only noise will come. Professor Modli, you want to announce something for this remaining poster presentation? How we are going to do? Hello?
So I think Peter is not
Professor Devanjan, do you want to have any announcement for the remaining poster?
No, I mean, how many posters are left?
Around 9 posters are remaining.
Around 9 posters. So where?
Yes. So then maybe we can restart it when this plenary talks are over. I mean, this session talks are over, then we can restart it. If all the committee members are free.
Online, so we can just go till midnight also if needed. Huh? Chalo, do that.
Plenary will be ending at 7:30. So after that, you can continue.
Oh, no. I think actually we are all having a very long day today, and there's a bunch of IOE proposals and all that going on in our department. I mean, how about this? Whoever can join, and maybe so can I access these posters somewhere?
Yes, you can accept a letter, you can give the marks also. But we can finish the presentation today itself because tomorrow
Yeah,
we lose
the presentation. If I can join, I will join. If I don't join, I will not join. But I can access to all these pictures somewhere.
Yes, you can access. Like you just log in to the website and then you can see the poster.
Bas, okay. That's good enough then. I will take a look there only. You people continue with the call then at 7:30.
Yes, so Pankuni, you can contact this on the 7:30. Okay, then all the student, all the presenter for this spin Semiconductor, you can join at 7:30 in the same link. Okay. Now we are starting the next session. So
okay, sir.
बंद कर दे क्या?
So hello. Hello. So already Professor Rashli is here and Professor Mukesh Kumar also here. So this is the last session of the today's 2D materials and devices. We are having very exciting talk from Professor Rashli, and for this session chair, I'm requesting Professor Mukesh Kumar from IIT Roopar. So Professor Mukesh Kumar is in Physics Department, IIT Roopar. He mainly works on the functional materials and optoelectronics devices. He has many awards from Young Scientist DAE and DAE Young Achiever Awards, also in Institute. So I'm not going all those three, but I'm requesting Professor Mukesh Kumar for chairing this session. And hello, Professor Mukesh Kumar, are you here?
Yeah. Good evening.
Good evening. So now I'll stop sharing. So Professor Vasli is here. You can take over. Okay, thank you.
Okay, thank you very much. Good evening, everyone. Welcome to this session. We have one invited talk in this session by Professor Vasily Provenos. I hope I pronounced the name correctly. So Professor Vasily actually is a professor of electric engineering department at University of Buffalo. And he joined University of Buffalo in 2018 from faculty at Skoltech, Moscow, Russia, where he was about 11 years. And he was also spent some time at IBM TJ Watson, New York. Okay, and like he has received three times highly competitive IBM Research Technical Accomplishment Award in 2005, 2006, and 2008. Professor Vivno's research and teaching interests are in the area of advanced materials and nanostructures for electronic and optoelectronic, especially for one-dimensional carbon nanostructures, novel 2D materials. He is an author and co-author for more than 80 research articles, 1 book chapter and 2 review articles, and 1 US patent. So, Professor Vasily, looking for your interesting talk. So, over to you.
Very much for the introduction and for the opportunity to present our work and invitations. Really a nice conference. I enjoy it. So I will talk today about optical spectra of 2D semiconductor materials due to the many body effects. And as you know, electron hole pairs, they bind, and in 3 dimensions, the binding energy follows like a Rydberg series with the binding energy renormalized from the hydrogen molecule to the bulk values by the effective mass and the electric constant. And so this is a very a small binding energy. So typically you don't observe at room temperature excitons in 3D materials. But as you reduce dimensionality, the binding energy increases. And in particular, in 2D materials, we know that this binding energy is large. And in order to describe it, you need to include those many-body correlations. And one of the features, you can see that in low dimensions, the spectral weight of the excitons is getting much larger than in the bulk materials. So with this, we can show that excitons, when the optical properties were discovered, the direct bandgap semiconductor and 2D materials, then it was shown that excitons dominate the spectrum. And as you change the number of layers, you change the optical properties, the direct bandgap material becomes indirect, and also as a function of layers, you can change the spectrum. So if you want to use those low-dimensional materials for practical applications, such as photodetectors, you need to separate electrons and holes. And because the binding energy is large, you need to apply some external electric field, which would separate electrons and holes. And to describe that interactions, we adopt the density function theory calculations for the band structure. And then we apply electric field in a tight binding model. And this allows us to see a stack shift and also ionization after ionization of the excitons. So the way we describe electron-hole pairs, we start with the Hamiltonian, which has a single particle kinetic energy term. It has a Coulomb potential between electrons and holes, and we take it using the Keldysh potential shown here. So there is a parameter I0 which tells about the screening of the Coulomb interactions, and of course 1 over Q is just a two-dimensional fully transform of the Coulomb potential 2D. So what's important here is that after you solve that two-body problem, you can calculate the spectrum, which is omega, and the wave functions of the excitons. And the wave functions of the excitons allows you to calculate the optical spectrum. And I should note here that the state-of-the-art approach is HW calculations when this Hamiltonian is solved in the basis of the first principle wave functions. But we are doing it in a tight binding model, so we have a much more efficient way to solve this problem. So in particular, the solution can look like this. So you start with the density function theory band structure. Then you fit it to the tight binding model. So you get essentially exact fit. And then you add Coulomb interactions. And then you can calculate the absorption spectrum with the A, B excitons, high Rydberg states, and so on. And after you apply electric field, you break the symmetry and you separate electrons and holes. So you can actually plot the wave functions in 2 dimensions. So the hole is centered in the middle. And if you plot the distribution of the wave functions, you can see that it's distorted. And that distortion leads to the Franz-Keldysh oscillations in the absorption spectrum. So you see this is the main peak, and then this is a replica, which take place in the high electric field. And what's more interesting is that you see the natural broadening of the exciton wave function. So this broadening translates to the after ionization rate of about 0.3 picosecond for those parameters, of course. The higher the field, the broader the spectrum, and the larger the ionization potential, ionization rate. So this tells you, and you can also change it by the electric environment after you introduce the electric constant of the environment, which screens the electron-hole interactions. And then your binding energy gets smaller, and it's easy to ionize the exciton. Of course, when you fabricate those materials, you have some unintentional doping, or you can control doping by the gate. So if you build a field effect transistor and you change the gate voltage, which changes carrier density in MOS2, you can see that the spectrum is going to change. And one of the features which you observe that the extra peak appears at high doping, and that extra peak is assigned to the trions. So the trion is a particle which contains two electrons, let's say, and one hole. And this extra electron is bound to the electron-hole pair, to the exciton. And now to describe it, you need to solve a three-body problem, which is much more intense. And in general, it is very difficult to model electron-hole interactions.
Just wait, Professor Wesley. So some people are not muted. Mohammed Saeed, please mute all the participants. Please mute it. Those who are not using talking, please mute yourself.
Yeah, okay. Thank you. So the way we deal with that many-body problem is the following. So to write, so we are solving the three-body particle problem. So we have a kinetic energy as before. This is just the sum of the electron and hole, two electron and one hole, which is shown by here. V is a hole, C is electron. And we have a Coulomb interactions between those three particles. It can be broken down into three different terms, which is not as important. What is important is that to model the doping, now what we are doing, we are changing the number of K points in the supercell, which gives our basis of functions, right? So this B, C, and C, this is wave functions calculated on the K points in the Boolean zone shown here. So it's M point to K points. And as you change the number of sampling, you change the size of those little squares, little rhombs. And as a result, this discretization leads to the level spacing, which is shown here. So this is, let's say, a parabola. And as you change the discretization, shown on the right, the n squared, this is the, let's say, 36 by 36 K point. So the distance between the K point to the first point in the Brilliant zone would translate to energy of 30 millieV. As you increase the number of K points, this lowest energy becomes smaller and smaller and smaller, and the E limit of the infinite number of K points, the energy of the point next to the K would go to zero. Of course, we cannot afford very high number of K points, but up to 100, you already can cover the range of doping levels which people use in the experiment. So usually in the previous case, when you deal with excitons, the number of K points tells you about convergence. So the higher the number of K points, the more you are converged. And we check that the exciton is converged by the time the number of K points is 36 by 36. So that doping level, so if you try to reduce the number of K points further, then we would run into convergence issues. But for that range, the convergence would be fine. But by changing the doping level, we essentially model the Fermi level change, right? Because we can put an electron only here. We cannot fill the states below. So what happens as a result of that solution, that we can calculate optical spectrum as before, because we know the wave functions, and we can calculate the absorption spectrum. And this is how the results would look like. So before we solve the Becker-Salpeter equations, it gives us a single peak. And as you solve the three-body problem, then you start to see multiple peaks. And by the way, the relative absorption is the same because in two calculations. And you can see that the spectral weight is shared between the exciton to the trion. So the extra peak at about 200 milliV EPS, and that extra peak is separated by certain distance, which depends on the key points or which depends on the doping level, like in our case. And then there is a new feature. You see an extra peak, which we ascribe to the valley exciton. And so once we benchmark this approach to the calculations, then we can actually see what's going to happen. So we change the Fermi level and we calculate the absorption spectrum. And you can see that the exciton increases in energy. So this is a well-known fact that if you're in a single particle picture, if you start to fill the band, then you cannot create an electron-hole pair with energy less than band gap plus E Fermi. So your energy would increase proportional to E Fermi. So the similar effect is shown here, except for now we also include the correlations. And this is a trion. So its oscillator strength grows as you increase doping. So the higher doping level, the more oscillator strength goes to the exciton. And what is interesting is that there is a new spectral feature EPS in between the exciton peak and trion peak, and that extra feature we interpret as a intervalley exciton, because we can also look into wave functions from our calculations, and we know exactly what kind of spectrum we deal. So this is the wave functions. So again, you can look into distribution of electrons and holes in this three-particle picture. And for example, the trion, as people usually describe it, this contains of two electrons in valley K and K prime, and the hole is sitting in one of the waves. So this can recombine radiatively, this electron and hole, and give rise to the bright trion state. Exciton is when you have an electron and hole in single valley, and the second hole is delocalized in the second valley. So the size of that radius tells you the degree of delocalization. So the larger the radius, the more delocalized state is. And this new feature, which is in between of the two peaks, we ascribe to the intervalley exciton because one of the electrons is sitting, localized electron is sitting in the other valley than the localized hole, and they cannot decay radiatively because there is a large momentum transfer between the two valleys. But of course, the second hole is sitting in the first valley, same valley as the hole, and those two can recombine. And as you increase the doping level, you have a higher and higher degree of delocalization, and you can actually easily recombine. You build this dipole matrix set. Okay, so this can be shown that explains why we saw brightening of that nominally dark state. So if you want to see the doping dependence, which is essentially the experimental signature for those trions and excitons, then we can nicely reproduce the observed level splitting between the exciton and the trion. This is taken from experiment with the points, and this line is the data from our calculations, and you can see that they match each other. And so what we theoretically predict the indirect exciton, it would follow the same trend. Of course, at low doping level, there would be smaller shift. But that nominal shift is this proportionality to the Fermi level. This kind of effect you can obtain even in single particle picture. Except for here, deviations from that straight line are due to the correlations which are included in our model. And so you can see in more details when you put a transition energy as a function of the doping level, you can see that those dashed curves, those are calculations of the beta salpeter equations for the two-particle picture. And as you change the doping level, as you change the number of key points, nothing happens because you're already converged. But the trion wave functions, the trion spectrum is changing. The trion goes down in energy with higher doping, exciton goes up, and the new feature, the spectral feature which we predict, intervalley exciton, actually lies in between. It has a small doping dependence, but the oscillator strength grows, and the higher the doping level, the larger the spectral feature of that intervalley exciton. So this is a more detailed spectrum figure of the oscillator strength dependence on the Fermi level. And so conventional exciton is shown here. It loses its oscillator strength. As you increase the doping level, the oscillator strength of the exciton is shared between the other states. So it has to go down. So if you add all the oscillator strengths for each doping level, they sum up to this orange line, which is essentially independent of doping and coincides with the beta salpeter equations for the excitons. But as in a trion picture, this oscillator strength is shared, and it's interesting that this new exciton, which is nominally dark, is brighter at the Fermi level, which are easily achievable in the experiment. This is our prediction. Of course, you can manipulate the optical properties of the excitons by changing the dielectric constant, so you increase the screening, so your binding energy reduces, as usual. And you can actually compare our results with the variational approach. So this is what people usually use to describe the trion. It doesn't give you oscillator strength, but it gives you the energy. And we can see that energy actually not too bad. It follows our predictions. But of course, if you change the doping level, that variational approach would give you different result. So basically, you can change the doping level, and you see stronger and stronger deviations from the variational approach. Now, so in this case, we sort of verified that variational approach is okay to use in a low doping level, but of course, at the higher dopings, you shown here by 10 millieV, 5 millieV, you can see different interplay of the oscillator strengths between the conventional exciton and the trion, and this newly predicted intervalley exciton. So as you reduce the doping level, of course, we no longer observe the intervalley exciton, but the predictions for the oscillator strength, which is shared between exciton and the trion, is going to change. So actually, the higher the dielectric constants, the more the brighter the trion becomes. Actually, so it has a larger oscillator strength relative to the exciton. So now I changed the subject and I talked about photoluminescence. So when you shine light, you create electron hole pairs, then they relax to the bottom of the gap and they illuminate. And so this luminescence has temperature dependence, has been measured already, and people see that there is a shift of the peak and the broadening of the peak. And so we explain this effect by our calculations. It's also due to the dispersion of the trions. And so the calculations are set up as the following. We solve this many-body problem, we get the wave functions, but now we assume that before luminescence, those states are thermally populated. So the lower the energy, the higher the population of the states, and the higher the luminescence. So this is the luminescence plot versus temperature, energy. And as you reduce the temperature, that this lower energy state, which is a trion, gets brighter because most of the population goes to the lowest energy state. And so this feature is the exciton. It's a 200 milliV above. And at low temperature, the exciton is not as bright as the trion, if you assume thermal population. And now we concentrate on what happens to that photoluminescence. And as you change the temperature, what you see that the peak, of course, intensity goes down, but you see the shift and you see the broadening. And so that shift and broadening we explain by the dispersion of the trion, because the left behind pole would be left at finite momentum. Because an exciton, after it's collapsed, it just collapsed. And so the only broadening you can get in exciton is by adding new terms in the Hamiltonian, like exciton-phonon coupling, for example, can give you temperature-dependent broadening. But here I want to emphasize that we see that broadening independent of electron-phonon coupling. And so you can actually see that the data which was measured up to liquid nitrogen matches our calculations very nicely. And we can, of course, extend the calculations down to 0 temperature. And you would predict the deviations from the linear fit at lower temperatures. We see that the trion peak would be red-shifted, consistent with the experiment, and also it would also be broadened. So that broadening is due to the recoil energy, because the left behind pole, you don't collapse 0 Q exit trion. You essentially collapse the trion at finite momentum, and the larger the temperature, the larger the momentum, and the larger the recoil energy, and the higher the broadening. And of course, the shift and broadening, they come together. So 20 milliV broadening is roughly the same as the 20 milliV redshift. So you can simulate those curves at a different topping level, and you can see how that temperature, total oscillator strength changes with temperature. And you see that there is some maximum and a minimum. So this has to do that there is a dark state. So there is a dark state below the bright trion. And so at very low temperatures, you populate the state which is optically dark, which gives the loss of the oscillator strength. And similar picture happens for the exciton. And by the way, those relative energies are this relative oscillator strengths are the same. So you can immediately see that at low temperatures, how the so the trion would be, let's say, order of magnitude larger in intensity than the exciton, but of course at room temperatures, they would be of the same order of magnitude, consistent with the experiments. So you can also look into fine structure of the excitons. You can resolve the very functions of the trion states, and to discuss this dark trion, which is optically dark because of, again, electron and hole in the same valley have opposite spins. So the color coding tells you this is spin up and this is spin down. And so this cannot recombine because of the large momentum transfer. But this is a spin forbidden recombination. That's why this state is dark. So all the rest are bright. So this can recombine, this can recombine, and this can also recombine. So again, you can model it in more details, and you can actually come with a simple model which reproduces the oscillator strength changes with temperature. And you can see that usually in exciton, you also can emit light at Q equals 0, but in case of a trion, there is some envelope function, and you can actually decay optically trions at finite momentum. And so the larger the momentum, the larger the recoil energy, and the larger the broadening, which we observed and explained the data. Of course, there are many states which come up from those calculations. So if you just try to plot density of states, then you can see that this is the low energy spectrum. This is a trion, this is an exciton, they're separated by 20 milliV. But then once you hit the Rydberg states, there are a lot of more states. And if you try to model the spectrum at much higher temperatures, those would be populated. And I think I'm running out of time. Of course, we can calculate dispersion, we can extract effective masses, which are renormalized from the single particle picture by about 20%. So, of course, it depends on doping because the screening depends on doping. It's included in our calculations. And I think what's important here is the energy level splitting between the bright and dark trions. It's of the order of few millielectron volt, and it depends on the Fermi level. So if you dope, then the splitting becomes smaller, and that splitting actually gives rise to the change of the oscillator strengths between the trions of dark and bright trions. So you can brighten your trions by doping in some sense. So I'd like to acknowledge my collaborators, Yaroslav Zhumagulov. He is a student who did most all those calculations. He is now at University of Regensburg, and other collaborators from Russia and Germany. And so this I will conclude that trions and excitons can be calculated on the same footing, means that we use the same level of approximations to calculate both, and we can change the doping level by the changing the number of key points. We predict the new state in the valley exciton, which is going to be bright and at finite doping. We predict asymmetrical photoluminescence spectrum, which would change with temperature. And there is a loss and share of the oscillator strength between trions and excitons, which can be again engineered by the doping and the electric environment. And thank you very much for your attention.
Thank you very much, Professor Vasily. It's a very interesting talk. So now we can take few questions.
Hello, so can you hear me? So this is Samaresh. So you talk about this changing of energy and oscillator strength of this exciton fine structure as a doping or dielectric environment. But in this material, like, like if the vacancies are there, like either sulfur or cyanide, these two materials or these things. So is there any chance, like look into the, like is there any like formalization how these things will change because of the even single, like few defects are there, this vacancy of the like sulfur or selenide vacancy in these 2D materials?
Thank you very much. It's an excellent question. By the way, so I would like to take a chance to say hello to you from John Bird. He sent greetings to you. So it's an excellent question. In principle, I know where you're heading to. This is our, let's say, next big thing. So once you introduce defect in those materials, you form localized states, and they can actually give rise to single photon emitters. And so people are very interested in that subject, in particular, what's the nature of the single photon, with which kind of, because once you introduce the vacancy, what's going to happen, you localize your exciton and you localize your trion. So once you break translational symmetry, the problem becomes much more difficult, but it's still doable. So you have to solve the same problem, but the Hilbert space becomes larger because you mix wave vectors of different excitons after you break translational symmetry. But of course, the details becomes very important. So you need some input from DFT on the localizing potential, because if you change the chemistry of the defect, you will change the Coulomb interactions. And this is actually the kind of, ongoing research by many groups. And of course, in DFT, you can calculate single particle picture, but then how to introduce correlations. So it's an interplay of the complexity becomes higher, but I believe it's a doable problem.
Okay, thank you. So very, very good. So it is an excellent talk. Thank you very much. I think at some point you will come here and visit IIT Delhi at least.
Yes, I was looking forward, but of course, now is not a good timing.
Yes. Okay, anyhow, any more question, other people?
Is there any other question? Professor Vasily, I have one question. So you were mentioning about this PL peak shifting. and also the broadening. So that broadening actually is not symmetric. Is there any particular reason for that?
Oh, sorry, a very good question. Thank you for pointing it out. Yes, of course, the reason is that you start with the, you have a parabola. Let's say you have h squared k squared over 2m plus delta, and you have a left behind hole. So you actually, okay, so when you introduce a high and high k points, you pick up the oscillator strength has k dependence, and this leads to the broadening. So it's like you populate parabola, right, at the bottom of the band, and as you raise the temperature, you have more and more states away from parabola to allow us to luminous. So this is why it's asymmetrical. So this is a very good point. So if you have, let's say, electron phonon interactions, it would lead to symmetrical broadening. But this mechanism would give you asymmetrical broadening. Thank you.
Okay. Thank you. Thank you. Thank you very much. So if there is no more question, let us thanks to Professor Vasily for very nice and informative talk. Thank you very much.
Thank you. So let me stop sharing.
So we have now next talk, Miss Kusuma. Are you here?
Hello?
Yeah.
Ah,
You can please share your screen.
Oh, okay, so 1 second.
And the title of presentation is Multi-Component Alloy Nanoparticle Decorated P-type MOS2 for Enhanced Hydrogen Sensing.
So can you see my screen?
Yes. So please do the full screen and then start. So you have 30 minutes next.
Sir, is it full screen now? Can you see in the full screen?
Yes.
So how much?
Hello?
Go ahead.
Hello. Good evening, everyone. Myself Kusuma. I am a research scholar in Icee Trivandrum. Today I am going to present a paper which was recently published in Nanoscale, which was done in a collaboration with us and which was done in collaboration with people from IIT Kanpur and IIC Bangalore. The title of the talk is Multi-Component Alloy Nanoparticles Decorated P-type multi-component alloy nanoparticle decorated p-type 2D MOS2 for enhanced hydrogen sensing. So the outline of my talk is introduction, preparation and characterization, sensing measurement, discussions and conclusion. So as we all know, chemi-resistive gas sensors are widely studied. Chemi-resistive gas sensors means on the absorption of the gas, we measure the change in the conductivity of the sample, either conductivity or the resistivity. So it has been very well employed in industries. It has been studied from past few decades, and the main focus has been given to the metal oxide gas sensors. And all p-type, most of the p-type and n-type gas sensors are widely studied, and the functional like oxides has been replaced by nitrides, sulfides, and other MOF like recently based new materials, zirconium, and those things are widely studied. Since the metal oxide gas sensors works they need very high operating temperature between 200 to 400. We want a gas sensor which can respond at very low temperature, like either from room temperature to less than 100 degrees Celsius. So upon the introduction of 2D material like graphene and TMDs, the onus has been shifted from metal oxides to the TMDs. As we all know, 2D materials, which is either single atom or single unit cell thick, and it has very strong intra-layer chemical bonding, and it's connected by very weak in van der Waals force between intra-layer. So because of these, it has been very well employed in the areas of electrocatalysis, sensors, biomedicines, photocatalysis, and energy applications such as batteries and electronics. So today, what I'm going to speak is the MOS2 and MOS2 decorated HA nanoparticle in the application to the sensors. So in our case, the sample was prepared by a person from IIT Kanpur. They took MOS2, commercially available MOS2, and they did cryomilling for about 7 hours. So on cryomilling, They did further sonication for about 30 hours, and they could see the reduction in the size of nanoparticles. That is very well evident from the Icee and the Raman shifts shown here. So the EG and AG peak of bulk MOS2 and the nanoparticle MOS2 has been drastically reduced, which will tell us that the thickness of the MOS2 has been very well reduced. And they decorated this MOS2 with the HEA nanoparticle. HEA is high entropy alloy nanoparticle, which is the alloy of 5 metals, equiatomic metal nanoparticles. The HEA has been very well studied, and it has grabbed the attention due to its high structural stability and catalytic activity. And they have mixed 1% of HEA nanoparticle to the MOS2 flakes. So, and they could see the plasmonic resonance of HEA decorated MOS2 nanoparticle around 284 nanometer in figure D, as you can see. That is that's been transferred to even MOS2 decorated HEA nanoparticle. So this figure shows this stem shows the decorated HEA nanoparticle onto the MOS2 flake, and the size of the nanoparticle MOS2 was around 5 nanometer. So these samples were the electrical characterization of the samples has been measured by using 2 probes. Since the sample resistance was high, like mega ohms, the sample was drop casted onto the gold IDTs, and which was measured using 2 probe measurement. Shockingly, we got ohmic behavior of MOS2 onto the gold, and even but MOS2 plus HEA decorated nanoparticles showed the Schottky behavior. But both of these showed the semiconducting nature, that is the decrease of the resistance with the increasing the temperature. To see what is happening, we measured the Schottky barrier height of MOS2 and MOS2 plus HEA in using this IV that we have measured with different temperatures. And we found that by plotting ln of IT square versus 1 by T using Arrhenius plot. So we got the Schottky barrier height of MOS2 as 0.13 electron volt, and for MOS2 plus HEA, it's around 0.19. So the barrier height for MOS2 plus HEA was quite high compared to MOS2. But still, we didn't know why MOS2 was giving ohmic with the gold. So we did some chemical characterization like XPS and UPS to see what is to understand what is happening. So when we took the spectrum of core level MO, like for clean exfoliated MOS2, we observe only MO4 plus peaks, like MO4 plus 3 by 2 and MO4 plus half. So in our case, we apart from MO4 plus, we got 6 plus peaks also. So that was quite shocking, and like studying the literature, we came to know that it's either because of the edge oxidation or the surface oxidation of MOS2 layer. So when we see that was reflected in even MOS2 plus HEA. So when we took the S2P core level spectrum, apart from the this anionic sulfur like S2 minus, S minus, we got some high binding energy peak that is corresponding to SO. So that confirms the oxidation of the S peak. So that was referred to as SO. So the decoration of the HA nanoparticle on MOS2 has further increased the oxidation that is clearly visible in the B figure. So the intensity of the SO peak has been drastically increased compared to just bare MOS2. So that edge oxidation, we can see the defects peak in oxygen core level spectrum. So to see what is the work function of the sample, like to understand why it is giving the ohmic for gold, we did UPS studies also. So generally the MOS2 that is exfoliated gives the work function of around 4 electron volt. In our case, the work function of the sample of bare MOS2 was around 4.4, while that of MOS2 plus HEA was 4. So the work function of MOS2 plus HEA was drastically reduced because of the Fermi level shifting towards the conduction band. Since this MOS2 was decorated with high entropy alloys, that is platinum and palladium especially, since palladium can easily dissociate hydrogen, we thought of doing the hydrogen sensing for the same sample. And the result was quite good. We got around the sensing response of the hydrogen of bare MOS2 and the MOS2 plus HA was plotted here. So the as you can see, there was some 30-fold increase of bare MOS2 plus HCA compared to the MOS2. The hydrogen response was around 30% increase compared to the bare MOS2. And the response and the recovery times were quite high, as we know, because of the like high binding energy of the 2D materials for the gas adsorption. And as you can see from figure A, this follows the power law, that is S is equal to AC by AC per beta, and the peak shift, the response peak shift, the peak, it peaked at 80 degrees. So at 80 degrees, we got around 30% response for the hydrogen, which is very good, with MOS2 plus HES sample. And we did sensing studies for various concentration of hydrogen and with various temperatures also. As it was giving very good response for the hydrogen, we thought we did the selectivity study by measuring the response for the various other gases such as ammonia, NO2, and VOCs, and it was very well selective to the hydrogen. And this was not observed in case of bare MOS2. Bare MOS2 was giving almost 10% response for all the samples, while in case of MOS2 plus HE, it was selective to hydrogen. That's because of the decoration of HE nanoparticle, which was confirmed again. And the stability of the sample was again studied, which was almost stable, which was giving around 40% for almost 3 months we studied, which was almost same. When we studied the humidity response, it was the response was around 40% till 60% humidity, and when we increased the humidity further, the response decreased quite drastically. So as that's because of the incorporation of the passivation of the water molecules onto the surface of the MOS2, which can be eliminated by increase the sample resistance. So when on basis of conclusion, so the MOS2 that we prepared, that gave the p-type response, which was like very unique, and it gave selective good hydrogen response at lower temperature compared to metal oxide. So which can be very well employed in the industries, as hydrogen is very flammable. Even 4 to 65% of it in volume of the air, we have to detect it very fast. So this can be easily employed in industries and other things. And it gave ohmic contact with the gold. So it can be used even in the electronics. Thank you. Hello.
Yeah, thank you very much. Good talk. So any question?
Yes, I have a question. So what is the limit of detection of your sensor?
The sample detected, it was not like few, like 50 ppm and all. We measured the response till 100 ppm.
100 ppm. So didn't you try, or there was some functional difficulty?
Sir?
So didn't you try at low concentration, or there was some functional difficulties over there?
No, it was not that much. It was not giving that much sensitivity at lower concentration. Till 100 ppm, it gave some. After that, the response became less than 10%, and the noise was coming, so it was difficult to measure the response actually.
And have you compared the response time of your sensor with the available literature? Because it's giving in 15 to 16 minutes, the rise time.
Yeah, actually the rise time for the TMDs that is reported till now, it's in the same order, because it has very high binding energy and the stability problems. But the recovery times has been improved a lot on the decoration of the HCA. So whatever the TMDs that is used for the hydrogen sensing, that's almost same.
And with temperature, this rise time or this recovery time can be improved?
Yes, the recovery time can be improved. Even the response time can be improved by temperature. Okay, but yeah.
Is there any other question?
May I ask one question? This is Ankur here.
Please.
Yeah. So it's a very good talk actually. So I'm a bit curious about your this high entropy alloy which you have doped, right? This nanoparticle which you have doped. Is it unique with this 2D materials, or it will be a same thing you can get from oxides also? Means what is the uniqueness about these 2D materials here? If you can elaborate, maybe you have
Actually,
stored.
this sample was prepared by one of our collaborator. So what they did was they gave the equiatomic like 0.2% of thick 0.2%, 0.2 atom percent of all these atoms, metal atoms. I don't think it is selective to only MOS2. I think it can be used for the other oxides also. Since this is this here they had doped the platinum and palladium, we thought of doing the hydrogen sensing. I don't think it is selective.
Okay, so that means any other 2D or any oxides also the
Sure.
similar result we may expect.
Yes,
With
yes.
this
And they had, yeah, they had given one more sample of TMDs with the same these things, HEA particles. So we are under the, we are doing the experiment for those things. So after that, we will get to know. I don't think it is selective for only MOS2.
Okay, thanks a lot.
Thank you, sir.
Kushuma, I have a question.
Yes, sir.
So actually, as you know, this detection the hydrogen timely manner is really critical.
Yes.
So the response time that you are showing actually is quite large, like
So the
10%, 10
response time,
minutes or so.
yeah, the response time here was calculated for 90% saturation.
Yeah, that is a standard way to calculate that.
Huh,
But
yeah.
in literature, actually, you can see the in on MOS2 the response time up to like 14, 15 second or even 20 second up to 20 second is reported in literature.
That might be because of the they had done it at high operating temperature.
No, it is our room temperature.
Okay, okay, sir. I don't have the idea of that.
So what could be the like reason for this?
One maybe because I don't know whether they had used the single like very single layer or multi-layer.
Mm-hmm.
So in our case, it is like maybe 2-3 layers. It's the diameter of the MOS2 was around 5 nanometer. It can't be more than 10 layers.
Thickness.
Yes.
Okay.
So that affects the time. So as the surface area is more, the time increases.
Okay. Okay.
The
Thank you.
response time and the recovery, yeah, that depends on the surface area. So that matters, as I know.
Thank you. Good talk.
Thank you,
And
sir.
with your talk, actually, we close this session. And thank you very much, Professor Samresh. So now it's over to you.
Thank you.
So
Can we stop sharing the screen?
yeah, stop
Yeah,
sharing.
please share it.
So tomorrow 2D material session will start at 11 o'clock in same hall, and we are very thankful. We are very thankful to Professor Vasley because it is in his time zone. He has really taken like around 6 o'clock in the morning. Yes. So thank you very much, Professor Vasley, for giving
Thank you.
impartial talk. And also for the contributor talk, thank you. So we are closing this session. We are now having a plenary talk, so you can join on that plenary talk. Thank you very much, all of you.
Thank you.
Thank you.
फुल चार्ज होईल ना.
बोला, मैंने उन्हें सुना ही नहीं.
Hello.
Yes, sir.
Pankuri, we can continue the session. I think you can call the name of the next person who is supposed to present.
Okay. So,
But let us try to finish in half an hour or so, right? We cannot have
okay. Yes.
very long.
So, Dr. Sagrika Nayak, are you there and are you able to present?
Yes, madam. I'm sharing my screen.
Okay.
My screen is visible.
Yes, your screen is visible.
Should I start now?
Yes.
Today I'm going to speak about the role of spin glass like frustration on exchange bias in two type of exchange bias system. One is iridium manganese and another is nickel manganese. And the exchange bias is studied with iron iridium manganese. Iron is the ferromagnet and other is cobalt iron boron is the ferromagnet with nickel manganese. So we know that the main motivation because there is an interface exchange coupling between a ferromagnet and antiferromagnetic system, and that gives rise to this shift along the horizontal axis of this magnetization and applied field loop. And also there is reports that not only the interface is reason for the exchange bias, but also the bulk of the antiferromagnet plays a significant role in the exchange bias. And also the interface of a ferromagnet and antiferromagnetic system is like spin glass like disorder or maybe compensated or uncompensated. So there are many possibilities, and interface can also be collinear and non-collinear configuration. But in this study we found the presence of spin glass like interface. The reason for the spin glass like interface is basically structural disorder, roughness, intermixing, interdiffusion, like this. And in this study we have used silicon 100 as the substrate. As you know, there is a huge lattice mismatch between silicon and the antiferromagnet iridium manganese and nickel manganese. So we introduced tantalum and copper as a seed layer in iridium manganese iron bilayers, and tantalum and platinum as seed layer in nickel manganese cobalt iron boron bilayers. And also we used copper as capping layer and also tantalum as capping layer in this study. And we have used this squid magnetometry to study the magnetic properties. So we have studied both static magnetic properties and dynamic magnetic properties in these systems. So first I will introduce about, hello? Okay. So we perform temperature and cooling field dependence of action bias to know the nature of the interface in this action bias system. We found both in this system, in the temperature dependent study, we found there is a decrease in action bias field with cooling field, so with the temperature, and also there is a decrease in coercive field with temperature in both the systems. And as we know, in a ferromagnet antiferromagnet system, if there is a maximum value of action bias field, then there should be a minimum value of coercive field, because this action bias is coming because of the pin moment, and coercive field is coming because of low anisotropy rotatable moment. From this temperature dependent study, we can conclude that the interface contains both pin moments and also low anisotropy rotatable moments. And thus we can conclude from the temperature dependent study that the interface contains basically both frozen and rotatable moments, which is because of spin glass like nature at the interface. Also from that cooling field dependent study, we found basically that action bias field with cooling field in both the system there is a decrease, but it should increase, means the action bias field should increase with cooling field, because that with cooling field the number of pin moments should increase, but in our case the number of pin moment is decreasing with cooling field. So maybe the spin glass like interface might be reason for that decrease of action bias field with cooling field. Beside this temperature and cooling field dependent study, we performed training effect data. In training effect data, we took the MH loop. First, we field cooled the sample and took the first MH loop. And after that, we did not field cool the sample, and we took 10 subsequent MH loops, and found that there is a very large decrease of action bias field from n equal to 1 to n equal to 2 loop. But after that, there is a gradual decrease of action bias field. There is not any uh, large large decrease like first n equal to 1 to n equal to 2. So we
Hello, Sagarika, please wrap up. Huh?
Yes, sir. So we fitted the action bias things with various models, and we could not fit the action bias field with thermal relaxation model. Therefore, we cannot say that interface is ferromagnet antiferromagnet. However, the fitting of the data other models is considered spin glass like interface. We found that training effect data is fitted. Training effect data is best fitted. And next, in all the study, we say that the interface is spin glass like, but again in nickel manganese cobalt iron boron system, we perform AC susceptibility. The bulk of nickel manganese is also spin glass. Therefore, we fitted the data with Vogel's structure and found that that bulk of nickel manganese is also spin glass. So we can conclude that both spin glass like interface and spin glass like ball might be reason for this trend of that cooling field and temperature dependent study. And also from the variation of action bias field with thickness, or says that bulk of the antiferrous contributes to action bias thing. And from the fitting of the training effect data, we can say that both frozen and rotatable spins are present at the interface, which contribute to the training relaxation. And uh, this is the thing. And then finally, I would like to acknowledge DAE, DST, SCRB, DST, Government of India for providing financial support for carrying out the experiments. And I also finally would like to acknowledge my supervisor, Professor Subhankar Vedanta.
That's fine. Actually, there's no time to hear to the acknowledgement. That is written, right? So, is there any question from the examiner?
No question.
Okay, so
Hello?
we'll go to the next speaker.
Yeah.
The next speaker is Abhishek Mishra. Is he present? Abhishek Mishra, are you present? Then the next speaker is Miss Gulaksha.
Gulabsan. Gulabsan, can you share your slides, or we can also share? Pankuri, you can also share,
Yes.
no?
Yes, yes.
Oh, he's doing it. He's doing it. So, very briefly describe, not more than 3 minutes. Hello? We are not hearing you. Gulabsan, we cannot hear you. I think you are muted or you have some problem with the. It doesn't seem you are muted.
We cannot hear you, Gulab Shah.
Yeah, let's go to the next participant.
Okay, the next speaker is Mr. Nane Kumar Gupta.
Hello. Hello.
Hello, hi, yes, sir.
Am I audible?
Yes.
Ah, yes. And Nanne, you can share the screen if you want, and please.
Yes, sir. I'm trying to share it.
Or I can share also.
Pankuri, can you share it? Actually,
Yeah,
net
yes,
is okay. Thank you. Thank you, Pankuri. Hello. Hello.
Ah, yes, please continue.
Okay, okay. Very good evening. I am Nanne Kumar Gupta from IIT Delhi. I am going to present my poster entitled as the comparison of annealing environment of MNGA thin films. Mostly why I'm choosing this topic because due to the high spin polarization material and high perpendicular magnetic anisotropy, ultra low damping constant like 3 into 10 to the power minus 3 and high Curie temperature. We can use it in various applications: spin valve, MTJ, MRAM, and permanent magnets and other spintronics device. The phase of this MNGA magnetic thin films are very crucial to growth with any other technique like CVD and PVD. We have chosen PVD and sputtering, pulse DC sputtering. The crucial role of this gallium is very important. Here we can see from phase diagram this gallium role. I mean, just 40 in the magnetic phase occur only 40 to 45%, but some few results shows the MN50 and GA50 I have chosen in the composite target of MN50 and GA50 and growth with 80 nanometer films at room temperature and anneal in different environments such as vacuum and argon in ambient argon at 400 degrees centigrade. Here we can see from XRD measurement there is a gradual change. First of all, we can see the degree of filtering enhanced in both annealing environment, and also XRD reveal the coexistence of this cubic and tetragonal phase. Here we want the tetragonal phase because tetragonal phase is more ferromagnetic than cubic, but there in both cases there is a simultaneously coexistence of this cubic and tetragonal phase. Also, when we calculate this uh, lattice constant, and we find this is nearly same about reported value, and from X-ray reflectivity measurement and atomic force microscopy measurement shows that the MNGA films anneal in argon ambient is more smoother than the film anneal in vacuum, because at the total minimum free energy is overcome by the local changes in MNGA film. We can say this: there is ice-like growth in argon ambient, and there is a layer by layer growth in vacuum ambient. From transport measurement, we can say that the when we anneal in vacuum, there is a semiconducting nature, and it changes when we change the annealing environment, like vacuum to argon ambient atmosphere. This shows the gradual change of it might be due to the when we anneal in argon, there is a vapor pressure. The gallium have more vapor pressure and changes this composition. The Mn we can also see from field emission, field emission scanning electron microscopy measurement, this composition and structure analysis. Also here we can see the atomic percent of manganese changes, like when we anneal in vacuum, it found to be 56, sorry, it found to be 70. When we anneal in argon ambient, we found it 70. Just here we write 70 Mn, magnesium is 70 and gallium is 30. This is due to this is the decrease and increase of vapor pressure during changing the environment. Fine, and also we can see from the magnetic measurement. I have performed the in-plane magnetic hysteresis measurement. Here we can see this: the high saturation magnetization and low coercivity found in sample annealed in argon and argon environment. It is due to there is a preferred texture found of tetragonal phase in. Hello, am I audible? Hello. Hello.
Yes, sir, you are audible. Yes.
Yeah, thank you. Due to the preferred orientation found in sample annealed in argon ambient, finally we can calculate that the XRD measurement reveal the coexistence of both tetragonal and cubic phase, and also the strong dependency of annealing environment as well as annealing temperature for the growth for the desired phase. And also FSM analysis shows the gradual changes in morphology and composition also. And hysteresis measurements, magnetic hysteresis measurement shows that there is a more fraction of tetragonal phase. Thank you.
Okay, thank you. Is there any question?
Hi, Nanne.
Yes, sir.
I am just wondering why MNG is not used in place of this other metallic ferromagnet in the mainstream spintronic research or even in the MTJs and spintronic industry. Is there a reason? Because I don't know. Can you tell me?
Sir, can you repeat? I'm not hearing you.
Why MNG is not used in place of this other metallic ferromagnets we have, like iron, cobalt, and all that in the mainstream spintronic research? If you see, what reason?
Okay, actually people are using in MTs if material have like moderate saturation magnetization, like cobalt, iron, boron, and also the crystallinity. Sorry, sir, I will see it.
Okay, no problem. Thank you.
Thank you.
Yeah, let's go to the next.
Yes. So the next speaker is Mr. Khatru Imtiaz Ali Khan.
Hello. Hello. Hello.
Yes, please go ahead.
Okay, sir. Let me share my screen. I will try to share my screen. It will works or not.
Yeah.
So, are you able to see my screen?
It was there, but it went back. I think.
So that was my
Stop
screen.
sharing.
That was
okay.
nice thing.
This is now I shared the screen. So can you see?
No.
Okay, Pankurish, you share. I will share.
Oh. Yes, that you can start.
Actually, I cannot see that you shared.
We can please speak. Oh.
Sir, okay. If you can see, like I can tell that. Okay, sir. So myself, Kalcho Imtiaz Ali Khan. So my topic is that we tried to nucleate antiferromagnetic fermion using in-plane spin polarized current, and we are in this work we are trying to compare the polarization direction to nucleate the FM fermion with Z polarization and in-plane polarization, which is Y polarization. It can be a Y X also. So for that we in this left top corner you can see they use the Lagrange equation to govern the FM nucleation and use a topological charge value equation to calculate the topological charge, and we use these parameters for the simulation. In this simulation, so we tried to inject a pulse, current pulse at a center of the AFM lattice. So we were able to nucleate the AFM fermion and at a 5.5 picosecond. You can see that in right topmost corner, you can see the graph for energy and both topological charge. You can see that when the pulse width is greater than 5.5 picosecond, the nucleation is possible. So, but greater than 5.5 picosecond, you have an antiferromagnetic state, and below this, you are going to a ground state, FM ground state. So from there we extract the threshold pulse width for the nucleation of AFM fermion for in-plane case. So similarly, we did a current dependence, how current is depend on this threshold pulse width and nucleation time. So we calculate the nucleation time and as well as threshold pulse width for the both case in plane and auto plane. So we found that for the auto plane case, these values are much larger as compared to in plane. So from this result, you can see that in plane spin polarized can be much efficient as compared to auto plane. So we try to see the trajectory of these spin when these spins are switching. So we try to see the trajectory in frequency. So we check for the frequency, then we get the frequency of around 1 terahertz for the both case, but the trajectory is different. So you can see in this color left bottom corners, you can see that there's a graph of 3D oscillation. So in which you can see that the SFP in plane is in plane polarized, which is with in plane, and the oscillation which is coming from auto plane. So you can say that the auto plane spin polarized current needs a higher threshold pulse width as compared to in plane. So here also we can see that in plane is much better than auto plane case. So at the last we try to nucleate multiple AFM fermion by changing the pulse width at a higher current density at 3 into 10 to the power 13 ampere per meter square. So at this higher current density with a different pulse width, choosing the different pulse width, you can control the AFM number of AFM fermion. So you can see that the topological charge as well as the schematic in this figure, and the values of nucleation time and the number of fermions is summarized in this table. So I would like to conclude my results that we are able to create a nucleate AFM fermion of 30 nanometer, around 30 nanometer, with a threshold pulse width of 5.5 picosecond. And this in-plane spin polarized can be much efficient in current in terms of pulse width and also in terms of nucleation time. By using this in-plane spin polarized current, we can also nucleate multiple AFM fermion. So that's that's all for my talk. Thank you. Hello.
Which simulation framework did you use in this? You used FOAMP or is it your own?
No, it's a Mumex. I mentioned this is simulation parameters. Yeah.
And one comment I have, this value of DMI 3.5 millijoule, I feel it is a bit high, or is it normal for N2?
No, I can understand that this is not possible to achieve in experimentally. You cannot achieve, but this is the simulation result. So people use these values around. People even use higher values of DMI, like around 4 into
Yeah,
10.
but that's right. But
But
I mean, the simulation value would correspond to the real life
yeah,
condition. So maybe
exactly.
you try
But
to reduce this value.
yeah, I can do that. But here our more major we want to see that this comparison between in plane and out plane. For the both the
Okay,
case,
okay,
we put the same value. So
okay, okay. Thank you.
yeah, thank you.
Thank you, Patu. So the next speaker is Ms. Namrata Bansal.
Should I share my screen or okay? Shall I start? Hello everyone, I am Namrata Bansal from Indian Institute of Technology, Delhi. So topic of my poster is the interfacial Zalichinski mode interaction in graphene NIFA system determined using the Bragg-Book technique. So I start with the introduction part. Zalichinski mode interactions arises when the two adjacent spin angular momentum trying to align themselves in the perpendicular direction. Similar to these type of interactions, interfacial DMI are found at the interface of ferromagnetic and heavy metal system. So in this work, we have used graphene in place of heavy metal system, as we have already quantified DMI in the thin film of graphene and IFA system, but using a sophisticated technique. In this work, we are using some other technique in which we have fabricated triangular microstructures, in which during Moog measurement, due to in triangular shape, due to the absence of two-fold rotation symmetry, so a shift arises in the hysteresis loop, and this shift is proportional to the DMI strength, which we are using in this work. So in the sample preparation, we have taken a high quality of monolayer graphene sample and a silicon oxide sample on which we have fabricated an array of equilateral triangular in which we have deposited NIFE using magneton sputtering. And now we proceed to the characterization part. So FSR measurement confirms a good fabrication quality in graphene and non-graphene sample. Now we proceed to the MFM measurement, which we have done on the graphene sample. So these are the MFM images which we can see at the different value of magnetic field. So here we can see that on at 0 Gauss, the magnetic MFM image look like this. If we increase the magnetic moment to 1000 Gauss, the magnetic moment changes drastically. And if we decrease the magnetic moment to 0 Gauss, and it again changes. And if we change the direction of magnetic field, here we can clearly see that the direction of magnetic momentum also changes drastically. Now we proceed to the MFM simulation, which we have done taking two conditions. That is, one is with DMI and other is without DMI. So in the DMI part, we have applied two different magnetic field direction. So here we can see on the upward direction, magnetic moment are in the downward direction in the up. So these simulation work is basically confirming our experimental work, through which we have confirmed that our graphene sample contains DMI. So this is a valid proof that we have. And now we proceed to the Bragg-Book technique. This arises when we take the periodic array of magnetic feature. And if we apply the incident beam, so in place of reflection, we observe the diffraction pattern, and this is the diffraction pattern which we have observed during the measurement. So the highest intensity has been taken as zeroth order, and the adjacent one has been taken as first, and the next adjacent as a second, and so on. So now we proceed to the Moog measurement, that is a Bragg-Moog measurement, which we have done for the 10 nanometer and the 5 nanometer. The first case is for the 10 nanometer, in which there are three samples. The first one is the non-graphene thin film. Second one is the patterned non-graphene sample, and the third one is the graphene sample, which has triangular microstructures. So in the first case, that is the thin film, the shift is 43. For the non-graphene sample, which has pattern, it has a shift of 43.2 Orsted, and for the graphene sample, which has pattern, it has a shift of 62. So here, if we take the difference of these shift, it is coming out to be 19.6 Orsted. So here we can observe that for the graphene sample, the shift is more as compared to the
non-graphene sample, which we have already discussed that we are looking for the shift in the hysteresis loop, which is proportional to DMI. So here we have observed the more shift for the graphene sample. So now we proceed to the second sample, which has a thickness of 5 nanometer NIC.
I think you have exceeded the time.
Okay. So, in the second case, we have also again observed the shift more for the graphene sample, and also in this work we have observed more shift for the lesser thickness of magnetic material. So through this work, we want to conclude that we can use Bragg-Mook technique as a convenient tool for determining GMI instead of using some sophisticated technique. So this is all about this work. Thank you very much for your kind attention.
Just one question I have. This for Bragg-Mook technique, I'm not familiar. So do we require the triangular pattern, or it works on any periodic pattern, square or?
It could be any pattern like square. We can. It must be a periodic array of any
Periodic.
shape.
Okay.
Yeah.
Thanks.
Yeah.
That answers.
Okay, so the next
Okay,
speaker
please
is
go to the
Mr.
next.
So the next speaker is Mr. Mohan John Rex. I think he is not in the participant list, the present participant list. So next poster belongs to me. So good evening, everyone. My name is Pankhuri Gupta, and I am discussing this work entitled Observation of Spin Backflow in IRMN-based structure. So as explained in some previous posters also, that the magnetization dynamics can be explained by this LSGS equation. So in my work, I am using this ferromagnetic antiferromagnetic interface, which is beneficial to study the spin pumping and this exchange bias simultaneously. So as in the experimental technique, we are using this ferromagnetic resonance based on coplanar waveguide, where this RF source is used, where the RF current is applied, and we are measuring the transmission voltage via this lock-in amplifier. So in this work, we are preparing the samples with AJ magnetron sputtering system. We are making two series of samples. One is the NIFE IRMN structure, and the other is the opposite stack, that is IRMN NIFE. So both the samples are prepared in an in situ magnetic field of 200 Oersted. So here we can see with this Moog loops that for the case of NIFE IRMN, we are getting the exchange bias, while for the other case, we are not getting the exchange bias shift. This exchange bias is further confirmed with the ferromagnetic resonance. So here we can see this is a case for the exchange bias system, and this is the case for non-exchange bias system. So we can see that the resonance fields for the positive field side and negative field sides are different. So for this case, these are almost similar. So we can say that the exchange bias is present for one system. Now, when we plot this line width versus frequency, we are getting different Gilbert damping. So we observe this unidirectional Gilbert damping in the case of NIFE IRMN, but the slope for both the field directions in the non-exchange bias system is similar. So there is no exchange bias, neither exchange bias nor the unidirectional damping. So in this case, here we have the antiferromagnet-ferromagnet interface, but we didn't have the exchange bias. So to study this series more, what we do is we make a reference sample of NiFe platinum, where this with the platinum thickness, this alpha is increases, which is already well reported. Now, when we place the platinum on both the sides, again this alpha is increases and saturated up to a value. But in the third case, when we replace this bottom platinum with the IRMN, initially this alpha is decreases. This decrease is due to the spin backflow. And then after a certain thickness, then there is an increase in the alpha, which comes due to some contribution of spin pumping from IRMN. So to summarize this result, we obtain the exchange bias in the case of NIFE IRMN, but not for the IRMN NIFE case. And the unidirectional damping is also observed for the exchange bias system. And the third is we are getting this spin backflow for the IRM, the non-exchange bias system. Thank you.
So what is the reason that there is no exchange bias in the inverted structure? Are you investigating it, or?
Sir, yes, we are investigating it, but the one guess is that when we are growing IRMN initially on the substrate, then they are not properly aligned, and then at the interface basically there is no spinning takes place. However, if we anneal the heterostructure that we form, then there may be chances of getting the exchange bias, but our samples are unannealed samples. They are just prepared in situ magnetic field.
And one more comment is for this very thin iridium manganese, let's say less than 2 nanometer, you should be careful because they may not have antiferromagnetic ordering. Thank you.
Okay. Thank you. So the next speaker is Mr. Ram Singh Yadav. Are you there?
Yes, ma'am. My slide is visible, ma'am. Hello.
I am already sharing your slides, so you can just start explaining this.
Okay, okay. Thank you. Hello everyone, my name is Ram Singh Yadav. I am presenting the poster with title Dependence of Perpendicular Magnetic Anisotropy on Fe content in tantalum CFB MgO heterostructure. In this study we have studied the PMA in tantalum CFB MgO heterostructure with two composition of CFB cobalt 20, iron 60, boron 20, and cobalt 40, iron 40, and boron 20. From the recent perpendicular magnetic isotropy is magnetic anisotropy in which the axis is out of plane of the film surface. From the recent theoretical calculation, the origin of PMA in FM and FM oxide heterostructure is attributed to the hybridization between oxygen 2p orbital and transition metal 3d orbitals. In the case of PMA, switching efficiency is faster and good thermal stability, and which is good candidate for the STP and SOT membrane. We have deposited tantalum CFB MgO heterostructure using AJ magnetron sputtering on silicon substrate for two composition of the CFB. We have annealed the sample. After the deposition, we have annealed the sample for 1 hour under at 300 degrees centigrade under high vacuum condition. After we have done the longitudinal and polar mock for as deposited and annealed sample. From the polar mock, it shows that its easy axis is out of plane, and which also changes when the sample is annealed due to some crystallinity in COFB. After that, we have done the Hall measurement for the annealed sample at 300 degrees centigrade. Ma'am, can we zoom the slide? Hello.
Yes, sir.
Can we zoom this AH in our AHE measurement slide part?
Which one? This one?
It's not needed actually. We just tell whatever you want to tell.
After that, we have done the Hall measurement, and for the annealed sample in a Hall measurement for the ferromagnetic samples materials, we have two contribution. One is from ordinary Hall effect and another is anomalous Hall effect. From the Hall measurement, we also concluded that for the CFB with composition cobalt, iron, boron 40, 40, 20, it will good loop which is shows that some good PMA in comparison to cobalt 20, iron 60, and boron 20. is something we have shown that in case of cobalt 40, iron 40, and boron 20 has good PMA better than in comparison to cobalt 20, iron 60, and boron 20. And these are the acknowledgement. Thank you.
Okay, well, let's go to the next speaker if there is no question.
So the next speaker is Mr. Avinash Chaurasia. So Avinash Chaurasia, please.
Yeah, I'm here. Let me share your screen.
Okay.
Can I share because here some problem. It's covering some part.
Okay. You can share.
Can you see the screen?
Yes, we can see.
Okay. So the title of my talk is basically the flexible artificial multiferrite composite based magnetoelectric system. So you see the title is multiferrite. So what is the meaning of multiferrite here? Basically, we have more than one ferric order here. So one ferric order is ferroelectric and another is a ferromagnetic. So we choose the ferroelectric as a PVDF material and nickel ferrite as a ferromagnetic material. So why we are saying here artificial? Because we do not use the material which have both property in the same material. So we combine these two materials to make the artificial multiferrite. The advantage of using these artificial multiferrite is that we can use independently to maximize the coupling between the ferroelectric and ferromagnetic component. So the idea was how we can get the room temperature magnetoelectric coupling in flexible artificial multiferrite systems. So for that, what we did, we used the PVDF and we added different amount of this weight percent of nickel ferrite in this matrix, PVDF matrix. And what we observe here, like basically with the increase in the loading weight percent of the nickel ferrite nanoparticle inside the PVDF, our basically the magnetoelectric coupling we observed for 40 weight percent. As you see here, for the 10 weight percent, this is not forming the loop like behavior. That means there is no magnetoelectric coupling. It's just showing the dielectric behavior. And at 40 weight percent, we can see the loop like behavior. So that means when we sweep the magnetic field, it is like loop like behavior. So there is a like confirmation that it is showing the magnetoelectric coupling. So the why we are doing this, we did this experiment. The idea is to basically control the magnetism by using the electric field, but there are several other materials. But in the case of the flexible multiferrite, we need to have some flexible materials that can be used to do some wearable electronics, and for that we use here the PVDF as a ferroelectric and nickel ferrite as a ferromagnetic. So as you see here, we did the structure characterization and then particle size analysis from using the transmission electron microscopy measurement, and then we did the dielectric measurement. So you see, as for the increasing the weighting, basically the loading weight percent inside the PVDF matrix, the dielectric constant enhanced. It is around 25 here and it becomes like 90 at low frequencies, and at high frequency it decreases. So these are the basically evidences that when we increase the loading inside the PVDF matrix, this dielectric property enhances. At the same time, when we do the IV measurement, basically these kind of IV measurements is basically for the piezoelectric material, which is basically our PVDF material. So when we sweep the electric, it's basically the voltage from the red curve from 30 volt to minus 30 volt. So as the polarity changes, there's sudden increase in the current. So that basically indicates there is a polarization switching at some particular voltage. So that voltage is defined as basically the quasi-electric field. So when we go from 10 to 40, we can see the leakage current decrease. That means the insulating property of the material enhanced. So that confirms that the also that the material has a more basically the electroactive phase. That is basically helping in getting the magnetoelectric coupling at room temperature, because the magnetoelectric coupling is basically the direct product of the magnetostriction and the dielectric property of the basically the material. So with that, I'll conclude it. Thank you. So any question?
If there is any question?
There is no question,
No,
I
no,
guess. So go to
I'm
the
okay.
next.
Okay.
Go to the next.
Gulasha is asking again. So, Gulasha, are you there? Hello, Gulasha. Are you there? Are you presenting? Also, there is another participant, Shilpi. She is present in the talk, but she didn't present. Shilpi, are you presenting?
Yes, I want to present.
Okay.
This last speaker, Anulika, there is.
Sir, no, sir. I think she didn't submit the poster. They just submitted the abstract. Yes.
Okay.
Shilpi, I think Shilpi is there, so Shilpi is presenting.
Yeah.
Yeah. Okay.
Ma'am, can you share the?
Yeah. Okay. Okay.
Can you see my screen?
It's coming, but not completely. Yes, it's coming. Yeah, I can see it.
Wait. Ma'am, it will be better if you only share the screen because
Okay.
my
Okay. Okay. Okay.
Johnny.
Okay. Good evening, teachers. What my topic is to explore the doping of Fe3O4 in a 5Cb pneumatic liquid crystal matrix. For that, why it is important is that we want flexible. Some places we want flexible devices which show magnetic properties. Also, we want to if we require devices which have flexibility and they show magnetic properties. So for that, what we chose is 5Cb liquid crystal and magnetic nanoparticle, which that is Fe3O4. What is the property of what is important in 5Cb liquid crystal is it is excellent in electro-optical devices, but it is very weak in magnetism, or it is a diamagnet. So our aim was to induce magnetism in that so that we can get a magneto-electric as well as a magneto-optic device. So for that, we have chosen Fe3O4 nanoparticle. We took the FESEM and TEM image of Fe3O4 nanoparticle, and the particle size that we got from that was 140 nanometer. We doped it in liquid crystal, that is 5Cb pneumatic liquid crystal, and what we saw was purely diamagnetic liquid crystal. It converted into a soft ferromagnet. It started showing soft ferromagnetism after doping with it. The science behind it is that there is a magnetic director and a pneumatic director coupling, which leads to such behavior. In addition, also needle rotation and Brownian rotation of the magnetic nanoparticle inside the liquid crystal matrix leads to such ferromagnetic behavior seen in liquid crystal after doping it with magnetic nanoparticles. There is when it comes to the dielectric behavior of the liquid crystal also changed after doping it with magnetic nanoparticles. That is, the surface of the magnetic nanoparticle started acting as a desorption site, and it started releasing ions. Also, there was no change that was observed in a Frederick transition voltage, electric field Frederick transition voltage, that is the reorientation of the molecules in the presence of electric field. But in future, we will also exploit magnetic field Frederick transition effect, which is a future scope. So, this is all what I wanted to present.
What is the application of this liquid crystal? I'm not familiar.
Sir, liquid crystal is it is basically it is used in electro-optical devices like our TV, in smart windows, in smart.
Okay, you mean that? Okay, liquid crystal. Okay. Thanks.
But it lacks in magnetic component. So our aim to provide fluidity to this liquid to induce it is a diamagnet. So our aim was to also make it magnetic, so that we can have a multifunctional device which can respond to electric field as well as respond to magnetic field.
Makes sense. Thanks.
Okay, so Gulabsha, are you able to connect now?
Is there anybody else who was not presented?
No, sir. Only Gulabsha is a person who is there, but she is not able to present. Maybe we can close the session.
Then you can, I think you can stop because we cannot wait for very long. So I think thank you all the poster presenters, and I also thank Professor Rahul Mishra and Professor Pintu Das who gave their time to share these posters. And yeah, that's all. So for now, you can take some rest.
Thank you.